They will share. Once you start, they will share. Okay. Okay. So I'm going to quickly start the proceedings of the day. So thank you all for coming, all the way from all the parts of the country, as well as there are people coming from IIT Bombay. So we are very gratified by the response, and thank you. And Sudipta, welcome back. And before we start anything, we'll let the Department of Chemical Sciences Chair, Professor Deepa Kushlani, give a few words of starting.
Okay, thanks, Jade. So I get to do something that, first of all, I want to start off with acknowledging Jyotishman. Everything, the entire pack schedule, we're starting at 9 a.m., hence the sparse audience in the auditorium. Sudipta, forgive us, but it has to be a 9 a.m. start to fill in all the people who wanted to participate with your felicitation. So it is an early start. There'll be people on Zoom, and obviously people will be coming in as the session proceeds. And so at the start, this is for the students, the new students. I thought just to introduce you to the person who is unfortunately left TIFR, leaving behind a huge void, but to tell you a little bit about how he joined TIFR. So I'll give you a little bit of his CV. His academic started at IIT Kanpur, where he did his undergraduate degree. He moved to States in Rochester, where he did his master's. He did his PhD at University of Pennsylvania, and then he did a postdoc at Cornell, staying in that northeast part of the States. And then subsequently, he returned to India. If I understand correctly, he had a short stint in IIT Kanpur, and IIT Kanpur's loss was our gain because he ended up joining TIFR permanently and did not leave for the entire of his major chunk of his research. So he joined TIFR in 1998. For the next 26 years, he has embarked on this fantastic journey of pursuing biophysics with an incredible amount of passion. And his work and everything will be detailed today. I am not the best person to talk about his science. Suffice it to say, he's one of those very rare individuals who's been trained in, or his degrees are in physics, who has worked in the chemistry department, but who's approached, I would say, predominantly biology-based research portfolios. So, encompasses all of the natural sciences, as it were, and it takes a true character, and it's a testament to his education, his knowledge, his passion for science, that he can do this so effectively that he has friends in all these three domains. And obviously engineering, by the way. So he's also pursued not only fundamental science, he's also pursued instrumentation in terms of fabrication and creation of new instruments that sort of help this sort of advanced research to the point where he's been able to market it. They've been patented internationally and so forth. So you can understand the breadth of his knowledge and how an exemplary scientist he has been for his entire stay here. And therefore, you can appreciate the reason we are celebrating his work so on this grand scale. Having said all this is on behalf of DCS. I would like to ask Shankar, but just before he gets up, I'd like to personally thank Sudipta for everything he's done for the department. It has been truly invaluable, and you leave behind a large void, which is difficult to fill.
So I first met Sudipta in 2002, probably. He was giving a talk in ISC. I was a student. And after that, we have been interacting. We've talked about colloids, spinodal decomposition, two-fluid interface, demixing. Never got a chance actually to work on a problem together with him. But every discussion that I've had with him has only enriched me. There's a small incident that, this is for the students. So Rajaram Nityananda is a astrophysicist, but a person of Renaissance character who likes optics, and both me and Sudipta have their interest in optics. Rajaram was holding classes for us, basically teaching us classical optics, Fourier optics. And this was held at what you call as a Maratha stores today, that room. And Rajaram, being a person that he was, is to give us tutorials. And the person who would do all the problems, sit through the recess and do all the problems was Sudipta. Everything. Okay. So overall, as science has progressed, TIFR might be a different place, but usually scientists have started seeding out instrumentation building capabilities to companies or engineers, basically companies build for you things, they do a very nice thing, and you do your experiments. Sudipta is one person who not only had a passion to do his instrumentation, that's okay, fine, some of us have, but also had the passion to go up and do these entire schools where in those days almost unheard of. You'd basically make people build those fluorescence spectrometers for autocorrelators and things like that, put them together. And I know for sure that many people have told me that they have actually used those instruments for their research papers. That's a testament for himself. Personally, I've always enjoyed talking to him. I would say that, his departure from here is a personal loss for me. It's loss for anybody, but it's also a personal loss. Did I agree with him always? No, I did not agree with him always. The best part of him was that you could disagree with him. The experiment was perfectly okay. That you can disagree and yet be absolutely good friends, kind of a brother to me more than friend. Is a nice feeling. That helps us to be in an environment where we can discuss, disagree, and come to conclusions. It's not great to see Sudipta leaving this place, but more he comes back, and now I know that will be a couple to the TIFR Hyderabad program, and I will see a lot of him probably here as well in Hyderabad. It's a new phase in his life. I wish him all the best. Thank you.
Okay, so thank you, Shankar. Thank you, Deepa, for starting out with very nice words, and Sudipta, thank you for coming back. And I will start the session, but just before that, since I will not be speaking at all during the entire program, maybe at the time of 4 to 6 p.m. reminiscence. So this event is basically all our love poured together to you. Okay, so one of the eminent reasons is that when I had a chance to come to TIFR as a VSRP student, you made a big difference to me in terms of how a student looks up to a faculty member. And typically, the way I have been trained from the education background that I had from IIT Kharagpur, we used to have a huge amount of fear talking to all the teachers, all the professors there. And somehow at TIFR, this feeling is strangely missing. Whenever you enter as a VSRP or as a PhD student or as a visiting fellow or any kind of, this fear is strangely missing, and you were one of the people who enabled that. So, and of course, from the day one, I recognized this man is special. You talk to him for 2 minutes, you recognize this man is special. You see him, I've seen you over the years. We have seen all across, and even forget about the discussions, even the questions that is asked in a seminar that you have, the questions, they are all in depth. They are all well thought. You are not asking a question to test the speaker, but you're asking the question to enable the speaker look for the answer. So this is something which is different. And thank you for inspiring many of us in this department. And I will come back to some of the things later, but I just want to say that this event will not be possible with some support from the sponsors. There are a couple of industry partners, and let me tell you, for a Sudipta symposium, it's not that difficult because all of them have benefited from whatever he has started in the country, for the contributions that he has put in. This set of people who have supported us, absolutely, no questions asked. And I thank Atos, Hallmark, Laser Spectra, Zeiss, and of course ACS, because Sudipto happens to be an editor in the Journal of Physical Chemistry. So all of them will join at some point. There is an industry talk as well after the patent that was granted, and Hallmark built an equipment. So we'll have that discussion. But without further ado, I want Biddut to come forward. I don't know where he is. Yeah, as the session chair, and Biddut, you can start the program, and you can have a few words for Sudipta as well.
Yeah. Thank you, Yatishmanda. Yeah. Yeah, it's kind of a very strange feeling that Sudipta has left TIFR. Still, it hasn't sink in. And for me personally, I would say when I joined TIFR and doing the lab rotation, after spending the week in Sudipta's lab, it was sort of the easiest decision where to join for my PhD. Okay, and then it was a very enjoyable journey throughout, and then I've always learned and still learning from him, and I think it will continue. So, so now coming to this session, we have three wonderful talks. I think he had very a lot of wonderful colleagues in TIFR, and this session will have three talks: one from physics, GRK, then a long-time collaborator from biology, Virita, and then from DCS, Koti will talk. So first, I actually invite GRK to start off with. Thank you.
Can you hear me? Oh, good. Firstly, good morning. And Sudipto, nice to see you again. I hope very often, even though you're going to be geographically away. And firstly, thank DCS for having me stand here today. I think it's all because of this guy called JD, who is man of many talents. And he said, when this was conceived, he said, we're going to have a symposium to just recollect a bit of what Sudipto has done at TIFR and elsewhere. And I'd like you to start. I said, what am I going to do? So it was not so difficult as you imagine, but then I've had so much of interaction with him. So this is what made me wonder why I'm standing here today. Share nahi kiya? Okay. So how does this happen? So it was a big challenge for me, but then I realized that I'll just pick out a little bit from my interactions with Sudipto, and these are not just anecdotes, these are not just corridor conversations, but actual science, right? Which I can talk about over the next 15 minutes or so. And Deepa tells me the schedule is very tight, so I'll stick to the 15 minutes. So, yeah. So can we move this away and take a picture? I want this preserved for, memory. Okay, so you might wonder why this kind of a first slide. I'm sure by the end of it, you will know what I'm actually meaning, right? Okay, and good to see also my friend from that time, and of course, long-term friend Balaji here. And the other people are not, I don't know if they're on Zoom, but welcome to the people on Zoom too. Some of them might know me. So why am I standing here? Because most people in this building, and probably in TIFR, know me as somebody who does this, right? Very powerful laser, hits something, blasts everything out of place, out of shape, and does all my colloquia at TIFR have been on this topic. So you create extremely excited state of matter, which is far from the chemistry, biology that we all normally like to have. And then you explore, you sort of find out what goes on in this exotic, high density, high energy density state of matter. So blast everything out of place and out of shape. And, but there's an older part of me, right? Which is not known to many people, hidden away for whatever reason by natural evolution or by myself, where I worked in gentler environments, like and bonded with many chemist friends. In fact, in the 90s, I had lots of chemist friends. I hope I still have them, but they were more friendly to me because we were working at that time. They helped me with wonderful molecules that I was using for my experiments. And I used to know lots about porphyrins, phthalocyanins, tetratolyl porphyrins. That's as far as I can go. And even bacteriorhodopsin, right? So I have a little bit of encounter with that too. And the reason was that, as all of us know, optics is, for most of us, this is what optics is. Can I move this with this? Yeah. So for most of us, it's just this. You have, I think this will work. Yeah. So you have, is this on? Yeah, otherwise I'll just move it myself. Yeah. So, okay, so you have light shining on a molecule or an atom, the electrons get jiggled around, then a dipole moment develops, and the dipole moment then re-radiates your signal. You call it fluorescence, scattering, whatever you want. And for most of us who use optics even in our research, it's all very gentle kind of, with small electric fields, low light intensities, and the electron motion is harmonic. And this is the spring mass model, which every undergraduate knows, that the electron jiggles around a little and then radiates that energy. But if you go to higher and higher intensities, ever since the laser was invented, people then realize that this story gets more complicated by the addition of higher order terms, E squares and E cubes and so on. So there's a perturbation expansion, but the higher order terms become significant. And the thing to talk about is that, this chi is the dominant one among all the responses, but chi2 is not so dominant, maybe 1,000,000 times smaller. This is a trillion times smaller than this. But then if you have a large E, the E square makes it appear like a significant signal corresponding to the dipole moment. So this is unharmonicity. And there's several things that people have known now. The literature is, exploding with all these phenomena, and many of them used by biologists, chemists, physicists for all kinds of applications. But the most crucial one that I want to talk about here is this process called in this case, two-photon absorption, where you couple a ground state or a lower state and upper state by not one photon, but two photons here, but typically multi-photons, right? So many, many photons. And the beta is very small typically, so you need a large amount of intensity. So in the 90s, so we had we were doing lots of this stuff where at very low light levels, the output fluence is proportional to the input fluence. So this is a linear regime of optics. But then if you start increasing this, the electrons get pulled far away from their equilibrium positions and nonlinearity start. And we had lots of work that was done in that period with several collaborators from here and outside, and many of them actually chemists, because I realized that the delocalization of electrons is the most important for producing large nonlinearity, right? So this is optical limiters unlimited. And so this is TIFR limited itself, where look at this molecule, I moved far away, but tetratolyl porphyrins, large molecule, right? And we did this experiment in collaboration with Hyderabad. Prem was a postdoc here. I think JD knows, no, JD, it was Sudipta knows him, but JD doesn't. So this is done with two molecules. I've shown that, as you increase the intensity, the response output sort of gets clamped. So there's a clamping circuit. That's good enough for me, right? And then I should refer to this path-breaking paper because of its sheer simplicity, right? So in 1990, this group from Florida, CREOL, Center for Research in Electro-Optics and Lasers, produced this paper where they said, look, it's after all increasing intensity. So the simple way to increase intensity is take a laser, focus it with a lens, and normally you would put a sample at the focus and go on increasing the laser energy. But why don't you move the sample across? There's already a varying amount of intensity here. And as you go from low intensity to high intensity, you get a dip in the transmittance or increase in absorption, then you move away. So it produces again an increase in transmission because the absorption goes down. So this is the standard Z-scan technique or Z-scan technique, depending on where you come from. And the beauty is that unlike all the measurements before, which was struggling to get absolute values of the multiphoton absorption coefficient. This gives you a direct measure. Like if you want nonlinear absorption is being directly measured, you don't need to look at a secondary signal like 2-photon fluorescence or something. You don't need calibration. You can just do it straight. And this paper, I think, has got about thousands of citations because it's so simple to use, and everybody, there's a whole array of papers saying Z-scan studies of this, of that. The industry just woke up at that time, and it's now hugely popular. But then, if you look at this structure here. So this is the focus of a Gaussian beam, as all of us know, most of us know, we don't need to belabor this point, that it is actually continuously varying. It's inhomogeneous across this, and it's only in a small region called Rayleigh range where it's reasonably constant. So you're exposing your sample. Suppose your sample has some thickness, you're exposing your sample inhomogeneously, and you get a response which is not uniform. If you want a uniform response, what people do is that they make this sample extremely thin. So they make it thinner and thinner so that essentially the same intensity falls across the entire depth of the sample. This is a big problem. And one more problem, which I'll tell you shortly, is this. Sample thickness has to be small. So if you have a small sample, femtoliters, whatever liters you have, and concentrations are femtomoles, picomoles, whatever you want, you can't do it because you have so little sample, the signal is very weak. And you're talking about change in transmission. So if you have 1% change, 0.5% change, it's very, very difficult to measure. And the sample has to be scanned across the focus. Across the focus means, many people say that signal is not coming, so let me just jack up the intensity. So they just turn up the energy of the laser or something. And then before the sample reacts, the glass cuvette has got damaged. And even if the glass cuvette survives, the sample gets damaged because biology does not really like high intensities, right? So we all know that. So the biggest problem, while this is universally popular, great, it's a 1B measurement, all that stuff, sensitivity is low because you have very little sample that you use, and applicability, you can't use it if some material gets damaged by even at the lowest high intensities, the lowest high intensity that you need for measuring your signal, then that's a no-no. Okay, so in steps Sudipta, this is 1999. He entered in 98, if I'm not wrong, right? And he was setting up his lab. So he steps in, and his office was opposite mine, right? I was in B133. He was in the present student's room of TCS. And we used to run into each other. And in fact, Sudipta has known me from IIT Kanpur days. So probably the longest that anybody has known Sudipta here. Yeah.
You got me here.
I got you here. So that you will hear in the evening, not right now. So I got him in trouble. Okay. So he steps in, and everybody is just busy using this technique, paper after paper. There's a whole industry that, many people got their PhDs and they flourished in their career, and they're still doing the same. My colleague S.V. Rao, whose student Dipanjan Banerjee sitting in the audience here, he continues to do Z-scan and produce maybe a dozen papers every year. Right? But then it took Sudipta to say that this is a no-go for most biological systems. So let me liberate the Z-scan from its limitations, right? And by liberating, liberation means, you feel free. So you should become more sensitive, and you should have wider acceptance. So that's what he did. He said, let's revisit the whole problem. The problem is that the sample experiences inhomogeneous intensity, right? As you go across. So what? So let me see what actually is the integrated intensity across this sample, and let the sample length be anything. It doesn't really matter. I'm going to take the full Gaussian propagation through this. I'm going to account for varying absorption across this entire sample, and then figure out what happens. And then he said at the end of it, look, you're getting all the information even without having to go to the focus. So why go to the focus at all? Just move it somewhere, anywhere between, well before the focus. So no damage, no nothing, safe. Any sensitivity is okay. Give me as thick a cell as possible, and I'll deal with it. And let it go through any path of this Gaussian beam evolution. The story is long, and I would give the reference, but Sudipta said, nobody revisits. Once there's some technique which is given, there's a whole industry of people who just want to use and publish. Nobody questions the basics. So he chose to question the basics and said, it's not so difficult to imagine. And with Balaji and who else was there? Parijat Sen Gupta, yes. So Parijat is here. Unfortunately not. Yeah, she will join. I'll have things to say to her too. So the transmitted photon flux on the left is related to the initial photon flux by a very simple relation. And if you ignore that zoom banner there, there's a sigma 2 there, which is a 2 photon absorption coefficient, right? So very simple. You just do output flux, input flux, and you get your result. So weak absorption, not a problem. Sensitivity has been boosted because of the technique by 2 orders of magnitude. 2 orders of magnitude sensitivity increase to get the 2 photon cross section. And he dismissed all other problems saying, don't talk about them, right? So we did this experiment in our lab with a femtosecond laser, half a terawatt femtosecond laser that we got in 97. And this is a 2 photon absorption coefficient, and a poor physicist like me only knew dyes, right? Rhodamine 6G, because we were using dye lasers in my earlier at IIT Kanpur and so on. So I knew rhodamine 6G is a very popular system, and we said, okay, let's try. So rhodamine 6G, people had said the 2 photon absorption coefficient was something like 30 Goppert-Mayer, which is the unit for the second order, the 2 photon cross section. But then as we measured, we found out it's exactly half of that. 16.2 GM. And the experiment was done with our laser. This is the 1 by NT, the transmitted inverse of the transmitted flux of photons. This is for the solvent, which was methanol, I think. And this is for the rhodamine 6G. And you have a beautiful curve here, which tells you can extract the sigma 2 from here, which is at 16.2 GM. And then this paper was written largely by Sudipta and students with a little bit of intervention from us, right? So Parijat, Balaji, Sudeep, Reggie Philip, and GRK, and Sudipta Maiti. And my first and probably only paper in JCP, which is a communication, right? So, and communications, people say, oh, communication is very hi-fi. You think really you want to go there? And look at this, 22nd February 2000, and 4th April, it's accepted, right? Imagine. Such smooth passage of a paper is unheard of these days. And I went and read this paper because triggered by this symposium. I can't believe how well it is written. Usually when I read my papers, I don't read my papers because once they are written, you should never read them. You'll feel like a worm when you read them and say, did I write this? How could I write this? It's full of mistakes. This paper I read, I couldn't change a thing, right? So it's a great tribute to the way Sudipta has functioned all his life, right? Extremely careful, very methodical, goes to the basics, figures out things, and does not let anything else distract him from doing what he wants to do. So, and I discovered that not only this paper, I have more riches, like I discovered later that I have co-authored all these papers. Of course, one of them is an abstract. Balaji was sending around. Later, Balaji comes to us and said, look, now we have done it at 806 nanometers of the TIFR. We should do it at different wavelengths. So that's where he comes in. He does tryptophan. He says tryptophan is a big molecule, it's used for fluorescence, this. So Balaji used a Raman shifter pumped by a 532 nanometer Nd:YAG laser, produced 683 nanometers, and did the 2 photon absorption of tryptophan, which is there in one of these papers. So 4 papers have been gifted to me by Sudipta and collaborate and students. So I'm eternally grateful. And by the way, I feel a little sad. This paper has been mentioned in all the significant reviews of nonlinear absorption in the literature, published in chemical reviews, lasers and photonics reviews, and various things. But because it comes from a remote part of the world, the citations are not that many. But that's no measure of the strength or the deep scientific content of this paper. And so just to go back, right? So you might discover funny parallels here. Sudeep Banerjee, who was a student of mine, IIT Kanpur, IIT Kanpur, IIT Kanpur, 5-year, right, MSc, and Reggie Philip, right, and other postdoc. There was also Riju, Vinod Kumarappan, Debu Goswami, and of course Deepak Mathur, who was, we were all working on similar themes at that time. So, and I don't know if you can see me there. You do? Yes. And I look like somebody else. Right? And I have I camouflage myself there probably. Now I'm not. Okay. From there, I watched Sudipta grow by leaps and bounds, right? And it's been a great pleasure for me and a matter of immense pride that somebody whom I may have had a little bit of cajoling or hammering to make this his home turned out to be such a brilliant scientist, right? And I had an occasion to capture a little bit of this. Sudipta came with a huge reputation, having pioneered the multiphoton spectroscopy technique along with Watt, Webb, and colleagues at Cornell, right? And his PhD advisor himself is was very famous. He's still famous, but he's no more. Robin Hochstrasser, whom I knew very well because of my connection with molecules. And so great lineage, but what he has done more than sort of, justifies the lineage and actually builds on it. So he did this serotonin work. That's a very highly cited paper. He's the first author in that science paper in 1997. And then once he came here, he exploded on the scene. Here and elsewhere in the country. He enlarged the reach of this multiphoton microscope so much and he produced some very interesting results. And more importantly, he also addressed very fundamental problems. Like, for example, Alzheimer's. Alzheimer's, why does it happen? What actually happens in the brain when somebody gets Alzheimer's? And all these things, and all this have actually resulted in him established as a leader in multiphoton imaging and this kind of work. And so much so that there's a new UK-India initiative where he's the Sarathi, Ratha Sarathi in more ways than one. He has to lead the program. So, well, I wish he had led it in TIFR, but now wherever he is, he will lead that. That's what he's promised. Excellent work, top rated. And Shankar said this a little. He had always had this, I wanted to build. Once he told me, I'll build such an instrument that looking in the beauty of it, tears will come down your eyes. Right? They'll come to your eyes. I said, what is this? He said, I'm going to build the best fluorescence correlation spectrometer in the world. And I think he did. And he did this at a cost which was remarkably low. It's not just the Mangalyaan which costs less than the Hollywood movie, but also Sudipta's instruments probably are a fraction of the cost that you will pay to all these industry wallahs. We should not say bad things because they're sponsoring it, but nevertheless, so designing drugs against toxic oligomers, etc., great work. But, we will all talk about this work over the rest of the day. But let me tell you, when I wondered why I was standing here, I'm not so out of place. Because but for an event, call it destiny, fate, whatever your liking is, Sudipta wouldn't have been what he is today. He would have actually been this, right? He went to Rochester, to the Institute of Optics, and where there's this big laser, nanosecond laser, producing ultra-large intensities, and they do a lot of fusion research. So he would have been blasting things out of place and out of sight, out of shape, out of place, out of sight, whatever you want. He would have been working on this. I'm sure he would have done stellar work even there. And stellar meaning those lasers are used to create stars on the Earth. So probably he would have created some stars with those lasers there or elsewhere. But then, and one of the people whom he was around with at that time in Rochester is Gerard Moreau, who won the Nobel Prize for CPA. That made these high-intensity lasers, femtosecond high-intensity lasers possible. And this was a sort of a reunion for them. In 2009, Sudipta still looks the same. Some of us may have changed. So Moreau and Maiti, as I captured at that time. And so he was in the neighborhood when that work was probably in one of the adjacent labs when that work was going on. And he also had courses by the famous Emil Wolf of the Born and Wolf optics fame, right? The legendary textbook on optics. But then Sudipta got a life. He said, oh, I don't want to do all this. This is just not I want to do something to do with biology or something that makes a difference to a large number of people. And so he got a life and biophotonics happened for him. And he happened for biophotonics. So I have immense pleasure and I can't describe to you how much of pride my chest is swelling with pride when I say congratulations on a great career, which was it's unfortunate that it doesn't flourish further here. That's an event that I can never reconcile with. But you will make a difference to more people when you're outside TIFR than probably when you were here. So congratulations, proud of you, and thank you for giving me a bit of your scientific career. And before I end, I just want to say one thing, just only one more minute. So after that experiment, we were all known by different names. For example, Balaji was called Balaji. Rezi Philip was called Rezi Philip. And Sudip Banerjee. And then I was called Z Ravindra Kumar. You changed my name too.
Thank you, GRK. It feels like just keep on listening to you, but yeah. Yeah, so
You can have some questions.
yes, if you have some questions.
Meeting gender.
Of course, we will. So we will do the roasting, toast and the roasting in the evening. Shankar says TIFR is not a place that roasts people, but I'm sure you have enough like pulling things, Sudipta, that you can prepare. Roast welcome.
USB. We're going to have a lot of fun with this because I actually don't have a USB connector on this one. This will need a C type to a. It'll need a C type connector to it. That's fine. Someone has a bless you. Thank you.
Problem solving, you share.
I should. I normally do, but today I read about that. So USB hai? Oh, thank you. You can take
Yeah. Meanwhile, if
just transfer it.
any questions for GRK?
One second. Let me first put it.
But that's for the evening.
That's for the evening.
Get more people into the hall. There's that.
Maybe does Sudipta have a question for GRP?
Roasting is for the
No. One second.
So was it in the same lab where you're working
Yes.
now?
Actually, I should also share. Sudipta had maybe 40 square feet of office, 30 square feet of office, probably.
And no lab.
And no lab.
Yes, back.
And the room was divided.
Yeah.
The room that is open now was divided. Prabhananda was still there. Prabhananda occupied the pride of, pride place in that room. GP was sitting in one corner. Sudipta was pushed to literally to the other corner of the room. And that's where he sat down and wrote all that. These kind of things, right? So I think, people say that space is needed. Space is certainly needed. We don't Hyderabad for a reason. But somehow,
Download it. Yeah. that-
it takes what happens in small places. And the fact is that we all run into each other all the time in here. If you are here and I am, 1 kilometer apart, like some other guy. It's important. So we were put to run into him all the time. I love to run into him, but I'm forced to run into several other people. Okay.
And welcome Vidita to talk
Thank
about
you.
psychedelics and his journey with Sudipta.
Yes. Is this supposed to be a roast Sudipta session? No. I'm just checking because I heard the word roast there. So I'm just checking that that's the case. It's certainly not going to be so. Yeah, yes, I will try to do that. Absolutely. So this was the Sudipta I met in, the one up there is the Sudipta I met in 2000 when I showed up here in March of 2000. And I was told by Veronica that there is this physicist I should meet who happens to be in the chemistry department who's interested in biology problems. And so I thought that this is an unusual human being and clearly I need to talk to this person. And then we discovered that we have a real love for a common molecule, a tryptophan-derived molecule called serotonin, and that's been one of the connecting forces for me and Sudipta. But perhaps more importantly, the bigger connecting piece has been a great friendship that has developed over the last 2.5 decades now. So my goodness, we're really aging ourselves here. But anyway, so what I want to tell you about is how conversations between me and Sudipta have resulted eventually in our migrating from not only looking at some of the interesting things that serotonin does in the brain, but actually starting to look at serotonergic psychedelics. I kind of got Sudipta into this game a little too late. This is the problem. I wish I had been talking to him about.
Mention that we are both in love of some of these molecules here.
I'm very clear. Let's be very clear. It's this molecule that we're talking about and not the others. Yeah, absolutely. So what I want to tell you about today is serotonergic psychedelics and why they are such interesting and potent molecules. They are, of course, many of them inspired by serotonin. Some of them are natural, some of them are synthesized. We work extensively with this molecule, and so Sudipta and I have done some work with you. I hope we do a lot more in the years to come, and that this is the beginnings of a longer sort of conversation that we need to be having. And I'll tell you a little bit about DOI, but I'll give you a little bit of a dive into what we are doing, and then where this dialogue becomes so interesting between neurobiologists, biologists, and chemists, and why this is a place that is ripe for interesting collaborations. So let me tell you about these molecules. They've been around forever. Psychedelics have been around as long as human beings have been finding things to grind and consume, and they for the last 10,000 years, we have a reported use of psychedelics. But from the point of view of modern parlance, it first shows up in 1898 when Arthur Heffter isolates mescaline from the peyote cactus. So that's the first real extraction where you have a molecule that we know is a potent psychedelic coming out of the peyote cactus. And then, but the big sort of landmark event is when you have your first major synthetic psychedelic show up. It's the one that everybody thinks about, which is lysergic acid diethylamide, LSD. And that happens in 1938 when Albert Hofmann is attempting to synthesize a fungal-derived antibiotic. This is the period of time when this is post-penicillin. So this is that window in which everyone thinks that they're going to pull out some really interesting molecules from fungi. He pulls out a really interesting molecule, but one that is not an antibiotic. So he shelves it. It stays on his shelf for several years until some point he decides he's going to self-administer a really low dose and see what it does. He self-administers a fairly high dose of LSD and ends up with a major psychedelic experience. And that opens the floodgates to understanding that we actually have chemical moieties that can shift states of consciousness. This is a non-trivial matter because consciousness remains the holy grail. If you have a tool that allows you to directly go in and shift states of consciousness, you have ways of studying what consciousness even is at all. Okay, you do this in animal models, you can do this in monkeys, rats, humans, etc. So this then opens up the window of time. This is actually pre the real work on serotonin. So LSD precedes the discovery in a major way of serotonin as a neurotransmitter. So it comes before that. And obviously, the structural similarities of these molecules are instantaneously apparent. And that opens up the window to asking the question of the neuropsychopharmacological effects of serotonin. Why is serotonin such an interesting neurotransmitter for behavior? So it's literally preceded by the synthetic discovery and then the opening of the interest in LSD. People work on it for quite a bit of time, but this is a period of the hippie culture and it eventually ends up getting banned. There are very poetic statements made about the fact that two major mushrooms showed up on the planet. One, the mushroom cloud, one, the mushroom that came from, derived from mushroom-related molecules. The one we chose to ban are the mushroom-related molecules. We did nothing to the mushroom cloud. So it's a very interesting sort of anthropological discussion or a sociological discussion in what we choose to ban versus what we don't, in terms of harm to humanity. So these molecules then, 1970, everything goes into a Controlled Substance Act. They're all Schedule 1 molecules. You can't import them, which is why Sudipta very carefully right now said, we are only interested in serotonin. We may also be working with these molecules, but yeah, they're all substances of abuse. They're not actually addictive, but strangely, they fall into this category because of this history. Post that, there is a reopening of an interest in these molecules that's happened in the last decade. And that happened because of a study that was done with patients who had severe depression or end-of-life anxiety. And this was done with terminal diagnosis, usually with last-stage metastasized cancer. And with that, this was allowed as a potential therapy to see if it helped with end-of-life anxiety. And they found really breakthrough effects, which is what resulted in FDA potentially allowing the opening of clinical trials with molecules like psilocybin, LSD, DMT, MDMA, that entire battery of molecules. So that's where it started with mescaline. where the structure of LSD bound to the 5-HT2B receptor, to the 5-HT2A receptor, both through cryo-EM and originally through X-ray, is now known. We have an understanding of these molecules and how they bind, but we still have a very poor understanding of how they mediate their long-term effects. We don't understand the underlying circuits that produce the behavioral states. That's one of the big interests for my lab. And there's a real interest in using psychedelic-inspired drugs that might now be able to parcellate the behavioral effects so that you get the effects on mood. You don't get the effects of the hallucination. You get the effects perhaps on anxiety, but you don't perhaps see it on others. So if you understand the circuits, you can design far better and more clearly potent molecules which are targeted to the therapy that you want them to work for. Just to give you a sense that if you were to do a PubMed search for something like LSD, this is what your PubMed search would look like. There is a window in which everything just slows down, and then something has happened in the last 10 years. DMT is dimethyltryptamine, commonly found in plants, tons of it in your own body. It's actually a Schedule 1 drug, and you don't realize it that when you are crossing borders with a ton of DMT in your own body. It's just that you don't think of it as a Schedule 1 molecule crossing borders. It's there in your body. It's just that we don't send enough of it to the nervous system. Most of it gets broken down by monoamine oxidases in your gut. So you don't end up with enough DMT in the brain. The way ayahuasca tea works is that it's a combination of providing you lots of exogenous DMT, at the same time providing you molecules like harmine and harmaline that block the monoamine oxidases. So you end up with now a big hit of DMT entering the nervous system, and that's how you end up with the psychedelic effects of ayahuasca tea. Here is psilocybin, which is the active ingredient of magic mushrooms. All right. So why are these molecules in the last 10 years causing such a re-interest in what they do, their properties? You have all kinds of people interested in these molecules now. It's because we are sitting on a burgeoning healthcare epidemic as far as mental health disorders are concerned. Generalized anxiety disorder and depression are now emerging as some of the largest sources of global morbidity. And because of the disease burden associated with it and the fact that we haven't actually come up with anything new to treat these disorders in decades and decades, we only tweaked whatever was there. So we got it better and better, but we tweaked what was originally there. We haven't really come up with anything really new or path-breaking. Perhaps ketamine is the one example that one can think of that showed up on the scene, but other than that, nothing really new has shown up. And that being the case, there's a super big interest in psychedelic-inspired molecules. And so that's why there's refocus on psychedelics. Okay, so what do we do and how did we get started talking to, Sudipta? We've been talking about serotonin forever. It's not like we haven't chatted about serotonin. There hasn't been a time when we have not been discussing serotonin. But psychedelic showed up on the scenario relatively more recently. I've been working with this particular psychedelic DOI for a very long time now. I actually started in graduate school. I found it fascinating. I've continued to work on it forever. So DOI does many things. It produces hallucinations. It drives modulation of anxiety-like behavior. It's a direct modulator of mitochondrial biogenesis. It's a modulator of neuronal structure as well as function. And here's where it is ripe for conversations with chemists because it appears to be regulating lipids directly. So I'm not going to tell you about any of this. I'm going to tell you more about this. And some of this work is all of this work is in collaboration. So this is where it becomes interesting because it's ripe for conversations with chemistry colleagues. Sudipta and I have a paper that came out recently. I have done pretty much nothing other than said, please look at psychedelics, please look at psychedelics. That's my contribution to the paper, pretty much. Ankuna and I are sitting on a story, which is, again, all from Ankuna's lab, but we've become like the suppliers, which is a little scary. But anyway, and getting all of our colleagues interested in these molecules. And then there's a major collaboration with Siddhesh Kamath at IISER Pune. He's also a chemist by training. So in a sense, I can put this into my cross-talk with chemistry. He's also just got the Infosys Prize yesterday. So I'll tell you a little bit about the work we've done with Siddhesh. I'll touch upon what Sudipta's lab has found, but he's far better placed to talk about it. And Ankuna and I guess Ankuna will talk about some of that work. So there's some work that's happening in there that is exciting as well. Okay. So what do these molecules do? And so serotonin clearly doesn't produce hallucination. So serotonin is the natural ligand for these serotonin receptors. It doesn't produce hallucinations. It also binds these receptors. There are 14 receptors. For the moment, we're going to take a very serotonin 2A receptor-centric universe view, which is there are 14 of them. This receptor seems to be the major one for several of the psychedelic-like effects, the 5-HT2A receptor. It's a receptor targeted naturally by the endogenous ligand serotonin, but also by psychedelics like DOI, LSD, psilocybin, etc., and by plenty of drugs that are non-psychedelic but also target the same receptor. Opening up the million-dollar question, what is the signature that produces the psychedelic response? If the same place, and it's an orthosteric binding site, so it's binding often to the same place that serotonin is binding to, what is it doing that you end up with a totally different, presumably signaling signature? It has to be a signaling signature to drive such a long-term different behavioral response. Behavioral responses are diametrically different. Minor changes. Glyceride is actually derived from LSD, but it's non-hallucinogenic. And there are plenty of such examples of things that are sitting right next to each other, fairly similar structurally. 4-methoxy-DMT, 5-methoxy-DMT, 6-methoxy-DMT, utterly different behavioral effects, but very poor understanding of what happens to drive such different behavioral effects. And the very earliest stages are, of course, receptor binding, and then things happening largely with phospholipid hydrolysis. That's the pathway that this entire cascade is connected to. And phospholipid hydrolysis is the first early event that will then drive a series of enzymatic changes downstream to give you presumably the signaling kind of signature associated with these molecules. So where Sudipta's work is super powerful is it tells you that the psychedelic is doing stuff without having to worry about the receptor. It's doing stuff to the membrane. And that then opens up an entire question of whether you can have receptor agnostic effects where you could be influencing a whole bunch of things without having to necessarily worry about a protein ligand interaction. It could also directly impact that interaction, because one of the things that has been consistently shown that for things like LSD, the on and off rates here are slow, and signaling with psychedelics seems to persist for a lot longer than with the endogenous ligand and also with ligands like glyceride or non-psychedelic ligands. So something special happens when you have the psychedelics in play. And that's also what seems to be happening when we look at Ankana's data, where she's looking at the earliest signatures of PIP2 hydrolysis using the probes that she has made, allowing us to pick up signatures which are otherwise difficult to pick up biologically. What we are picking up is stuff down here, happens across minutes, happens across hours, etc. The time scale for the behavioral effects is within 15 to actually 5 minutes, not even 15 minutes. You get very, very rapid effects with these drugs. But this tells you that something is happening here at the earliest stages that might be critical to pick up. So what we had done before we started talking to Siddesh is we had done what most of the biologists were doing. We're all rather protein-centric in that we want to find an enzyme that is phosphorylated, some phosphorylation signature, some change. And we already found, yes, signature changes which indicate that the nature of response evoked by DOI, be it measuring the phospholipids itself or the activity of the phospholipid, so these are the phospholipases, the accumulation of diacylglycerol, etc., you could clearly see that DOI compared to glyceride was giving you a much stronger and persistent response. It still didn't explain why you didn't get anything with glyceride. You should have then just seen it across a dose range where glyceride should have given you effects at a dose range perhaps different from what you get. You should have at some point seen some overlap. Don't see it. So that opens up the question that maybe we're looking at the wrong thing for signaling signatures. What if we switch our lens and instead look at the lipidome? Forget about the proteome, forget about phosphorylation changes to proteins, just let's look at all lipids, agnostic to the lipid without having a particular view in the beginning. So here's where, with Siddesh, we started this collaboration led by Antara and Toshali in the lab and with a team of wonderful, talented students at Siddesh's end. So this is a totally joint project. So what first they set up to do was we said, okay, we're going to treat neurons in culture, and we'll dump DOI on it, which is the psychedelic. We'll dump glyceride, which is a non-psychedelic, at doses which are reasonable and expected to be the range in which you would be working. 1 hour later, we're just going to mush up the cells, freeze them and send them to Pune. And we're going to take the medium and send that also to Pune because we are asking what's happening to the lipidome, both in the cells and in what is secreted. And when you do that, you agnostic and blinded Siddhesh students ran all the mass spec and actually looked at what are the potential signatures. And already it should be instantaneously obvious to you that if you look at a heat map of DOI over DMSO is just the vehicle. The drug is made in DMSO, so the vehicle would be DMSO. If you look at the signatures of this heat map versus this heat map, yes, there are overlaps as expected, but there are clear signatures that are different for this ligand compared to this ligand. And that's true whether you are in vitro or actually in an animal. So you can inject the animal, flash freeze the brain and send the whole brain to Pune, and then they run the mass spec. And when they do that, they start seeing certain commonalities. And what's so striking is there's a molecule here that shows up that's up very high associated with DOI, but not regulated by glyceride. And that becomes interesting to us because we are looking for signatures that distinguish these two molecules and that have utterly different behavioral effects. So the molecule is 2-arachidonyl glycerol. Okay, that's the moiety, and that shows up in culture, in the cells, shows up in the medium, so it's clearly being secreted by these neurons, and it's showing up in frozen brain. So we see this in the lipidome. So then that's interesting, and so here's just showing you a little bit more of that data more closely. This is the molecule 2-arachidonyl glycerol. So if you now look at a volcano plot, here is 2-acyl glycerol showing up as a majorly altered regulation associated with the psychedelic, not seen with the non-psychedelics. And that is true here. If you quantify it, we are looking at 2-AG. Arachidonic acid also gets regulated, but focus on the 2-AG. Here's the upregulation with DOI. Nothing happens with glyceride. This was super interesting to us because now you have a early lipid signature that's utterly different. Now, let me tell you what 2-arachidonyl glycerol is, which is when it starts getting super interesting. Tetrahydrocannabinol, familiar to everybody, the active ingredient of marijuana, right? You know that marijuana can also produce hallucinations. All these molecules were not made simply to stimulate your brain. There are also equivalent endogenous ligands you have in your own body. So the cannabinoid receptors that tetrahydrocannabinol binds to has its own endogenous endocannabinoids that can bind to these receptors and stimulate them. The most potent endocannabinoid we have is 2-arachidonyl glycerol. Okay, so that is a direct ligand for the cannabinoid receptor. And you're driving up large levels of endocannabinoid signaling in neurons and in the brain associated with a psychedelic, but not with a structurally similar molecule that is a non-psychedelic. So that got us really excited. It's also, maybe it's just DOI, maybe this is just unique to DOI. We haven't tried the other drugs. So the natural thing was to go in with 2 other very potent psychedelics, TCB2 and NBOM. These 2 molecules also give you the similar signature. You get this big increase in 2-arachidonyl glycerol, and you're not seeing it with non-psychedelics. So now we got excited, saying maybe this thing is doing something, and that's interesting for us to look at. So now we want to ask, is this a lipid-related event which has nothing to do with the receptor and is just somehow that the drug is capable of influencing this biosynthesis of this molecule without necessarily going through 5-HT2A receptor signaling? So here is using a drug that blocks the 5-HT2A receptor, MDL. So what we do in this experiment is, so we have rats and lots of rats. We block the 5-HT2A receptor using MDL 100907, which is a selective antagonist of the 2A receptor. We wait 60 minutes and then we come in with DOI, and then we are looking at behavior evoked by these drugs. And of course, we are flash freezing the brain and sending it to Pune. So we are doing both these experiments. So we run the behavior, and what's obvious is here's the head twitch response evoked by DOI. It's a very good proxy for a hallucinatory response. You'll ask me, why is a head twitch a hallucination? A head twitch is essentially what you would do if you took a dog and poured water on its head. It would do this to shake off the water. It's a very canonical stereotype response. Turns out every psychedelic just produces it. the more potent the psychedelic in the human, the more potent it is at producing head twitch responses in rodents. So it's become a very powerful, none of the non-psychedelics produce it, serotonin doesn't do it. So it appears to be one of the motor behavioral signatures associated with psychedelics. So it's used as a proxy, because we of course can't ask a rat, what are you experiencing while you are on the psychedelic? Though, believe me, all of us who do the experiments will tell you they must be going through something, because it's very obvious behaviorally that they look quite different. I'll go quicker. Okay, so the bottom line, here's DOI. If you block the 5-HT2A receptor, you block this effect. That's also true for the levels of 2-arachidonyl glycerol. You attenuate the effect. You might not completely block it, but it's coming down quite substantially, telling you that there's a strong receptor component that is involved. And if you knock out the receptor, so if you make a mouse that doesn't have the 5-HT2A receptor at all, you won't get the head twitch response at all, because there's no receptor to work on. And you'll also not get this increase in 2-arachidonyl glycerol. So this is a receptor ligand mediated downstream event. It turns out, I'll not walk you through that data, but the bottom line, so this is work done by BG along with Siddesh, where we were able to show that this happens because of an increase in enzymatic activity of DAG lipase. You end up, for whatever reason, having a big boost in DAG lipase activity. DAG is what breaks down to give you 2AG, and that's how you end up accumulating 2AG quite substantially. If you block this particular enzyme, you attenuate greatly the head twitch response, telling you that this signaling cascade is important for that particular behavior. Yeah, it's responsible and involved in this behavior, but it is not involved in the antidepressant-like response. Not showing you that data, but it's splitting it. So it's telling you it's different circuits, different eventual targets for both of these particular behaviors. Is this happening in the human? This was a natural next question. What if we take human neurons, grow them in a dish, dump DOI or psilocybin on it? Would you see it in human neurons? Right now from healthy volunteers, not from individuals with life histories that are complex, which is the next step that we are going to do. Here's work done with Biju at Nimhans, Salil and Lekhanch. Without Lekhanch, we would not have had any psilocybin to actually try in experiments, but here is the active ingredient of magic mushrooms. What should be instantaneously obvious to you is it happens in human neurons as well. So you see it in a rat neuron, you see it in a mouse neuron, and you also see it in human neurons. So this is a signature that is holding consistent across 3 different species. What we'd love to do, and what would be so much fun to do, and we will figure out how to do this best, but perhaps in a team science sort of approach, is to be able to ask this now with human neurons derived from patients with all kinds of potential life histories, with single nucleotide polymorphism deficits in specific components of the 5-HT receptor, etc. I am going to go really fast, I promise. I just have 2 more slides, I promise. So yeah, so this is just, in the meantime, Sudipta's lab has been tinkering with serotonin as they have been for multiple decades, and they discover that serotonin is a direct regulator of lipids. So you don't need to worry about having a receptor on board. You can do all kinds of fun things with serotonin straight to the lipids themselves. So that's kind of mind-blowing. And right around that time comes this paper that came out from David Olson's lab that says, you know, all the psychedelics are lipophilic. They just make it straight into the cell. Maybe the lipophilicity is associated with their strong hallucinogenic properties. Again, a debate, again, a discussion, but a very thought-provoking one. And so Sudipta and I are chatting and we are saying, listen, this is, now next thing should be to look at serotonergic psychedelics, clearly, right? So here's this wonderful work from Deb Shankar that just came out, where looking at a psychedelic drug, far more potent than serotonin, you have this potent effect on membrane fluidity. I'm not going to get into the science because Sudipta will literally have to explain it to me and I will do a terrible job of translating it. So I will give you the graphical abstract version, which is to say that you have an effect that is potentially so strong and so interesting, and if that becomes signature that you see with psychedelics versus non-psychedelics, you have a non-receptor mediated event that's allowing you to play around with potentially broad signaling independent of proteins and potentially directly through recruiting membranes. Yeah, so why are these molecules interesting and why should they be exciting to the chemists, since this is also a continuation of the chemistry annual talks? Because of their lipophilicity, because of their effects on membranes, their ability to directly influence protein membrane related interactions, their influence on broad endocytosis, phospholipid dynamics, and because endocannabinoid signaling is a tip of an iceberg to major behavioral effects. So I will wrap up by saying that this is a space that is ripe for more conversation, dialogue. We should be talking, Ravi, because there's a lot of interesting stuff here, and clearly there's room for lots of interesting things to be done. That's Sudipta, who's been also an incredible friend of not just DCS, but also DBS. He's been an adjunct to the DBS for as long as I can remember. So we pretty much think of him as an additional member of DPS. That's always been the way it is. And so he's not going to be missed because we're going to continue bugging him. That's just the bottom line. That's just the way it is. And yeah, here he is with several members of the DBS team, celebrating all his wonderful achievements. Sorry, I took a little longer, but I had to do justice to the work that we have started. We have 4 papers together as well. This seems to be a thing, but I hope that this is actually the beginning of many. And I think psychedelic related stuff, there's a lot of exciting promise there. So yes, thank you.
Thank you.
Yeah. Yeah, Ravi.
I can just. Yeah, I think this GPCR work is always fascinating actually. So are there DOA versus some of the non-psychedelics? Do you see any differences in terms of the cognate partnerships, basically, like the GPCR versus the cognate partners? I mean, I agree that the lipids can get mediated, but ultimately, does it change the associations?
People like to believe that, and that was a working hypothesis for a long time, that the heterocomplex is formed with when you had a psychedelic on board with the 2A receptor, were very different when it was a psychedelic versus the endogenous ligand or a non-psychedelic. The problem with that is it's all been done in kidney cells, where overexpression of those receptors has been driven, and because that's also been done to catch the Fred sort of stuff. Very powerful data there. But the minute you move to the brain, you have all these things coming up as just endogenously heterocomplex half the time without any drug on board. So this becomes very hard to interpret in the context of a behavior. But in more sort of artificial systems, absolutely. You will see them coupling, you will see this bias, but it doesn't seem to hold true the minute you move towards, if that's the case, then you should be shifting the bias towards a heterocomplex. And the heterocomplex is seem to endogenously be present already in the brain to a differential degree and extent. It's a good question, one that people are getting stuck with fully pursuing well, because the demand is show us that that's the driver of the behavior.
Great.
So, yeah. One quick question. So I saw that even with MDL and even with your receptor knockouts, it didn't quite get to the control. And that's exactly that 10-20% left is what I think there is an interesting stuff there. What's your comment on that?
Yeah, it's back to, I mean, one would imagine with a 2A knockout, you should be totally wiped out. Like there should be nothing left because there's no receptor left. I mean, those of us who want to take a quasi-biased approach towards other receptors will say there's a 2C still in there. There are 1A receptors still in there. At high enough concentrations, you hit those receptors. I wouldn't preclude the possibility that there is a lipid-related component, which, yeah, absolutely. We don't wipe it out. We get down quite substantially, but not completely to zero.
Thank you.
Yeah, let's thank Avita once again. And next talk is by Koti.
Full screen. I can put HD on, so then I can get full screen better. It's better. Sure. That's going to be. No, I can connect to HDMI. Then it's better, no? Okay, because that's going to be there. No? Ready? Yeah. Okay. Good morning. So celebrating Sudipta. So I have been associated with Sudipta for a long time. I think 97 we joined as PhD students, young students, and he joined in I think early 1998. So more or less we finished our coursework and then just walking around looking for the labs. And then suddenly new faculty actually comes into the department and then sits at the same computer where actually you're sitting. You suddenly check that you're checking your mail and then suddenly new person comes and checks at the same terminal. In the BC30, it used to, yeah, it used to happen. And then of course we have had many interesting interactions. So we used to go to even cafeteria in the gym, right? Current gym, where we used to have in the evening ice cream, cup of tea, etc. And of course, his classrooms used to be very popular. Very little chemistry students because very few students we used to have. But most of the time you always find that many physics students and then biology students, of course, very popular among physics and biology. Of course, he got good students from physics as well, like Kanchan, etc. Okay, so but then of course I moved out of TIFR after PhD and then trying to come back to India. And then I'm also interested in building instruments. So then looking at places where, where actually, because the kind of stuff which I wanted to do is not there in India, and also it requires pretty much instrument building. So Sudipta has been inspirational because his lab has always been building new instruments and etc. So then I thought that, okay, TIFR is the place where to go, at least come back and then say that do something. And of course, we have been talking about various things along the way. And so he has been part of TMC of my students, always giving good feedback and etc. And today I'm going to talk about two collaborations, which really are memorable and it's a time to cherish and relish. Is that one is on this xenonucleus and the other one is phase separation. So Sudipta has been, of course, very well known in my multiphoton microscopy, cells, and etc. And of course, he built a huge program around peptide synthesis. So he was the one started peptide synthesis in actually chemistry. And then, of course, he has a beautiful program around peptides for the aggregation, etc. But I don't think he ever really worked with completely folded proteins, maybe GFP in his early life. Then, of course, Anirban in the lab was looking at, okay, how actually we can use this to, for the proteins. So then suddenly we strike a collaboration. So Anirban was actually interested in trying to see that how peptides can be used with proteins to do something very interesting. Of course, protein folding problem has been there for a long time, many decades. So much has been really going on. But then Sudipta and Anirban really thought that, okay, so nucleation of protein folding has been long time. But this is actually intramolecular, always protein folding when you say nuclear. But then Sudipta and Anirban really thought that how actually we can use, because these peptides have a beautiful shape. You can really get, if you tune the sequence, you can have either helical or beta sheets and etc. A lot of knowledge from the aggregation studies. So then they were thinking that, can we use that as a nucleus for protein folding? And then obvious choice is that you need to really look for good folded proteins. Lucky that I am around, so I feel that I'm honored basically in that collaboration. And then suddenly we strike that let's do something together. That's where actually we began to do that. And then initially we got really surprised that these molecules are really affecting the folding, rates of these molecules. So that itself is basically the genesis of this project. And of course, these are the kind of peptides we worked, and this is our contribution, and this is from their lab contribution. And then suddenly, it became obvious that we need to really quantify this. Is this effect qualitatively, is it really occurring or not? So this is where we have done stop flow fluorescence-based measurements. Here I would like to acknowledge even former member of DCS, Professor G. Krishnamurthy. Thanks to him, actually, he had this stop flow setup before he left, and then I started using after that. So this is a kind of legacy again. Sudipta really continued the legacy of predecessors, Professor Periasamy, GK, in continuing that facility, which not only helped members within the chemistry department, but many people, outside the institute within India. People have used these setups. Even now, people really come. Of course, now there are plenty of setups around the many institutes, but still actually people really come here. So that's a kind of continuing legacy. So anyway, so here, so we observed that just by adding the peptide to this protein, so basically the folding is really accelerated to some extent. Shows that it's very interesting phenomena, but can we do really more? How do we know that the protein is really interacting with the peptide? Is it really part of the thing, or something else is going on? So suddenly, Sudipta, right? He's infectious. He's infectious. Suddenly just calling people and then see that, okay, let's do something, So Ranbir, okay, can we do this in NMR? We have this protein, we have this peptide, we have done these experiments, Kote has done these experiments. Let's see that, can you do this in NMR? That's actually how he is, right? So then suddenly Ranbir says that, yes, let's do things. And then suddenly Shachi comes in. She's also going to talk about in the afternoon. Can we really see it computational? Is it experiments we see that? Can we really come up with a modeling, And then Kalyaneshwar at TIFR Hyderabad. Okay, so who is expert in making D-type peptides in itself? So he really looped in many people. And then this is a true pan-TIFR collaboration I can really think of to date, where many institutes, many members, many of colleagues across the TIFR system is involved in that. And of course, very interesting thing, but finally, it's down to the science, right? So we have an unfolded protein. You add a peptide, which is acting as nucleus. Okay, this is Sudipta's invention, that word xenonucleus. Okay, I think she's going to talk about in the afternoon. Xeno is not xeno, maybe it's something else. Okay, so then the question is that Sudipta's interpretation was, okay, so the folding is accelerated. But of course, this is going to be part of the protein. But it has its original copy, right? So it should really kick back. And, so in the end, maybe on long run, this xenonucleus is not really part, it should be really kicked out. And because even the unfolding rate is accelerated. Okay, so then how to actually really test that? Can we really look at single molecule level? So this is where actually, again, coming back to our lab, where we have this beautiful single molecule setup. Again, inspiration coming from Sudipta's instrumentation, like, yes, we can really build these instruments. And then I came back and then build this single molecule pulling setup, AFM based. And of course, by far, of course, we got beautiful experiments, but by far, I would say these are the most difficult AFM based experiments which we have done, in our lab compared to other experiments, where we could really show that. So if you have a protein alone versus protein along with the xenonucleus, so xenonucleus actually weakens the overall state of the protein. So the protein with the xenonucleus in the end, is not really stable because it has its original appendage. So they're going to compete with each other. So in the end, it's going to get back its original one. So in the sense, in the resulting thing is that it should have much lesser mechanical stability compared to the original protein. So we could really show that at the single molecule level. And then, so unfolded protein, you can have xenonucleus, which can be part of this, but then in the end, it's going to kick back and then it can be unfolded. So we have done that. And then finally, we really proved that unfolding rate also can really go up using single molecule experiments. So the second memorable collaboration is much more recent. The student in the lab, Simran Arora, okay, she has been working with proteins, in the lab, but then suddenly you see that the field of phase separation is actually really blown up, right? So anyone who is working with proteins which doesn't have a structure, suddenly they say that, okay, phase separation has to do something with this. But no one really ever thought about the phase separation of completely folded proteins. And then we know that the proteins which we are working in the lab, like sumo and ubiquitin, they have been heavily involved in phase separation in the cellular studies. So many people have really shown that. So then we thought that, okay, we should really try to understand that if these molecules do have anything to do with phase separation or not. But however, these experiments really involve not just pure biochemistry experiments, but heavy microscopy, because you have to really look at the droplets at the end and then try to understand whether proteins are the part of the droplets. If they are, how, why, when, and what. So I'm not really a microscopy person. But then Simran struck collaboration with Sudipta's lab again. So thanks to Dev Shankar and Sudipta. Okay, so briefly, what we have done is that folded proteins are really happy in solution. But however, we want to really mimic this crowding conditions which present in the cells using in vitro by large polymer molecules like polyethylene glycol. Just if you add a little bit of amount, then basically the solution becomes scattered. And then if you take a droplet of this, and then you see that tiny droplet, the scattering is actually due to that. So this is a kind of interesting phase separation. Of course, so a lot of fluorescence spectroscopy is involved. So you can actually label these molecules with fluorophores and then track that whether these droplets which you see because of the scattering, do they have really protein or not? So clearly the labeled protein is in the droplets. So showing that, so this simply mimicking the cellular conditions using PEG or dextran, etc. You can actually get these droplets. So again, so you can actually make these droplets. So again, thanks to common confocal microscopy lab, again, legacy of Sudipta. Sudipta basically thought that we should have a common facility where we can really, people can come and use. So not only I benefited, my colleagues Ankana, Malay, who have been the regular users, among many others. So here what I'm showing is that, so under the confocal microscopy, you look at just one droplet, and then the green is coming from the labeled protein. And then you can actually photo bleach at the center of the droplet and then see that if there is a recovery because of the molecules which are diffusing from the boundary, then you can claim that this is basically the environment within the droplet is actually liquid-like because the molecules are able to move. These are not rigid aggregate structures. You can actually get even the kinetics and etc. So clearly showing that this is called fluorescence recovery after photo bleaching. So one of the ways to convince anyone that the droplets have liquid-like nature from the protein point of view. Of course, these molecules, these droplets, the liquid nature goes away with time. Over hours, if you see that, they even become non-spherical because of the aggregation within the droplet. So again, how do you actually probe these proteins and then show that these polymers are not really, they are acting as what are called crowders, but they don't really specifically interact with the molecules in this entire driving process. Is that here beautiful, again, confocal microscopy, we have shown, basically this is the same slide. So protein is labeled with Alexa, shown in red color here, and then the polyethylene glycol is labeled with green, shown here. So clearly you see that exactly they're complementary. The wherever the protein is there, PEG is not there. Wherever PEG is there, protein is not there. Clearly these are exclusive, meaning that the PEG is really acting as a crowder, making this protein somehow collide with each other, and then suddenly these intermolecular interactions drive this phase separation. So of course, we went into detail to try to understand in terms of the molecular interactions. So are they like charge interactions? Are they driven by hydrophobic? So you can have beautiful tests based on simple small organic molecules versus salt change. And then we showed them basically the driving force is basically electrostatic because the salt has actually huge effect. And again, we have done a lot of fluorescence-based assays on the aggregation part using THT and comparing even the time scales. So the process of droplet formation versus the further changes, are they delayed or are they occurring simultaneously? If they're simultaneously, how close in time? Clearly they're not simultaneously because there is a huge time difference between the formation of the droplets versus the further changes in the molecule because of the aggregation. And of course, these droplets, the molecules in the droplets finally becoming aggregates. Okay. And of course, obvious question you would ask if it is an aggregate, is a beta aggregate. Again, expert, so Sudipta's lab. So we could really see that Dev Shankar has, this is again one of the most difficult experiment because droplets are very tiny, very small amount, and then the content of aggregates are also not really huge. And we can't really have large amounts of protein. So Dev Shankar and Sudipta have this beautiful setup where it's a specialized Raman setup where you could really have small volumes and then finally show that basically the aggregates have a tiny amount of beta nature. So this is a beautiful evidence from that. Of course, they become large aggregates. You could really see under temp, etc. So, of course, further we looked at tryptophan-based fluorescence, again, legacy of fluorescence, TCS/PC lab, etc. And then finally, we came up with this mechanism. Basically, the proteins when they are in the outside the droplet, they have certain properties. But the moment they go into the droplet and they undergo further changes, and then you could actually track these things. The final mechanism we put together in this paper, where Dev Shankar and Sudipta are part of this, is that if you have a protein, you mimic the conditions, intracellular conditions, crowding conditions by adding simple polymers, and then you begin to see the droplets, either under microscopy, test tube assays like turbidity, or FRAP assays to show that liquid nature. But if you wait longer time, you can actually use tryptophan fluorescence to see any conformational changes which are amenable to simple microscopy and turbidity assay. And then you can again come back, microscopy, SS, and FRAP to show that the liquid nature is really gone, and then now molecules are actually becoming aggregates. And once they become really large aggregates, there is no comeback, and then so they are not reversible at all. So, of course, now we have continued these experiments in much more elaborate way, where we have done even pH dependence, and then we find out that this is very, very important that you have the right pH, because if you don't have the right pH, then you don't really see the droplet formation for these folded proteins. And then even more interesting is that in the cellular context is that you make these polymeric versions of sumo molecules, which are physiologically relevant because some of the molecules get polysumoylated as part of their life in the cell. And then we have shown that whether you have just a monomer versus dimer, there's a huge difference, huge difference. If you have a dimer, very little concentration is good enough to form droplets, and this has huge physiological effects. Of course, the story is only a beginning. And then people are now, this is again one of the landmark study in addition to the xenonuclease thing, because now people are beginning to look at folded proteins themselves, which are not readily form droplets or aggregates. But now we have shown that these physiologically important post-translational modifier proteins themselves can actually drive phase separation. But whenever people see these tethered molecules which undergo phase separation, it's not really known how much that phase separation is coming due to the protein or due to the tag, or is it the combination effect? So I think our experiments on purely based on the tags have something to really add to this. And then currently we are trying to understand, because we have beautiful homology of molecules which look together completely different chemically because the sequences are different. Is there any underlying grammar? Because one molecule forms, but the other don't, things like that. So story is really bright. And of course, Sudipta will update you with the proceedings. Of course, I said Sudipta is infectious, right? So I joined back in 2008. And then, of course, I was just setting up my lab. And then by the time, of course, Sudipta has really set up his labs, and then he's conversating, with people in the fluorescence community. I think that's the workshop. That is the year he had FCS build workshop. And then just subsequently, he had this beautiful conference, 2009. Of course, then later, 2016. These are the conferences at TIFR I'm talking about. Otherwise, he has these conferences, annual conferences. So I've been honored to associate with these two conferences to Sudipta, to work very closely, to see that his leadership skills. So he's very good at taking very fast decisions. He doesn't really mull. He says that, okay, we want to do, let's do this. If you want to do, how to do. So quickly he'll get on to the action, I would say, action mode. So for that, I'd like to thank you, Sudipta, for being a wonderful colleague and for cherishable collaborations, definitely, and for inspiring us to do good science. And then hopefully we'll take this legacy, which started by Professor Peryasamy, G. Krishnamurthy, and then you to further, next generation. Thank you.
And yeah, Devanjan, question.
Exciting part. I have 3 questions, but to the same topic. So, what is going on in the boundary when you are seeing phase separation between PEG and the protein? Do you see when some of the images I'm seeing that they are actually bigger than the optical resolution? So, do you see size difference in the domains that you see in the two different fluorescence imaging that you're doing? That is question 1. Second is, have you thought of doing something like AFMIR? So to look at the boundaries separately for a different kind of arrangement.
Yeah.
And third question is, I'm not from the field. So how much is the PEG length this thing would depend on?
Depend on. Okay, maybe I'll go in the reverse order. So the PEG length difference, the size dependence is there. So right now, most of the data which I have shown are PEG 20 kD. But if you use the smaller ones, of course, phase separation really occurs, but you need a larger amount of PEG. But if PEG size is larger, so then you need smaller amounts. Okay, so in all cases it forms, it's only concentration of the thing. Second thing is the boundary. Okay, so in all the cases, compared to, let's say, if you want to compare the size of the droplets with intrinsically disordered proteins, typically there you get much larger droplets. Even like we began to work with synuclein with Torsha in the lab. So you see larger droplets of few microns, sometimes even 5 or even 10, you're not surprised, and very stable liquid-like. But with the folded protein, so we barely saw any droplets beyond 2 micron, and almost average size is about a micron. Okay, there might be many much smaller droplets, which we can't really see resolve, but the droplets we see are about a micron. But coming back to the boundary, so definitely it should have something, because the lifetime of the droplet from the liquid nature to the complete aggregation, very fast. It's a matter of minutes to hours. Okay, we know that this aggregation, is it boundary dependent? We don't know. Where exactly it nucleates within the droplets? Again, we don't know. How the molecules in the bulk might be recruited? Again, we don't know. So this is where we just began to do experiments with synuclein. And then we are actually mixing droplets of synuclein versus droplets of sumo. So then you can actually mix these 2 droplets. Now you can have a scenario where, one engulfing other. So you can have actually boundary differences. So we don't know whether they mix homogeneously or from the periphery to the center. So these are very interesting questions. And the third one is, have we looked at AFM? Yeah, we haven't, but that would be interesting to see. Yes, we haven't really looked at it, but that would be interesting. Thank you. Interesting question. Sudipta. Usual, lifting his hand and then always says that, okay, I have a quick question.
No, I mean, these are very interesting and pertinent questions. And I don't think that the biology or even the chemist community is doing a great job in solving these. Kind of people that we need to talk to, perhaps people like Shankar, who are sitting right here. I think we need to talk to these people and to find out exactly what's going on, because every theory that somebody gives and things work out, there's a 1% exception. I don't like that. I mean, how can you have a 1% exception? Oh, by the way, this folded protein also does it. I don't know why. I mean, come on, there must be something deeper than that, than what explains the 99%. So I think we're missing the thing somewhere, and we need to talk to the physicists a lot more than we have been doing.
Yeah, so definitely, I completely agree. Usual suggestion. You see that whenever there is a talk, Sudipta pointer gives the pointer. I think, yeah, I should really talk with physicists as well as biologists. Thank you.
Thank you. Let me ask you one question. So, yeah, for the xenobiotic, you showed the kinetics was changing, folding and folding.
Yes.
Doesn't the equilibrium change?
Equilibrium.
You showed the stability was almost the same. With,
Yeah.
and
So,
without
right.
nucleus.
So basically, there might be, depending on the population, you know. So if you have to see the stability of completely folded, well-folded protein versus folded protein in the xenonucleus,
Right.
there should be small difference because after all, the chemical composition is different. Right? You have added molecule, bound molecule interactions. So, but the thing is that ours are really bulk experiments. So this is where the single molecule experiments clearly demarcate that you have molecules which have genome nucleus. Clearly, I can pinpoint in my single molecule experiments that this stability is different. And in the same heterogeneous population, and definitely single molecule fluorescence is one of the ways one should really go about it.
Right.
People like you. Good, thank you.
Yeah, thank you. So, any more question? If not, let's thank Koti to start with, and then all three speakers.
Yeah.
And let me thank Jyotishman and DCS for having us here. So, all the students.
Yeah. Thank you, Biddut. Thank you for doing a fantastic job. And now is the time for a bit of a break. We will have some tea, coffee outside, actually inside the West Canteen. And after the break, we have a set of four, speakers lined up. And I would request the speakers to put up, if they want to put it up on the computer here, they can put up their talk or use the Zoom. Just to mention, I think there's now a wider audience here. I welcome all of the colleagues coming from different parts, from Delhi, from our other institute, IIT Bombay. Samir Maji is here, Indo is here. So thank you all for coming through. I know it's not a very long trip, but it still is you have to go through sometimes the rush hour. So let's head to the tea area, and then we will come back with Kanchan. Kanchan Garai somewhere should be there. He has to host the session. He was here. Okay, he has to host the next session. So thank you. पानी का बॉटल কি খবর মাঝখানে এবার ফোন করেছিলাম তো তুমি তুললে না তারপর আমারও ফোন করা হয়নি Session chair is most important, bhai. Session chair is most important. We are going to now let's start speaking. Under antibiotics, given antibiotics, improving but not very rapid. Okay, the meat. He's working with your lab mate. He's working with lab mate. Class. Oh, you're working with class. Yes. I will start. We're going to start now, and there are a set of 4 talks, and I am very happy that Professor Kanchan Garai is here from TIFR Hyderabad. Of course, we missed him in the annual meeting, but he's kindly come here for this exclusive session as well as the other aspects of FCS and all. But Kanchan actually graduated sometime in 2007 or 2007, yeah. And so now we are backtracking with, we started with Bidyut, the session chair, but now we are going back. So Kanchan, thank you very much, the chair.
It's a real pleasure, and I'm also fortunate to be here. Okay, yeah. So first of all, a lot of thanks goes to JD, because I'm really thankful and that JD has put together this amazing program. And when he first wrote me the email, I was thinking, yeah, I mean, we should have thought about it, but it's JD who ultimately the man with a lot of energy, which probably got transferred a lot from Sudipta as well. But JD is always high energy, right? So thanks to JD first for putting together the program and also asking me to come and putting me as a chair as well. And since JD wants me to talk about Sudipta a couple of lines before the session starts, and although I find it very difficult to praise Sudipta in front of Sudipta, and as a student, I was more of a troublemaker than try going around praising him. Therefore, I will keep it very short. Yeah. So the things that you guys probably know, all of you know that I was from physics background, and it was like so much into physics that I wanted to do string theory. So the first 1 year, I was talking to many professors, looking for a lab or a group or an advisor to do my PhD. And as Koti or Jyotishman probably both said, that Sudipta has this magnetic personality, right? So this is why sort of brings me from string theory to biophysics. The amyloids look like strings, but they are not really strings. And actually today in the guest house, I met some person who was visiting from South Africa, the Indian student. And he said that he works on something called EDS CFT. Whatever the EDS I couldn't fully catch, but it's conformal field theory. And when I was a student, I could know all to quantum field theory, but the conformal field theory is even higher than that. And then I was asking him little more questions. And then eventually I said, oh, it looks more like a string theory, right? He said, yeah, I don't care about string theory, but yeah, I mean, these are sort of somehow related to string theory. So looks like that now, if I would have gone to string theory, somebody would have said that I don't care about string theory. But so far, nobody is saying that about amyloids, right? Yeah, so as you all know, that working with Sudipta is for me, it was a lot of learning. And therefore, anything that I do today is a lot that I learned from him. So I am really glad that I joined him as a student and had this opportunity. And I can see that you guys are sad because Sudipta is leaving from TIFR Bombay. But I am not that sad because you guys know that he is moving to Hyderabad. So yeah, while the magnet attracted me, but now the magnet is there in close to my home. So I am, yeah, partly happy. Okay, with that, I think I will introduce our next speaker, Ankana. And I'm looking for her amazing speech. And we all know how she's a great, captivating speaker.
I think it's on now.
Yes.
It's on. Okay. Pointer, yeah. I don't want to change the pointer now. फिर मेरा surprise ये हो जाएगा. Debug करेगा तो देखेंगे. Okay. So बाद में देखते हैं. नहीं चलेगा तो check करेंगे. Okay, so it's, very emotional to talk about Sudipta and, in his symposium. It's almost like we can't believe that Sudipta is not here or around us, but he is. So today I'll talk to you about this work that we have been doing for quite a while, which is on lighting up lipids. And there's a reason why I can put Biophotonics under my name, and that will be clear in a bit. But this name was given with a lot of deep love and emotion from JD. So we have this, I had to put this on the side, Biophotonics at TIFR, a halo of memories. So this, I would say, my work has been more in the halo of fluorescence at TIFR. And this is a painting that my student Smitarupa has drawn. So I just thought of putting it up here. So what do we do here at TIFR? Well, we are the chemical biology and molecular imaging group, and we are in the business of making fluorescent molecules, which can, have lots of applications ranging from fundamental biomolecular imaging to detecting pathogens, disease diagnosis and drug screening, and so on and so forth. But where did we start? Okay, and this will be very educational for Shomnath here. So I joined TIFR in February 2010 when TIFR was not prepared for a synthetic chemist. Neither was TIFR Hyderabad prepared because TIFR Hyderabad was not there. So essentially, the question was, where do I get students from and where do the facilities come from? How do we start our lab? And this was a question. And, we had lots of interesting ideas from scientists coming that can you set up a synthetic chemistry lab in a balloon facility, for example? That didn't happen because of two people. One was, in around April 2020, I met GK in the corridor and he was like, Ankona, I'm going to have an eye surgery. And I have this VSRP student, which is the visiting scholar research program student that we had. And will you be okay mentoring him? And I was like, yes, I'll mentor him. But then the thing was that I had, I'm always like that. I'm impulsive. So I took that opportunity, but I did not have a lab. And the plan was to develop, of course, my research proposal was on developing near infrared, optical, magnetic resonance imaging, all these kinds of smart sensors. And I didn't have a lab. We didn't have any lab. We didn't have chemicals. We didn't have any imaging setup, but I was very hell-bent on, starting this. So I looked into my proposal. And then I had this idea of developing cyclic peptide-based metal ion sensors. And the idea was we take very simple peptides and we convert them into cyclic peptides, and then we reduce them, right? And these can actually bind to metal ions. And you see, how this project actually grew. But this is where I felt that, okay, so I'm a synthetic chemist. I've made one of the most difficult molecules in my PhD, porphyrins. I had made hydroxypyridonates during my postdoc and so on and so forth, but I had never made a peptide. I knew the theory, but I had actually never done it. And of course, we did not have a lab. So who came into our rescue was Sudipta. And so he had a peptide synthesizer because he was working on amyloids. And so he said, yes, you can use my lab. And the interesting thing was Sudipta, when I joined, was actually probably in Toronto in Gilbert Walker's lab. So he was not here. So he said, and little did he know that isko matlab lab dena matlab kya ho sakta hai. But he said that you can use the peptide synthesizer and you can use it. So he said that. I said that's fine, but then I didn't know how to use I'd never synthesized a peptide before in my lab. So here he introduces me to a student who is one of the finest individuals that I have actually met in my life, Bidut, who actually one afternoon, so I said, the student is coming, I have to learn how to make peptides, otherwise I am not going to be able to mentor the student, right? So one afternoon, I bought a notebook from this TIFR notebook, and then Bidut very nicely mentored me and taught me how to make a peptide. We actually synthesized a peptide. I was very happy. So I made my first synthetic peptide in TIFR sometime in May 2010, preparing for the student who is going to come. And then we didn't have amino acids also. So Sudipta said, raid my fridge, you use whatever amino acids you want. And so we started using these amino acids and we started synthesizing this peptide. But of course, after you synthesize a peptide, you have to, cleave it and do lots of things. So he even allowed us to work in this very tiny space that he has outside his, optical setup, where we could actually then cleave the peptides and do the studies. It was a very successful project, by the way. We made the cyclic peptide, we characterized by NMR, again, something that I had not done peptide characterization with NMR. And I kept on doing this, okay? So since the last 14 years, wo mera picha nahi chhura paye hai. I have, been using all his, equipments, whatever he has. Now we are also going into Raman. But so we have used his equipments through and through. So we took these pictures, I think 2 days back. So your lab looks exactly like this. This is just 2 days back. And we started. So we were ready to fly. So we didn't fly from the balloon facility in Hyderabad. We actually flew from the Biophotonics lab at TIFR with the initial students and the lab that started. So this is 2024, where we are, developing probes that can actually visualize molecules inside living systems in a confocal fluorescence microscopy setup. Again, something that I completely learned and picked up when I came to TIFR. So where do I come in as a synthetic chemist? Well, the idea was to track molecules inside living systems and understand how life works. And of course, you know that molecules of life do not fluoresce in the visible. So this is where we come in being able to develop synthetic chemical probes that can either give an increase in fluorescence or a change in emission when they bind to the analyte of interest. So this project actually started, lighting up lipids actually started very early on in my lab by trying to develop protein-based sensors for lipids, which are lanthanoproteins, which glow in the presence of lipids. But very early on, we realized that if we have to see lipids, most of the signaling lipids are on the inner side of the cell membrane, and proteins are not cell permeable. So we had to go and start developing cell permeable peptide-based probes for looking at lipids, and this is where we have continued developing probes for signaling lipids. And today I will tell you a story that also has another connection with something that we did with Sudipta. So I'll start with why we wanted to detect lipids. Well, lipids form the border, and people who have heard this, part of this talk, the introduction is going to be similar. So lipids form the border of the cell, and so this is going to give you practice to give my talk if you had to give it later on. But anyway, so why lipids? Well, lipids form the border of a cell, and they allow restricted access to the cell membrane. And there are about thousands of variants of lipids on the cell membrane, which are participating in many critical processes on the membrane, ranging all the way from signaling, trafficking, cell movement, and many, many other processes. So what is happening in all of our cells in seconds to minutes time scale is that the lipid distribution on the membranes is changing, right? And this change in distribution is important in recruiting the proteins, which are the spatiotemporal regulators of signaling processes of life. So in essence, this dynamic distribution change of lipids on the cell membrane, which is brought about by proteins and enzymes, is regulating all of these essential and critical processes that are going on inside living systems. So the idea here was that we want to see lipids in order to understand cell signaling processes and also diagnose pathophysiological conditions. And we wanted to detect this very specific class of lipids known as phosphoinositides. So most of you have heard the introduction yesterday, but phosphoinositides are major signal mediating lipids on the cell membrane whose concentrations are really, really low. And reversible phosphorylation at the 3, 4, and 5 position generates 7 phosphoinositide species. Now, the lipid that I'm going to talk to you about today is phosphatidylinositol 4,5-bisphosphate, which is present on the inner side of the cell membrane, and it is also present in organelle membranes, giving organelles their identity. Okay, so in essence, what happens when Vidita showed this already, where PIP2 was shown in one of her schemes, what happens is during signaling processes, PIP2 cleaves off from the membrane and produces this second messenger called IP3, right, which then releases the calcium from the endoplasmic reticulum. So what we wanted to do is we actually wanted to see this signaling processes and how the lipids are basically inducing or mediating signals on the cell membrane. So very early on events that happen when, let's say, a substrate like a psychedelic binds to a receptor. So how would we do that? Chemically, this is very difficult because there are 7 species which are almost identical in structure. And now the other issue is that for this particular lipid, which is the center of classical signal transduction in all of our neurons, the head group and the second messenger has exactly identical structure. So chemically, how do I make a sensor that is going to selectively bind to this and not to that, which is both of which have very distinct functions in the cell? And most importantly, this is the lipid that is central to the regulation of ion channel transport, signal transduction, cell motility, phagocytosis, name it. So we actually, we were introduced to this project by Sandhya Kaushika, a colleague of mine, and I'd never heard of phosphoinositides before that, which was good because I came from a blank sheet and I drew what is needed to make a sensor. So I drew that, this lipid is inside the cell, so my sensor has to be cell permeable. Now it has to go and bind to the lipid, and it should give a change in the emission when it only binds the lipid. Then I'm going to be able to make a reversible probe that is going to be able to detect the lipid dynamics inside the cell. And this has to be reversible, right? But how do we go about doing this? Well, we knew by this time, because we were dabbling in peptides, that peptides, positively charged peptides, are cell permeable. So we wanted to look at peptide binding scaffolds from proteins that are the signal mediators and see what we could do with that. So there's this one very interesting protein called gelsulin, which is an actin regulatory protein in which we have a positively charged peptide sequence, as you can see, with a C terminus that is enriched in positive charges and an N terminus that also has, some positive charges. This is an overall positive charge. It has been shown that this peptide can bind to the lipid even when it is taken out of the protein, and most importantly, a solution structure of this peptide in a helix forming solvent was known. So we went, so now the problem here is that there is huge concentrations of ATP and other negatively charged things inside the cell. So why should this peptide bind to a lipid that is present in micromolar concentrations and is the least abundant phospholipid amongst other phospholipids that are anionic in nature, right? Why should it go and bind? And we needed to understand this. This we did with Ravi Venkatramani. So we took the NMR structure of reported structure of the peptide and placed it on a membrane in silico, which has majority of the phospholipid phosphatidylcholine, which is the major constituent of the cell membrane, and the PIP2, the lipid that we want to detect, and we wanted to see what is going on. And we found that initially the C terminus, which has positive charges, interacts with the lipid head groups, forms very directional contacts, and then the peptide dips into the membrane. And here, this was already there in my mind because there were some MD simulations that had already shown this. And when we repeat the MD simulations, we see the exact same thing. Every time the peptide comes, the C terminus binds and the N terminus dips into the membrane. So this was the strategy. And this basically is what we have been working on. So the idea that we had is if we now put, and the dipping into the membrane is happening after the event of the electrostatic interaction, which is very, very central to our sensing strategy. So we felt that after the initial interaction happens, if the peptide dips into the membrane, and I put in what is known as a polarity sensitive dye. This also, by the way, I learned in TIFR when I came from talks of Koti and GK, that there's something known as a polarity sensitive dye that changes its emission based on the dielectric of the medium. If I put it in the correct place based on the MD simulations, then what is going to happen is even if this sensor interacts with anything in the solution, which is anionic, it is not going to give a change. So basically, we are not making a selective sensor. We are making binding-based sensor. We are making a detection-based sensor over here. And if it falls off, then we are going to be able to, see this thing. So we started with this, and here again, my impulsive nature comes into picture. So we were looking at this dye that we should put, and this dye happens to be excitable by 2-photon excitation. So my students, usually say, so we'll make this, but then how are we going to test this? And I said, no, we will do it somehow. And of course, I knew that there was something in Sudipta's lab that could help us actually image in multiphotons. So we went ahead and we synthesized it without even thinking of what we will do after we make it. I was like, ये idea अच्छा लग रहा है, बना डालते हैं, फिर उसके बाद देखेंगे क्या होगा. So then, we made this, and very nicely as per our predictions, you see when we make vesicles, again, this we learned from Sudipta Das group because they were also then dabbling in lipids, and they taught us how to make these vesicles very nicely. And so we see that initially there's an emission in the green, which shifts to the blue as the lipid vesicle, this is PIP2 in 10% PIP2 in PC, and as we are increasing the concentration of the lipid. So this is a very nice ratiometric sensor, excitable at 380 nanometers, but 780 nanometers in multiphoton. So this was good, and you can see that this is now the first generation sensor showed an okay selectivity. So it's selective over all other lipids that we tested, but it detects both the bisphosphorylated and the monophosphorylated version. So with this, I then went to Sudipta and said that, can we start imaging in your system? And he very nicely actually not only allowed us to do it, he said, we'll train your student. So they trained Shamshu Joha, and he then started imaging in his multiphoton, and we took the data, and you can see this is the blue emission intensity map. You can see things in the membrane and also in the Golgi apparatus. So PIPs reside both in the membrane and also in the Golgi. So this is something that was positive. We can take a ratio image of the bound to the unbound or bound plus unbound, and we can see here that it is lighting up regions possibly that has high levels of PIP. So this probe actually was cell permeable. So this is the first cell permeable sensor for PIP2s that have been reported. Enters cells within 15 minutes to 5 minutes of incubation, lights up the membrane, and you can see inside the cell it is green, unbound, and in the membrane it is blue. So this was good. And this is 2016 when we published this paper, okay? CS and OWLS to TIFR, and he happened to, include me in the organizing committee. Now, I'm a synthetic chemist. Nobody in this community knows me. So we had FCS 2016, and we were having this discussion about OWLS, and I said, we have to give talks. And he said, no, organizers don't give talks. So I said, nahi, I have to give a talk, because if I don't give a talk, then nobody knows me here, right? So you have to ensure that I give a talk. So I got a talk in the auditorium. It was good. And I'll show you some pictures, because OWLS is coming up, and we had all these first days, second days, hectic third days, so on and so forth, and everything happened. And I managed I managed to be a part of the organizing committee and also invite myself to give a talk. And that was very important, because this was my last slide in OWLS, okay? And I had said that, so the images that I was showing were static images. And my dream was to actually visualize lipid dynamics. So how are we going to do that? So this is where I said, I want to do in vivo imaging and I want to look at dynamics, but we need photostable probes. So this DAN probe is not very photostable. And so in the audience there, Andriy Klimchenko. Oops, what happened here? Was Andriy Klimchenko, who is in the group of Yves Milly, who happens to be the person who has been you want to put them on your peptide. So, so forcing Sudipta to let me give the talk really helped there. And what we did then is he actually shipped his first series of molecules. And later on, of course, we are now synthesizing that in Anupul's lab because there's another story where this molecule is extremely difficult to synthesize because of the moisture sensitivity of the reaction. It does not happen in Bangalore. So we go to Hyderabad to do this reaction because it's dry there. Okay. But anyway, we got the first series of molecules and we made the second generation sensors, okay? And once we had the second generation sensors, these were much more sensitive. You can see there's a 70 nanometer shift and there's about 100-fold enhancement in very low concentrations of PIP2. So this was great. And then, of course, I wanted to see dynamics. So initially, I said, मुझे तो dynamics देखना है, कैसे देखना है, नहीं पता. And we happened to talk to Vidita. And I knew that Vidita was working with, this neurotransmitters. And we read a little bit because I'm also learning biology by this time. And we found that, of course, serotonin, when it binds to the serotonergic receptor, the first thing that happens in classical signal transduction is that phospholipase C comes and cleaves off the head loop from the membrane. And this is a process that my sensor would perfectly be able to look at, right? Because as it cleaves off, it would do this. So I'll not go through, I don't know how much time do I have? Or you're not checking the time. Wow, ये तो बड़ा अच्छा मुझे मिला है. I have a perfect session chair, better than you, Amarto. Okay, so now, so I actually reduced. Okay, so then, we put this sensor in actually not initially neurons, but in cultured cells. But then we actually put them in neurons and we wanted to see the dynamics of this lipid on neurons. So essentially what you're seeing here in neurons, in the axonal connections, the concentration of this lipid is known to be high. So when we put serotonin here, you will see that you see some mild changes that are happening with the yellow mountains going down and then becoming red mountains, okay? So we also showed that this was not photo bleaching of the dye. The dye is extremely photostable by just doing a vehicle imaging, and we were able to see that there's no change. So the yellow mountains in the axonal connections go down to red. Okay, so this is the effect of serotonin. Remember, this is what is happening in our brains. Now, Vidita was very interested in these questions. How do hallucinogens like LSD affect signaling pathways? And she's exact timing. My God. Okay, does stress in early life makes us more prone to hallucinogens? And are there any differences in lipid dynamics and signal response to hallucinogens? So let me remind you about the molecules that we are looking at. So this is the hallucinogen DOI. This is the non-hallucinogen lyseride, which is a structural, I would say, analog of LSD. And then we have the neurotransmitter. So you remember that neuron data that I showed you. So now let us look at them, all of them together. So if we have a vehicle over here, we barely see any depletion. With serotonin, we are already seeing some depletion. Now, this is the hallucinogen and this is the non-hallucinogen. I have not started the video yet. That is still depleting. It's like an immediate effect, right? I just played for you once again. So you see those are depleting and depleted all the PIP. And this is actually very low concentrations from what Sudipta does experiments. Two micromolars of these things. So hopefully this is receptor mediated. But essentially, what we were able to do is even with this hallucinogen versus non-hallucinogen, we were able to time the differences. You see there's a profound effect of the hallucinogen, very early stages, and there's lot of depletion of the PIP, while with the non-hallucinogen, you're seeing there's still some PIP left on the membrane. And this is at very early time points. So you're looking at seconds time points over here. And we were imaging at every 5-second intervals, okay? So within about 3 minutes or so, we see the entire effect done. And for DOI, of course, for some of them, we were able to see recovery of the signal or some recovery in other cell types. But here we don't see any recovery. So it's a very profound effect that we were able to catch with these sensors. So now I'm going to try and wrap this up. So with this, actually, this sensor, actually, the idea actually reaped a lot of benefits in my lab, because as you can see, this is a very modular design. I can now change the peptide and the dye, and I can make sensors for any PIPs. So next we targeted a lipid that is present in very low concentrations on the cell membrane. And this I won't talk about here, because this is now saved for OWL's next edition, which is coming, in which my talk is on Monday. So essentially, because the previous OWL reap benefits, we'll try to see what happens in this house. But this actually led to a sensor that can track a lipid that is upregulated in malignant cancers. And this is the first sensor that can do that, and is currently under translation as a breast cancer diagnostic in CCAM. So this kind of brings me to the end of my talk. So we started from here, and you saw that we learned how to make peptides in TIFR, and we made peptide-based sensors that were cell-permeable. But of course, we were also doing manganese, and how can a talk that I'm giving not end with manganese? And we did also make manganese sensors, which were water-soluble. And you can see how this is inspired from the cycle that we had made, which are able to visualize manganese dynamics in living cells. So with that, I would like to end by acknowledging my group members and Rajeshri, who has done all of this work. And there's another link, because Sudipta, when he was a department chair, ensured that since I flew from the Biophotonics lab, like labless, and then, had B130, and now we have NMR 202, which is a beautiful lab with, 4 more fume hoods. And those who have, come back, you can go and see how it is. So I'll end here, but maybe I'll take just a few minutes to show something. And so you see, we have these conferences, right? And the photography section keeps on taking lots of photos of these conferences. We don't know where they're used, so I thought it might be a good place to use it here. So the photography section actually gave me lots of pictures, and I'll just quickly go through them before taking the questions. So this is Sudipta in TWIM with Amnon. Again, introducing us to colleagues from Weizmann, FCS with Koti, very determined, again with Professor Hosur and others, in ground state and in excited state, and in very normal conditions, very, very proper conditions, and, also here with friends, with students, and in this room, and also with his favorite snack. So with this, we would like to end with this picture over here and take any questions. Yes, Divanjan.
I just am curious about one data set. So in the UI fluorescence decreasing data, one bright spot is not going down.
So basically, it's not throughout, right? So it's not uniform. I mean, unlike what people feel, these lipids are not uniformly distributed on the cell membrane, and neither is the receptor, possibly. So essentially, wherever the binding is happening, there is a signaling that is happening, and it depends on the reach of the molecule that you are adding, right? Where is it going and binding, how much it is able to diffuse. And that's what we have been seeing for a long time. Even in GUVs, we see that the lipid distributions are not uniform, and it stays like that. So we have to figure out, but I feel that it is mainly the heterogeneity and also part of the signaling process, because the signaling here is actually spatially regulated also, right? So which direction the signal has to go. Okay. Devashish?
Yeah, a very interesting sensor. So, but I have a thing that this sensor's activity depends on the peptide, right? Basically, it interacts with the lipid and then you sense it. Now, there are many proteins, otherwise cytosolic, which interacts with PEP2 and does many different things in neurons in many cells. So how do you think your sensor can help? Because
it's actually interact, you know what I'm saying? Like it's
Yeah, yeah.
interacting, sensing
Yeah.
it, but then it can also hinder that
Yeah.
interaction.
So basically, you have to realize that these probes that we are adding are probably going in the cell in nanomolar concentrations. The main thing is you have to consider this like a pH indicator. So when you do a titration with a pH indicator, you're not changing the pH of the system. Although if you added enough amount of the indicator, it would, right? So here, the concentration of the lipid, which is around 50 micromolar versus the sensor, is like we are adding only few micromolar. Sometimes they're even acting at 0.5 micromolar or so. So essentially, the amount that we are adding is much less than what is happening. It's just indicative of the process as the binding happens. And also the important thing is that the binding constant of the sensor has to be in the in vivo concentration regime. These sensors bind with micromolar affinity, and PIP2 concentration is also in micromolar. So essentially, it's not as if all of the sensor that you're sending is going to bind. It is indicative of the percentage of binding, like, you're seeing the sensing, and there are many open sites on the lipids where the other function can happen. There's no way really to say whether it is hindering, but I can give you one example for the PIP3 signaling. Radio-labeled PIP3 had shown that growth factor stimulated signaling was increasing within 1 minute and then coming down within 3 minutes. Protein-based sensors actually was capturing this event, which was taking about 5 minutes of time. They are diffusion limited. Our sensor captured the event ditto. It showed that the rise was in 1 minute, there was stabilization and decrease. So I feel that because of the fact that these are small in size, the binding constants are not so high, that we are in a sweet spot where we can look at the dynamics.
I have one question. So
Sure.
when you say dynamics, is it only binding, unbinding, or suppose the membrane has all those ordered phase, disordered phase? So these probes can also monitor
So
those
this
things.
probe, we don't want to do that. We have not designed it to do that. The main thing about this probe is we want to detect a specific lipid on the membrane. But there are, of course, other dyes which can look at ordered and disordered phases in the membrane.
Okay, so let's thank Ankana for giving me a really captivating talk. Where is Ravi? I remember is that much. I trained him, Ravi. You not expert.
Yeah, I don't know why she told him. Actually. Yeah. Can you remind me at 25 minutes?
18. I understand. 18.
Just taking a chance. Yeah, can everybody hear me?
Yes.
Where is this thing? Yeah.
Hide.
Okay. Yeah, I want to first start out by thanking Jyotishman for setting this whole thing up. Actually, this guy is a one-man army. Initially, it began as me and he as co-organizers, but then apart from giving one annoying suggestion about the schedule, I was nowhere in the picture basically. This guy just ran through everything and amazing job, really, truly. And of course, it's a special honor and pleasure to actually speak at Sudipta's, symposium, in this case, right? Sudipta is laughing about it actually. We'll see how much you laugh after we move forward. But essentially, I just wanted to kind of, see, Sudipta is that kind of a character, right? This one character in your life, basically, who always pushes you to be the best version of yourself. That's exactly, I think that's how we can describe Sudipta actually. Because when I came in here, right, I had many ideas in my mind and whatnot. Huh?
That's your best.
Right? Yeah. This guy is ragging me actually. It's impossible to speak. 45 minutes of speech. Yeah. I think I should make him meet Anustup actually, and let's see what happens. Yeah. Anyway, so so when I first came in, I had lots of ideas and everything basically. But one thing that I was not clear about was mentorship. Right? This is the first time starting an independent lab. Students come in and you don't know where you stand with them. Are you able to attract students, etc.? And I had a terrible, disastrous start, the whole campaign. right? I came in, I taught a mathematical methods course in chemistry. And then I somehow managed to miraculously attract one student to give a lab rotation. At that time, lab rotation was 6 months. After 6 painful months, the student came to me and said, "Sir, मेरे हाथ experiment करने के लिए ये हो रहे हैं, तरस हो रहा है." I was totally devastated. I was like, this is not going to work at all, right? Because I was the first computational chemist in an experimental department. It's not going to work. Fortunately, during that, there was a VSRP following that, and I was despondent, but I'd already selected a student. The student came, and somehow that student from IIT Madras, Prashant Ramesh, basically, was really, really cool, basically. I mean, he started doing MD simulations, something Ankita actually also has looked at, essentially, the effects of electric field, etc. actually. So the story I'm going to tell you is actually going to begin with Prashant Ramesh's work, but what they will highlight is Sudipta's encouragement of young faculty, first of all, how he includes them in his research, and then how he comes up with, like, he creates opportunities through his clever strategies, experimental strategies, really, which help us as computational chemists to actually really tackle some interesting problems, actually. So that's what the story is all about. So I'll be talking about essentially this elusive amyloid beta peptide, which most of the people in this audience are familiar with, essentially, which is an intrinsically disordered protein. And essentially all the wonderful biology is hidden in the intrinsically disordered part. And it's extremely difficult to catch it, actually. So I'll talk about atomistic structures of peptide in both monomer and oligomer form, which we've been able to shed some light on. And of course, I must credit Professor Barun now. Right? He was Sudipta's brave student, basically, who actually did a project with me and continued working with me on MD simulations. And with him, we did some really wonderful things. We got some really nice insights about amyloid beta, which today, even now, persists, actually. I'll tell Sudipta at the end, I'll talk about, the current work that's going on there. Actually. Oh, okay, this is not working. Yeah. Right. So just setting up the problem. I mean, everybody's familiar with this in this audience. Right. So amyloid beta, the main problem is amyloid beta aggregation, which is once you actually have this fibril stage, that's where you have the disease. And that's where the main problem is. That's where the problem is detected. However, the problem doesn't begin here. The problem actually begins somewhere here. Right. When this innocuous peptide, which is present in every healthy human being, actually, which exists in monomer form, starts to develop a propensity to aggregate. It then forms these small oligomers, right? And then becomes fibrils eventually. What Sudipta has shown, and others as well, that small oligomers are like the most toxic component of this particular species, right? But this is transient. There's almost like a non-equilibrium situation, actually, where you're completely getting driven towards the fibrils. So essentially, one would like to know the structure of the amyloid beta peptide in this small oligomer form. Moreover, if you look at the monomer itself, you can ask essentially what drives the propensity of monomers to actually aggregate, actually get into the small oligomer form, and then eventually go to this particular state. Actually. So these are the two questions that actually, we assisted Sudipta in actually addressing. So the first question, I'll start with the monomer first, which was Prashant Ramesh's work, right? So as I said, Prashant came in and we did these electric field simulations. The simulations were spectacularly boring. He took peptides, he put them in electric fields, and what we showed is that if you have temporally varying electric fields, etc., if the electric fields are all the frequencies that typical lasers use, really, I mean, they should not matter too much to the structure of the peptides. So I kind of casually mentioned this to Sudipta at some point, right? And that actually catalyzed a collaboration. So this is Sudipta's idea. So as it turns out, we are talking about the aggregation propensity of this particular peptide. It looks like pH is one of the big factors that actually controls this aggregation propensity. So if the pH is about 10 or so, then the peptide is soluble, incredibly soluble. But when you take the pH to 5.5 or so, basically, then it becomes insoluble. The solubility decreases dramatically, 100 times, greater than 100-fold, actually, overall. So the question really was, this change in solubility typically leads this peptide to aggregate. But why does it do that? I mean, does it do it because the pH changes the conformation of the peptide itself, for example, or is it something else, for example? So Sudipta wanted to actually disentangle this complex problem. So he, along with Gilbert Walker, and it was spearheaded with Debanjan, who's in the audience right now, came up with this wonderful idea, basically. They took silver nanoparticles, about 50 nanometers, and they grafted amyloid beta peptides on the silver nanoparticle. So the idea was to put the peptides, to place the peptides in such a way that they cannot aggregate, they cannot come together, right? They are isolated in some sense. But essentially, if you change the pH around this, if the local pH changes, then you can talk about the pH changes and how it affects the conformation alone. And then that can actually help you understand whether pH changes the conformation, therefore it leads to aggregation. Wonderful idea. And then when I was talking to Sudipta, I put this, so when you collaborate with computational people, probably some, muddy waters, if everything is looking clear. Sudipta already had the result, and it was absolutely perfect for him to just go ahead and publish it. Not a problem, basically. But I muddied the waters a little bit, asking him, you have this nanoparticle. Now this nanoparticle, you're actually exciting it. You're using surface plasmons. Plasmons generate these very intense fields, electric fields. About, it can actually reach about like a volt or like, some hundreds of millivolts per nanometer or something like that. So the question is, do the peptides, whatever you're seeing through the plasmons, is it actually a result because of the field? Or is it actually because of the intrinsic property of the particular peptide, right? Moreover, if you look at essentially these nanoparticles, typically when you prepare these nanoparticles, you would like to actually functionalize them, etc., so that they don't aggregate. So the solution has a zeta potential, right? It's about 30 to 40 millivolts as well, actually. So if you think about the zeta potential, then there is also a static electric field component, which is actually dropping with the nanoparticle. So how are these electric fields actually influencing the thing? So this is something that we just had a discussion, and he generously actually included us in this particular work. He really didn't need to, right? But we really ended up actually helping. So Prashant Ramesh actually ended up doing the simulations of this particular peptide, and we investigated essentially how this peptide would look when you expose it to electric fields, both static and temporally varying. So this is just just snapshot. We did like incredibly short simulations, 5 nanoseconds. I know it looks ridiculous by standards of microsecond level simulations actually, but the point is all these simulations are done in the presence of strong electric fields, right? The electric fields that I use in the simulations are about 1 volt per nanometer. So this is much higher than the typical electric fields that those peptides would experience around the nanoparticle, which would be about a millivolt per nanometer, thousands of times forward. And what we're asking is, if you take this particular peptide, particular helical conformation. So why helical conformation? Because Sudipta found evidence that the peptides on the nanoparticle surface actually is in a helical form, right? And then you expose them to electric fields, and then you do controls. What you find is essentially with the temporally varying electric field, with the surface plasmons overall, you don't see significant change in the structure, just as you would see in a control, right? Without an electric field. But if you actually subject it to a static electric field, or whatever it is, then actually you start seeing changes in the structure at this level, at 1 volt per nanometer in that case. So this was, I think, a control calculation that we did, which simply helped him eliminate any artifacts that he was doing, basically. So I think
very helpful for us.
Yeah. So anyway, so this kind of tells you that even though you have an experimental result and everything is working out, you have an explanation of whatever it is. Ruling out all the artifacts may actually provide you nice insights and whatnot. I'm moving on now. So the second problem is, so I'll just go back to this slide. I should have really put a second slide in here. So this problem of the small oligomers in this case. So as I said, here Sudipta came up with a clever idea of taking nanoparticles and grafting peptides. Here also there is a clever idea actually. So you want to capture the small oligomer conformation. Right? Experimentally, you would like to capture it. But how do you do it? It's a transient species. So Sudipta's group actually came up with a wonderful flash freezing technique. Essentially, they create solution conditions where the peptide has a propensity to exist more in the oligomer form, etc., where it's actually more stable in the oligomer form. And then you take that and you flash freeze it, right? And once you flash freeze it, basically, then you can actually use that sample in NMR experiments to actually figure out more details about the structure. So Sudipta's experiments, which was both spectroscopy, his own IR spectroscopy, as well as Madhu's experiments with NMR, actually gave us lots of information about what are the possibilities of the conformation of the peptide. So this is one possibility that came out, that this particular peptide, which in fibril form exists in a parallel registry, right, where all the peptides are arranged in parallel order, they become anti-parallel in this particular case, right? So now the question was, what Sudipta, again, this time Sudipta actually approached me and asked me essentially, is it possible to capture the oligomer conformation of this particular peptide. Now, there have been other people in the work. I'll just explain this in a second, actually. But there have been numerous attempts to do this before. But the typical way to do it is in the simulations, you take many copies of the monomers and then let them aggregate. And once you aggregate, you can actually see maybe some small oligomer species, etc. Now, this is an incredibly time-consuming simulation. It's really long, and there is no guarantee that you're going to see what you want to see. Right? So it was very difficult. So we came up with a very different solution, actually. And see, I do also electron transfer, etc. So these are like electron transfer Marcus curves. So the idea is the following, actually. You take, for example, the fibril, we know what the structure looks like in fibril. For example, this is TICO's NMR structure, which is captured from this particular fibril, right? And this structure, which has a parallel registry, like what we know, is perfectly well organized and very happy in the fibril form. So this I call the fibril state, right? What I do is I subject it to a shock in my simulation, basically. I extract a particular fragment out of that, right? And then solvate it, right? And then let it evolve. So what is the idea? The idea is I create a small oligomer model, which is completely solvated, right? And this small oligomer model now is very uncomfortable because it doesn't have those contacts which are there in the fibril form. It is fully solvated, and therefore it should evolve to something that looks like the oligomer, right? Now, of course, I had no idea how rugged this landscape is, where would it get trapped, etc. So those experimental signatures I mentioned, right? Those IR data, for example, and those contacts that Madhu got, those are critical for us to see whether we are actually moving in the right direction or not. So I proposed it to Barun, and Barun enthusiastically actually started carrying out these simulations. And then ultimately the idea was to see an oligomer-like state and see if there was an antiparallel conformation that would come out. This was the hypothesis. If everything was right, this is what should happen. So these are the experimental signatures that Sudipta provided to us. Antiparallel hairpin conformation was the thing through the IR, etc. And then Madhu's data told us that there should be an F19 L34 contact, there should be a salt bridge G23 K28, and there should be this E22 I31 contact as well, actually, right? Now, the challenge here was, when I say small oligomer, what the heck do I mean, actually, right? Small oligomers mean, they could mean trimers, or they could mean dodecamers, for example, right? So we had to have a way to actually solve this problem going through this whole bunch. So the way Barun and I decided to tackle this is we started simulating everything from trimer to dodecamer, right? But we ran short simulations, about 40 to 50 nanoseconds of these trimers to dodecamers, and then asked whether any of these simulations are actually going in the right direction or not. That's a simple question that we asked. And how do I know it is the right direction? These points, actually. So I'm sorry, this came here. So this is the overall scheme. You take the fibril, you cut it out, you make simulation models of the trimer to dodecamer, and then run it and ask if you're going to get this oligomer form. So when we started doing this, what we noticed, we got some very brilliant, beautiful insights in this, actually, right? So if you are a trimer, which is the smallest possible oligomer in this particular scenario, or even dimer, for example, when we started simulation, basically, we saw that essentially the structure tends to become disordered completely. The number of contacts are never sufficient for it to adopt any kind of a conformation which is even stable. Trimer is too unstable. That is the conclusion we drew even from the 40 to 50 nanoseconds of simulations. This is a simulation of the protofibril that was there in TICO's experiment as a control. And that itself also starts destabilizing, right? In different ways, essentially, but it is still, kind of maintaining some kind of a parallel registry, which is a imprint of the previous thing. So you don't want to be in protofibril, you don't want to be in trimer. And then as you move forward, you start seeing something better, actually. With tetramer, you start seeing some stable conformations, right? These pictures actually don't do justice in this particular case, but in the simulations, if you start measuring contacts and the non-bonded interaction energies, you'll find essentially that this is more stable as compared to these structures, actually. But now here's where interesting thing starts to happen. If I go for a nonamer, right? In the nonamer, what seems to happen into a pentamer versus a tetramer? So here's the point. At trimer, you're too unstable and everything starts dissolving and you're not able to form anything structured. If you go towards octamer and higher, you start breaking into smaller, segments. And so the most stable conformations actually appear somewhere in between, where the tetramer, pentamer, hexamer, that's where something can happen, actually. So this is what our initial preliminary simulations actually showed us. So we persisted with the simulations, and then when we looked at essentially these pentamers and hexamers, we found that spontaneously within the pentamer and hexamer, we started seeing this parallel registry actually shift to this anti-parallel form. Now, what is quite amazing about this is this forms on a timescale of hundreds of nanoseconds, first of all, right? And secondly, this structure, once it forms, is stable for hundreds of nanoseconds. Like it was stable till we were able to simulate it. But when you simulated up to what, 800 nanoseconds or something, or 500, 600 nanoseconds. So he went up to 600 nanoseconds at that point, basically. But the thing, this anti-parallel conformation is stable in that particular pentamer for up to 600 nanoseconds, right? Whereas in a trimer, it would dissolve in like in about 40 to 50 nanoseconds, for example, that is. So this tells you, now the background is essentially that these anti-parallel hairpin conformations had been seen before in simulations, right? In certain types of experiments where people had engineered contacts, for example, etc. But in the simulations or, you know, whatever, the structures are very, very transient. They would form and they would dissolve. They would form and dissolve. The pentamer and hexamer type oligomers seem to provide a right environment with a stabilizing contact where this anti-parallel hairpin conformation can remain stable for really long periods of time, actually. And if you're stable for long periods of time, you have the chance to actually attack the cells and actually create toxicity in this particular scenario. So this was something which was really exciting. So we actually verified, you know, various types of contacts. Like this is how the contacts look. This is a residue to residue contact, for example, when you are in the parallel registry, and then this is when you actually become the anti-parallel conformation, etc. And we verified essentially how these contacts are breaking, and actually even created an energy landscape based on the data that we have actually. So this energy landscape is typically showing essentially that most of the, once at 100 nanoseconds or so, essentially you are actually going over to this anti-parallel conformation, which with signatures like this, and then here you actually have stable states for each of these reaction coordinates, right, which actually are forming along these areas actually, and somewhere here essentially is where your initial beginning structures are. So what I wanted to tell Sudipta is, now we've taken this forward, right? And what we're asking is some very simple questions. For example, Daniel Huster's group has created mutations of the phenylalanine and leucine contacts, where if you mutate either one or two, single or double mutants, you actually see that the toxicity of the peptide is going down. So one of the questions was, essentially, is it happening because this anti-parallel hairpin conformation, for example, gets destabilized overall? So here we have actually kind of started addressing this and started describing energy landscapes. Now, these are much more quantitative energy landscapes than what we had before, right? Because now we actually have an umbrella sampling protocol, Sudipta, where we are able to actually, take this particular peptide and figure out what the reaction coordinates are. You see these reaction coordinates here? These reaction coordinates they're well correlated with COM-COM separations, but we're not taking the COM-COM as a reaction coordinate. You kidding me? Yeah, it's okay. Okay. Yeah. So anyway, but they correlate really well with COM-COM separation. So my point is that when I do any kind of energy landscape and projections, right, I don't need to guess a priori what my reaction coordinate is. I do the unbiased simulation run, and I can extract these principal components, which actually already tell me what the reaction coordinates are. And then I can do an umbrella sampling on that and get quantitatively, quantitative free energy surfaces. These are actually quantitative, as opposed to these are qualitative, because I had to guess what this reaction coordinate is, number one, and my sampling is not enough. Here, the sampling is enough. And I can tell you here that there are these mutations, proline to all of these guys, basically where the black line is showing you essentially what the standard anti-parallel conformation is, wild type, how stable it is. And after you do the proline mutation, how that energy landscape changes, right? So you can see that these mutations actually stabilize it to different extents. Destabilize it to different extents. And these mutations actually stabilize it to different extents. The point of the story here is, even with these quantitative energy landscape, what are we learning? We are learning essentially that the amyloid beta toxicity, which was getting abated, is not because of the destabilization of this particular thing, because all of these mutations actually lead to less toxic conformations. And I just take 30 seconds at this point. So Sudipta, where we're going with all this actually is we're trying to integrate it with spectroscopy. So we're also designing this new protein charge transfer spectra, which can actually probe aggregates as well as protein-protein interactions in condensates. So we'd like to bring this all together essentially. Our simulation ideas, the quantitative models, and essentially talking about what the spectroscopic signatures are. And I believe these are the kind of spectroscopies that will actually help you solve the liquid-liquid phase separation type problems in this particular case. So with this, I want to just thank Sudipta. I just had a couple of pictures. You can see Vicky, who was a joint student between me and Sudipta, actually, he's so blissful, right? Sudipta's phrase was, "Aankhein band karke bhi bharosa kar sakta hai." Overall. And this is me, Sudipta, and JD, of course. Right, yeah. Okay, so thanks, Sudipta, for everything, for a wonderful presentation.
Questions?
So, I forgot one thing. So when you look at this contacts of antiparallel beta sheet formation,
Yeah.
what is happening to their contact with the other members of the tetramer or pentamer hexamer?
Yeah. So, I mean, so there are contacts of this particular antiparallel conformation with the remaining things. So the first thing I wanted to note is, I don't know whether you caught that actually. Actually, I didn't show that. Whoops, it's getting haywire. Yeah. So, I'm sorry, I don't have a picture of that. But let's look at this tetramer actually. So the antiparallel hairpin conformations always form on the terminal segment, which is most exposed to the solvent. So one side is always exposed to the solvent. That catalyzes the parallel to antiparallel to antiparallel transition. That's the first thing. And then once that happens, the remaining, base actually serves to stabilize that particular antiparallel conformation in that case. So there are contacts, but only on one side, right? We don't see something in the middle changing to a antiparallel conformation. What? Oh, yeah. So, right. So that we have to still analyze it properly, actually. So we haven't done a proper statistical analysis of that, actually. Right. Actually, I think what Varun and I concluded at that point, this is a little bit of old work, actually. What we concluded is, I think we need to run it on a diverse set of, we need to have a statistically meaningful number of simulations to actually figure out those contacts. Because there could be different configurations of the base, which can actually form contact with the, antiparallel conformation, right? So, yeah.
Okay, I have one question.
This work really told us a lot about things that could have been solved or guessed without an MD simulation. It really was beautifully hand in hand with the experimental results, revealing details that the experimental results would not tell us, but giving us insights about how this works. So it was really nice.
Yeah, no, it was truly a wonderful, back and forth, actually.
Yeah, very nice talk, and it was so nice. I will have a question also, but I wanted to praise this first before this. So
after ragging,
it was so nice that I forgot to look at the timer until Jyotishman.
For you to
that to me. But anyway, so as you know, in biology, this A beta is not alone.
Yeah.
So there are things like lipids, for example, very obviously there.
Right.
So I don't know if you are planning to do simulations.
No, indeed. We started some work with Vicky, right? Vicky was, so my plan was essentially to ask, I know that a pentamer can stabilize an antiparallel conformation, but now if I put the peptide inside a lipid bilayer, for example, can that also stabilize that, for example? If I put it in solution versus in lipid bilayer, right? So is the pentamer or the small oligomer a medium to transfer this antiparallel conformation to the lipid where it remains stable so that other antiparallel conformations can come together and form a core, for example? This is some of the questions that we wanted to start.
Okay, then we'll discuss it more.
Yeah.
At the lunchtime. Yeah.
Yeah.
Okay, so thanks, Ravi, for a wonderful talk. We should clap. Okay, so now I invite the next speaker. Yeah. Your time starts now. Yeah, your time starts now. And I haven't started.
So when I realized I was after Ravi, I cut down 5 slides. But the wedding has taken on the wall. Somebody has उसमें तो नहीं है किसी के लैपटॉप में लगाओ अच्छा अच्छा Yes.
Sorry. Yeah. No, this here. They want to make this full screen. What happened? Oh no, yeah. Yeah. No, yeah, that's fine. Ah, you can hear me, yeah. Sudipta's left.
He could not take this argument.
Should we wait a few minutes or is he going to come back or?
I think he just went to the restroom.
Okay. No, sorry, I didn't mean to.
No. It's out for a bio break and then there are people standing there and everybody is wanting to talk.
Of course. I met Sudipta soon after I joined NCBS when I invited myself over to TIFR because of some visa thing which I had to go to the consulate or something. And since then, I've been bumping into him at various places. We had dinner in Delhi with GK and somebody else somewhere in the middle. And then in IIT Kanpur, he took a bunch of us and described what happened here and what happened there when he was a student and what happened there when he was a student. So it was, the dinner with GK was interesting because he was talking about how they used tonic water for his first experiment in Robin Hochstrasse's lab. So one always had these interesting conversations with Sudipta. And I was here, I don't know why, in 2018. And at that point, in TIFR, I was diffusing through for some reason or the other. And of course, Koti and Sudipta were working on this problem, which Koti introduced on ubiquitin. And of course, they had approached Ravi, the friendly neighborhood computational chemist, to do something about it. And maybe Ravi had too much on his plate or whatever it was. He said, no, you go talk to Shachi. Her models will probably be able to. Huh?
Ravi suggested your name.
Yeah, that's what. So he said her models will probably be able to deal with this. So maybe you should talk to her. So this story starts in the West Canteen, where I spoke to Sudipta and he said, oh, we have been looking at this problem where we are using what he called the xenonucleus. Or that time it was exonucleus, then it became xenonucleus, where you basically take a piece of ubiquitin, ubiquitin from Koti's lab, they had, between Koti and him, they had decided they would add just the folding nucleus of ubiquitin in with ubiquitin, and then see whether the protein sort of folding was affected, so as a folding modifier. And so whether I could do something, and and our models, actually, we do a lot of domain swapping simulations. So our models are really perfectly set up for doing this. And so again, here is sort of the pictorial description, all of this, which is, here is a protein and here is sort of maybe its nucleus. And if it folds by itself, the nucleus forms first and then it goes to the native state. Or otherwise, you put this sort of foreign or xenonucleus in, and then maybe some set of proteins will actually use this and fold on to this, and then you get
what we've been calling the peptide folded state. So this we'll call the native folded state, and this we'll call the peptide folded state. And so could we do something about this? So I built these coarse grain models, and I really loved this problem. So I said, okay, fine, we'll do something about this. But because I do these coarse grain models, I do like 1,000 controls because I make my own model, I have to whatever. And so, when somebody comes to me, and an experimentalist specifically comes to me and says, okay, can you work on this problem? What I've realized is that your timescales have to match, right? And my timescales really never match with experimental timescales because I usually get to the problem really late. And by then, I can see 1 year's worth of work where they say, okay, can you tell us something, in 3 weeks' time? And so when Sudipta came, I also had this, I wasn't sure this was all going to work out. But then I realized when Sudipta said the manuscript is going to get submitted in 3 weeks or 3 months or whatever, it was a good time to start building the model. And so there was enough time to build model, do controls and so on. It would still all be sort of useful in some way or the other. So that's why this collaboration came about. It's been really nice. And meaning as with many of the stories here, the problem starts with Sudipta and then we've taken it forward in other ways, right? So he's the root of the problem, exactly. Yeah. So okay. So I'm going to tell you a little bit about what we did, our contribution sort of to this problem that Koti and Sudipta started, and then I'll tell you where we've taken it from there. So here is ubiquitin. And you can see its secondary structure colored from blue to green here. So there's beta 1 and beta 2, and that is the folding nucleus. And this beta 1 specifically makes, meaning you can see that beta 1 and beta 5 are close and they have a lot of interactions. This is what is called a contact map, which means that anytime two residues are close, you put a square there. And in our models, actually, this is all that goes into the model. So you really can only fold to this state, nothing much else is happening. So beta 1, beta 2 has these contacts. That's the contacts between this. Beta 1, beta 5 are the contacts between this blue strand and this. And beta 3, beta 5 are contacts between that and the others. And these all will come in later. But the main thing is the beta 1, beta 2 is the hairpin, and that's the folding nucleus. After seeing that movie sort of a few days ago, I decided I should show you some real simulation movies. So I will show you that. So here is ubiquitin folding in our simulations, and you can see that the blue bits actually, you can see that the blue bits actually form fairly early on. And then everything else comes together. So you can see that even in our simulations, that blue, this part is the folding nucleus. It forms early, and then the rest of the protein comes on top of that. Oh, sorry about that. So maybe this will work. Yeah. So then, of course, we did lots of, this is just one transition. We have like 100 of them, maybe 1,000, I don't. Lots and lots of transitions. Later, we get this nice smooth free energy profiles because we are doing this at folding temperature and so on. And you can again see, you can go along, and this is how the protein folds. So if you take a slice here at this point, this is when the protein is about 40–45% folded. And then you can calculate a partial contact map where the parts which are in red are more folded and the parts which are in yellow and so on are less folded. So you can see again that this beta 1, beta 2, which is supposed to be the folding nucleus from experiment, actually does form early. So our models are getting that bit right. And so we had confidence that we could do the rest of this. So then what we did is in our simulations, we also added this beta 1, beta 2 externally. We stabilized it in our own way. And then we said, okay, fine, we'll plot this is a 2D free energy profile. On the x-axis is the number of contacts. So this is, if you look at the x-axis, this is how folded ubiquitin itself is, the full protein. And on the y-axis is how many contacts are formed between ubiquitin, the full protein, and this xenonucleus which has been put in. Right? So if you see only U and M, that means that the xenonucleus can't insert. If you see a third state here, that means that the xenonucleus can insert. And the coloration tells you the population, which means that a deep blue color means you have a lot of population. And here, if you stabilize the xenonucleus and so on, you do see a lot of population of this M prime state or the peptide folded state. So not only do you see these two, you also see this one. And then we went and showed this to Sudipta. And then there was this question of whether this inserted state stays inside and so on. And so they did further experiments and it seemed like it was being populated. So
that's something we learned from your simulations, which is being used now by Anu for the
okay. Yeah, that's right. Yeah. Okay. So we were a little more useful than just showing this picture here. Right. So this was a really nice project, and we've also, I mean, we got hooked onto these peptides. But we were, so again, you saw this in Koti's talk as well, which was this lovely collaboration. And so essentially here's the folded protein, here is the xenonucleus, and in some cases you fold and unfold, in some cases from the unfolded state you are getting into this peptide folded state where the xenonucleus inserts and stays. So at this point, we were simulators, of course. So we wanted to do, meaning, as I said, I do controls. So we decided we'll move a little bit away from xenonucleus and start calling them self-peptides, because I wanted to put in every peptide that was there that you could produce from this protein in terms of secondary structure, and sort of prove to myself that this was actually the nucleus beyond what was being seen in experiment. That yes, this part was inserting, but was it really because it was the nucleus? Was it because of something else? So we basically called them self-peptides. We cut up all the pieces and we wanted to put this into the protein. So at that point, so again, this is something that we got because a reviewer asked a question. So this sort of simulations we started doing very recently. And we got this because the reviewer said, okay, great, but you know, if you change concentration, something should happen to your free energy profile. But what, and we did a hack job of this for the paper. But now we do these simulations where we have a single protein and we have multiple pieces of every possible peptide in there. And so now essentially the question is, what is the protein able to fish out? So what inserts and what doesn't insert? And so really it should be specific, only specific pieces of the protein should, of the peptide should insert and others shouldn't insert. And maybe these are also xenonuclei or nuclei, right? So again, I'm going to show you this movie. Just because, you know, movies are exciting. So here is the protein. This is not ubiquitin. This is the C-terminal domain of the main protease of SARS coronavirus. And so you can see that only the blue bits actually have interactions. So they cluster around the protein and then they, one of them goes and insert it. It gets fished out and sort of inserts into the protein. So now we can answer questions about, if concentration of one thing or the other changes, because we have real concentration of the peptide in there. Okay, so, maybe I should do this. Yeah, so we did the same sort of study. So we took every peptide of this SARS-2-MPRO, and we were interested in it for some other reason, and then COVID also came along, so it seemed like a sort of appropriate study to do at that time. And we found that, and this MPRO is a target, and the C-terminal domain is far away. It affects activity without being anywhere part of the active site. So we thought maybe this sort of peptide could be an allosteric inhibitor, which means that resistance would may not creep up as quickly. But anyway, so we did the simulation and we found exactly this, which is that things which this alpha-1 and loop-4, which are things which with early forming contacts. So now the earliest forming contacts is between alpha-1 and loop-4. So either of the peptide works. So the nucleus, if you can call it a nucleus, is not polarized as they say in protein folding terms, but it's far away from each other. And so you can, it seems to insert, and so these are the two things that insert. And so we said, okay, fine, I think we are happy with this nucleus terminology, etc. And then of course, you always do that one extra set of simulations and you take it a bit too far, and then now we are stuck. Right, so we did one, we said, okay, fine, we already have ubiquitin, now we're going to put every peptide of ubiquitin as well and ensure that it is actually, I mean, again, why not, right? So for a variety of reasons, and why not? And then, of course, now we put in every, so again, this is not the xenonucleus in the sense that we're not yet putting beta 1 and beta 2 fully in there. And one of the reasons for doing this simulation is we wanted to grow ubiquitin, because we also do domain swapping simulations where, you know, this is equivalent to have an entire protein as a self-peptide. That's what happens in domain swapping. And we know that ubiquitin doesn't domain swap, at least in our simulations. So ideally, we should go from a place where beta 1 inserts to a place where, as we grow the peptide, in the end, the domain swapping should not happen. So the question is, what is this interface and what is happening? So that's why we started off these simulations. And so you can see that so the way you read this is, these are different peptides added in different simulations. And if you see this third state, that means that you are seeing insertion. And if there is no third state, then that means you're not seeing an insertion. So also note one thing, that these U and F states spread out to having more inter-protein peptide contacts differently with the different proteins. And this is going to come up, I mean, later it becomes important. And so what we found is, yes, beta 1 actually inserts, but beta 2 does not. So this in our simulation, so I mean, we've only done beta 1, beta 2 simulations previously. So now if you just do beta 1 simulations, that inserts, but beta 2 does not. And then we start seeing beta 5 inserting, which is nowhere close, I mean, which interacts with the beta 1, beta 2, but which is sort of far away. I mean, it's not really the folding nucleus at all. Right, so so what is happening here? And so then we've spent the rest of, I mean, I've been sort of driving my student Argadeep, who started off doing the original ubiquitin simulations and then whatever nuts doing all of this. But he's been sort of a good sport and done all the controls that I keep asking him to do every so often. Anyway, so so the first question is, why is it? And we said, okay, fine, what is in our simulations? All we have in our simulations is contacts. Right, so maybe the peptides, some peptides just have more contacts, and really those are the things which are inserting. Right, so this is actually why a folding nucleus is a folding nucleus. It's because it has the most number of contacts. That's where you start off with. And so we looked at individual contacts of peptides, and of course there is no, I mean, there's no way to differentiate between beta 1 and beta 2 and beta 3, beta 5. So all of these, so these are a number of contacts that these peptides have. And really that's not what the distinguishing factor here is. It's not the number of contacts. So what is it? So we said, okay, fine, not meaning really, when you think about how these contacts form, you know, you need contacts which form all together, right? So if I have contacts with one piece on one side and some other piece on some other side, it's unlikely that both sets of contacts are all forming, because then you really need to fold the protein. So we said, okay, let's look at sort of contacts which clump together in the contact map. And here I think we see a signal, which is that beta 1, beta 2 has a whole bunch of contacts, 22 of them, a lot more than everything else. Beta 1, beta 5 has a lot of contacts, 21. And beta 3, beta 5 has a lot of contacts, 22, right? Which means that it seems to make sense that beta 1 has these two clumps of contacts, either with beta 2 or with beta 5. And so beta 1 would insert because it either made beta 1 contacts or beta 5 contacts and sort of stuck to the protein. And if you stick to the protein for long enough in the unfolded state, then you had a chance of inserting at the end. And the same was true for beta 5, which is that it had these two clumps of contacts. So it could either stick there or there, and then it would insert. And so, great. So we said, okay, fine, that's nice. And so now let's go and look at our simulations and see which of these two sets of contacts are forming, and is any of this really true? So do beta 1, beta 2 contacts form first for the self-peptide, or beta 1, beta 5 contacts form first? And so really there are two types of transitions in our simulations. There's unfolded to folded, and there's unfolded to peptide folded. And so we looked at both sets, and then the question is whether it's beta 1, beta 2 forming first, or beta 1, beta 5 forming first. So we sort of took all the transitions that we have and we classified them. And now I'm going to show you movies, and this is for the most part, I mean, this is like, oh, we know how to make movies now, more than really analysis. And so here's one where the beta 1, I mean, the red is the peptide, and this is inserting via beta 1, beta 2. But the more interesting transition is this one, where it's inserting, I think this works actually, yeah. So it's inserting the other way. So you can see that actually this is a lot more accessible, the beta 5 region. And so it sticks to the beta 5 region a lot more easily and for a lot longer time. And so, in fact, that was what we saw. We saw that our transitions actually of this was not because this was a folding nucleus, so to speak, because beta 1, beta 2 are so close to each other in the protein that it is very hard to sort of outcompete the self beta 1, beta 2 interactions. So in our simulations, at least, for the most part, the way the transitions goes is that you have the U to F. So these are the U to F transitions in ubiquitin without any self-peptide, right? So this is why ubiquitin, and 95% of the transitions start with beta 1, beta 2 forming. There's a small percentage where what Arkadeep calls inconclusive is that you don't know which of those sets of contacts are forming first. So he doesn't know how to classify this transition as beta 1, beta 2 or beta 1, beta 5. So, but 95% of them go by this beta 1, beta 2 route. And if you look at the intra-protein contacts, so this is, so if you're looking at U to F in ubiquitin, but when you have beta 1 present, again 97. So this is folding, meaning even when the beta 1 is present, it doesn't seem to perturb the folding pathway of ubiquitin itself. It does exactly what it's doing without the peptide. But if you add the peptide, the way you seem to go to the beta, the peptide folded state is the peptide seems to come and stick to beta 5 a lot. And when it sticks to beta 5, essentially those contacts are formed early, and then every so often the entire protein folds and it seems to be able to displace beta 1. So that's what we are seeing here. So a large percentage of the first forming contacts are actually beta 1, beta 5. So the beta 1 cell peptide does not follow this native folding route while inserting. So what happens in beta 5? Again, two sets of contacts, beta 1, beta 5 and beta 3, beta 5. But now here beta 3, beta 5 is not an immediate, meaning they're not immediately connected to each other. There's like a long loop between them, which means beta 3 actually remains accessible sort of throughout simulations. And so as you expect, oh, okay, I will skip the simulations. As I said, they're mostly there for so here, so if you look at the beta 3, beta 5, the way beta 3, beta 5 inserts, it essentially inserts more or less exactly like it would in the wild type. So beta 5 goes and sticks to beta 3, and it sticks easily enough. And once it sticks to beta 3, it just gets pulled along. So in some sense, this is it modifying folding? It seems to be taken along for the ride rather than modifying folding. So as the protein folds, this one, if it is sticking, it just goes along and stays stuck. So that's what we seem to be seeing in the case of beta 5. And so beta 5 self-peptide follows this native folding route while inserting. So essentially, okay, so why, so I think the whole point here is that if you have a non-local set of contacts, which is like beta 1, beta 5, then they can outcompete the, meaning the peptide protein contacts can outcompete the protein contacts. And so they can, I mean, you can sort of drive them to form earlier than intra-protein contacts. And so that can sort of then, but it's not clear it always nucleates folding, but maybe it could at some point. And while if you have, so here are the intra beta 1, beta 2 contacts. So there they always form more because it's very difficult to outcompete them with sort of a peptide which is on the outside, even when you have high amounts. So the non-nucleus derived segments can insert actually in some cases. And usually they are not the folding nuclei, mostly because they have sort of far away interactions. So it's sort of, they're not local. Self-peptides need not follow the native route to insertion. And again, the lack of polymer connection between the self-peptide and the protein allows non-local interpeptide protein native contacts to form in the unfolded state, which they may not be able to form in the protein itself. So insertion via an alternative. So this is a bit like alternative folding pathways in circular permutants, because when you make a circular permutant, you're making some contacts which were non-local, and then you can drive the folding pathway to go like that. So that's what this, I mean, in this case, the cell peptide is doing. So, so I had like a slide about, these folding modulating cell peptides. So I've just deleted this one thing, but everything else sort of remains the same from our sort of ubiquitin work. So a big thank you to Sudipta because of that conversation, and Ravi, I guess, because he said, okay, go talk to Shachi, because now this has sort of become very interesting to us, and we are looking at other proteins and figuring out what is happening. So as a folding, I mean, I sort of coming from a folding group, this is all, this is interesting to me, just even from a very basic protein folding perspective, which making me think in ways which I'd never thought of before. So, and a thank you to Arkadeep, who's, as I said, I drive him nuts every so often with trying to do many different controls, but he's been a good sport so far. He should be graduating maybe in the next year or so. Anyway, thank you. Oh, I also hope a few more interesting things will come up together. I have these 4 papers to compete with. I have only the one.
Okay, thanks, Sachi, for a very nice and
Sorry, I took
insightful
over.
talk. So I think we'll go to that next speaker directly.
Yes,
Can-
absolutely.
So, Shachi, very nice that non-nuclei peptides can insert. The experiment has gone to the other next step, where we're asking what happens to the native part, because you showed that it doesn't fall apart, the external cell peptide. The interaction with the native part, which is hanging out, basically, in some cases, it will be interacting with the protein in a way that if the protein, let's say, is an enzyme or ubiquitin, which grabs something, the potential for it to change its action. So basically, we're going to protein silencing now. So to look at that, and is it forming contacts with the active site of the protein? That this is the kind of thing that will be lovely to see, because each peptide gets caught is a potential drug, because if it can silence the protein. So it's very interesting, really.
Just follow up to this comment is that in main protease work, essentially you have 2 domains, and these 2 domains are connected. And if the linker is not tight, they know from mutations per linker that if you you sort of make mutations per linker, the activity which is in this domain, it goes away if the linker length changes, right? And actually the peptide insertion brings out this extra flap, right? Because that's at the between the thing, and so we are sort of hypothesizing that this will actually work to kill the activity of this because of the change in the linker, because of this flap coming. But you are sort of taking it elsewhere.
Yeah.
But the flap is
Different
important.
proteins,
Yeah.
etc.
Yeah.
This question will always have to be solved. A, does it insert? B, if it inserts its own part,
Yeah.
whether it's interacting with its the active region, so active site, kill the active. That
Yeah.
will be always, this one will come.
Yeah.
Will come.
Yes.
Thank you.
Thank you.
Okay, so next speaker is Devashish. No problem.
giving me the opportunity to present in this, special occasion. And basically, we work on two different fundamental problems. In one is understanding the mechanism of vesicular secretion from cell, and another is understanding the protein quality control mechanism. And in both the projects, we have done collaboration with Sudipta. We actually got lots of benefit from Sudipta being around. Now, but before going into the scientific thing, I want to tell you, kind of a small kind of story sort of thing. So when I joined, after a couple of months, I joined in TIFR. I met Sudipta, and Sudipta asked me, "So what do you work on?" Okay, so we had this conversation in West Canteen, and I told that, okay, so we work on the snare protein, we work on these, membrane fusion, all these things, vesicular secretion. And then then he listened everything. And then after, say, a couple of weeks or, couple of months, then I got a message from Sudipta, so we need to sit. Okay, so we went, and then we sat with Sudipta, with students. And he said that, he wants to actually test the effect of the serotonin on this snare complex assembly and all other different things. Now that may be very trivial to, many of you, but it was very, very, kind of a confidence boosting for at least to me, because being junior most colleague, person like Sudipta is coming and telling me to test it, because at that time we were at the stage of just setting up the lab. Couple of assays are kind of started working, so I didn't even know that these things will work or not. It was really, really very, and then thanks Sudipta for all other things apart. But this is really very, and then all this we did. We got something. And the effect of serotonin on snare complex assembly, we are still trying to understand what is that mean. But I will not talk about that. I'll talk about the other project where we are currently working on it, and then it's kind of a very interesting thing that we are getting. And again, a lot of, probably a lot of things that wouldn't have been possible if we wouldn't have been around. So this project is about how, essentially the protein folding, and trying to understand the protein folding inside the cell. Now, when I talk about folding, for me is a very generic term. The reason is I work with snares. Snares are essentially intrinsically disordered proteins. So there are two different proteins coming together and forms a 4-helix bundle structure. That's also a folding, right? We call that a snare folding. So for us, folding means essentially the functional activity gain of the protein for now. That's, I think, is very important for the living cell. So how, and the broad question that we are asking is, once a protein is synthesized on the ribosome, at what point it starts to attain its functional conformation? That's kind of the thing that we are trying to understand in this project. And our focus is essentially here, where the protein comes out of the ribosome and either it folds or gets misfolded. And particularly, we are trying to understand that once that the protein conformation that we call as a functional protein, how close it is with respect to the protein that is just being fully synthesized on the ribosome, and how comparable these two structures are. Those kind of questions that we are actually asking currently in this project. And these are all the students that started with Shulekha almost 5 years back, and then Mayank took over, and these are the PhD students in PhD students who are doing it. But Dev Shankar, I have to mention, is Sudipta's student, a very talented student. Without him, it wouldn't have been possible. What kind of couple of things that we are actually getting currently. Okay, so now it is not really new that at least now that people are appreciating ribosome can have a role in protein folding. Unlike when I did my PhD, I also did my PhD on similar kind of topic long back. At that time, it was not are indicator of that. But what they have done is they used very interesting technique, including in a single molecule resolution. And what they have established is that, or shown very nicely, that different folds of the protein, how they stabilize on the ribosome. Now, what is really not known is that whether these different folds engage together and forms a functional protein, and if it does so, at what point it starts to happen. And that is, I think, very relevant in terms of in the cellular physiology, if you want to understand the cellular physiology well. And that is exactly the question that we are asking. Now, I have to a little more, background in there, and I'll give here is that this is the ribosomal structure. This is a cryo-electron microscope structure where you have a nascent protein present inside the ribosome. And now this is the cartoon that I drew. Believe me, the remaining structure is real. So the red one is essentially the nascent polypeptide. So this is the site of the amino acid polymerization within the ribosome, where the what you call it as a peptidyl transfer center. And and then after the amino acid polymerizes, the nascent polypeptide comes out of the peptide exit tunnel, which its length is around 100 angstrom. So it at any given point of time of synthesis, around 30 to 40 amino acid stays within that tunnel, mostly in its unfolded conformation. Or maximum it can attain its alpha helical conformation, not more than that. This kind of information we know now. Okay. Oh, it went so fast. Okay. So now we are talking about a scenario like this, where essentially out the N terminus of it, nothing prevents it to start forming the tertiary structure while its C terminal bound to PTC and its amino acid polymerization is still going on. So that's a kind of a scenario that emerges from what we know so far for the ribosomal structure and all these things, right? So and we are particularly interested in this stage where you have a full-length polypeptide that is synthesized and stuck last at the beside tRNA on the ribosome, and from there it has to come out, and then we'll start forming its functional form. So these are and how comparable these two structures are, and what ribosome perhaps is doing into these kind of structures and so on. Okay, so how we do it? So we are using currently two test proteins to start with. One is superfolder GFP and another is luciferase. And what I'm going to show you today, a couple of data sets that I'll show you today is on the superfolder GFP. And the reason, please don't ask me why is superfolder GFP. There are a lot of physiology, because it's just the reason for choosing this is it's very easy to trace the functionality, as simple as it is. For superfolder is the chromophore maturation, you get a fluorescence, that is what you call it as the functional formation. Or luciferase, you put the substrate, it will light up, you will have the functionality. That's the main reason to use these proteins. Okay, so now so what we do, we essentially do in vitro translation in the lab, and in the in vitro translation we don't have release and recycling factor. So what really happens is during the translation, you have initiation factors, elongation factors. What they do is it's a really energy consuming process, right? It takes up lots of GTP. So to synthesize the whole protein. So after that, so at the end of the synthesis, these release and recycling factors cleave off the polypeptide from the tRNA so that it now comes out of the ribosome. So we don't have this in the reaction. So hence, you actually end up in this form where the full-length polypeptide is stuck at the last beside tRNA on the ribosome. But most important thing is you do ultracentrifugation through sucroscussion to take only this thing out and throw all the other things out. This is a very important step, at least for us. And then that is our termination complex and starting material for our all the study that we do. So and then you have this here, and this is a proof that you have superfolder. This is the immunoblot showing the superfolder GFP is present when you have these are ribosomal protein showing the as a proof of fact. So then we took that termination complex and just wanted to see the do what happens when you now add release factors or puromycin to see if you see kind of a chromophore maturation activity again of the superfolded GFP. And this is the black trace. If you see, it slowly increases with time, as we see. And red trace is when you don't add that essentially. And the blue one is when you do a chromophore mutation of superfolded GFP. Now, an important thing, and weird enough, we got is a zero. If you just look at the 0 time point value, is we got a huge amount of fluorescence in the 0 time point. We didn't know what it is, and we got it like n number of times we are doing it. We are getting the same thing with the lucifers also. Like at the 0 time point, we're getting huge amount of luminescence as well. We don't know what is that, and at least till now, initially when we started this. And we had an indication that we did some release assay with some biochem. I'm not going too much detail. It's a very long story, so I'll just tell you a couple of data from there. And we had an indication that perhaps somehow or we rather hazard perhaps some of GFP is released from the ribosome, and that's how you are actually getting this inactivity, right? That's kind of a first thing that comes to your mind. And obviously, we wanted to check that. And we wanted to check that. Yeah, take it. We wanted to speed up. We wanted to check that. And obviously, there's no other person than going to Sudipta for that purpose. So we have this thing, what we do with it. And here I will, this is, everybody knows it. I just got this picture from Dev Shankar, your FCS, setup. So why it is relevant in this respect is because you're actually talking about ribosome bound GFP, which is a mega Dalton complex. And if a GFP releases, it's a killer Dalton complex. All you have to do is to, if you see the separation, you have to do a diffusion of these two molecules, and you kind of get an idea of that. And that's what that's why we thought it's a kind of a very good technique that Sudipta described, and we used it. And this is one of the trace that we got from that machine that in Sudipta's lab. The red one is just the FITC, and the black one is essentially the termination complex. We did not add any external fluorophore to it. You are still getting this nice curve. And then then what we did is we fitted with, we actually learned all these things from Sudipta. We fitted with different equations, and then we actually quantified the diameter of the particle, large particle, and that perfectly matched with the known ribosome diameter and not with the superfolded GFP diameter until you add release or recycling factor and release it. So that was very important thing, and that tells you that essentially we are talking about either of these two scenarios. Either your protein is in the canonical form, is bound to PTC and somehow gets matured, or it is somehow released but somehow peripherally attached to ribosome. It's also possible, and then it is giving fluorescence, right? So that's another thing we tested with, and I'll finish in quickly. So then we did basically one of the best way to test is just adding puromycin, because what puromycin does is it will only go through the PTC. It will not act without PTC. Wherever you add puromycin, it has to act through PTC. And not only that, it remains bound to the C terminus of the nascent polypeptide, because that's how it takes over from the canonical tRNA. So we did that, and as you can see that it is actually reactive to puromycin as well. So that means it boils down to the fact that the nascent polypeptide is in these GFP was actually in this form, and showing the chromophore maturation. Now then we wanted to actually check how comparable these two structures are. This is very hard to do, and we just started to chase it. One of the things we thought is why don't we do this lifetime measurements again. Sudipta explained everything to us, and we did that, and we have much better data. So just here I'm just showing this raw data. If you can, these are free GFP and these are the termination complex GFP. It's more or less very close to each other, at least what we get from the raw trace. We have to do a lot of other fitting and all these things that we are doing now to get much finer information. But the ultimate the conclusion doesn't change. Essentially, it tells you that these are more or less the same kind of a conformation. Now, the question is then how it is happening. Because if you think about the GFP structure, in this conformation, you are actually talking about almost 30 amino acids inside the tunnel in its unfolded conformation. That means you're talking about one entire strand out inside the tunnel. But how it is possible that does that mean that is not required for GFP? You cannot even delete, you are talking about 30 amino acids, you cannot even delete 14 amino acids because we just deleted 14 amino acids from C terminus. You have the protein, GFP is here forming, but it's just non-fluorescent. So forget about 30, you cannot even delete 30. So what we believe, and we have done a lot of experiment that actually, suggest us is that the dwelling time on the ribosome is very critical. I just quickly mentioned we have a C-terminal deletion of GFP, which is active but showing activity on the ribosome, but which is off the ribosome inactive, non-functional. So and a lot of other experiment, but it also suggests that perhaps internal environment of ribosome has a role in it, because we got some antibiotics which are known for translation elongation, that act on the translation elongation. Here, no translation is happening anymore. So, but one of them is actually decreasing the functional activity of superfolded GP when you treat and add it here, but not the other antibiotic. We have done some cell waste assay as well. So, as I said, it's a long story. I'm trying to wrapping it up. I don't have time too much, but I'll kind of quickly wrap up that these are essentially those kind of the questions that we are asking here. I'm kind of skipping all this because it will take a lot of time to explain. But I just quickly said that there are of course one thing is that the proteins that have defined structure, but there are also proteins which doesn't have, like alpha sonic, which is known to intrinsically disorder. So what happens to those proteins? We're also working on that. We are actually halting it in the same stage and trying to ask how that and then the oligomerization or monomers formation and all these things, whether that is a concentration dependent and all these things. So those kind of things we're actually working on. So I'll just stop here, and I must say that of course I am thankful to all my students, my TIFR colleagues and funding sources, but I must say thank you very much, Sudipta, for being there, and I will still keep bugging you, and then without you, many of these things couldn't have been possible. So thank you very much. And yes.
Yeah, this is beautiful work. I hope it will publish soon. But very little is known at what the partial folding intermediates are just at is coming out of the tunnel. So now the question that I have is, since you have chosen GFP, there is chemistry associated with the formation of the chromophore.
Yeah.
Now, the time scale of the chemistry is very, very important to notice here. So when you cut those 14 amino acid, right? Do you still have an intact chromophore?
Yes. Chromophore is in the N-terminus.
Chromophore is in the N-terminus completely, right? So you don't have any requirement from the C-terminus, right? In principle.
When it is on the ribosome. When it is on the ribosome, not off the ribosome. So what we are saying is,
No. You have not. You don't have a requirement for bringing an amino acid which is part of the chromophore. The chromophore is all built at the N-terminus, correct?
You don't need that.
Yes. So the thing is, the only idea would be, is the chromophore protected from quenching? Okay. In certain cases, it might be protected, and you see the emission still in that as it is coming out. But when you have cut these things, then you probably have a much more unstructured.
Possible.
That's important to characterize. The lifetime measurements can tell you those.
Absolutely. Yes. Thank you. Those kind of things, has to be done.
But I think the similarity I said that your lifetime was showing that you lifetime.
That's full length protein.
No, that's the full length protein. But the point is that when it is on the ribosome and off the ribosome, that looking at only the lifetime, can you really tell that the structures are same? That's exactly similar to what JD has said.
It's just
you are deleting some part,
and
probably when it's off the ribosome, it might not have that entire structure on the ribosome, might not have the full structure, but because the chromophore is far away from that part, that's the reason probably you are getting the similar lifetime, isn't it?
No, but if you delete, say, if you delete 30 amino acid, that doesn't happen. If you delete 14 amino acid and do the experiment, you do have the same thing, same observation as you get with the full length protein, that on the ribosome, 204 deletion, 14 amino acid deletion, and the full length protein has a similar kind of lifetime.
Okay.
But when you delete more than 14, 30 amino acid, that doesn't happen.
So that means that's typically the limiting bar, meaning beyond which probably it's affecting the structure, is it?
Absolutely. You are right on there. So those kind of things we are doing, and we are kind of those kind of things we are actually
So I was also wondering that what is that, like, suppose that 30 residues that are inside the tunnel is not important for a chromophore purpose. It's just that it interaction with the ribosome is more important for the
well, while it is on the ribosome, that's what it looks like. Because what I believe, at least currently, is that you have a strand, right, that is totally inside the ribosome. So that strand will go and give stability to the remaining structure, hence you get the functional final folded. While it is on the ribosome providing similar kind of stability to the remaining structure that otherwise region will go and provide to the remaining structure. That's kind of what I think, but I might be wrong.
Hi.
Yes.
So very nice. So not we, but generally the idea has been that you want to leave water out of this barrel, right? So there are, from what I understand, other versions of GFP, and I think superfolder doesn't have it. They have these 3 prolines which go from trans to cis, which basically locks this barrel, the helix in place, and keeps the water out, and that is preventing the chromophore from not getting quenched. And so it seems almost like you should look somewhere for an extra, and it's known that these things absorb on the meaning many proteins, while they're coming out, they're stuck onto the ribosome like that.
Doesn't look
what?
Actually, water is needed for function. It's a proton transfer reaction. So there's one single molecule right in the chromophore.
No, but they've made the chromophore, and if you put it in solution, it doesn't work.
Extraneous water may be an important thing, but
fine. Yeah, but for the most part, you have to exclude water from this.
So for ribosome,
meaning it's known that things as it's getting pulled out, it sort of sticks to the tunnel like that.
So that's exactly where this experiment, whether it is bound to PTC or not bound to PTC, is very important. Hence, we have done FCS and we have done other experiment also. I didn't tell. So all other biochemical experiments that suggest that it is. So if you notice, there are 2 populations. I didn't want to go into too much detail. So I don't know what is happening here. Okay, so there are 2 populations essentially. One is inactive population, for which when you add pyromycin, you are getting a increase activity gain, and you have a already termination complex which is fluorescent, that is active population. Now we do in vitro translation for 90 minutes. When you reduce the termination time to 15 minutes, and we trace the time from 15 to 90 minutes, and then Siddharth quantified active bound versus active bound population on the ribosome, that actually increases with the in vitro translation time, and the reverse, like inactive population, decreases. So those kind of things has been done, and so far what we believe is that as long as it is interacting with the ribosome, it is providing, some kind of a support to it. I don't know how. Yeah. Yeah, exactly.
Inside of the ribosome and not water outside.
No, exactly. Yeah, exactly. But the question is, people have also reported whether the surface or internal environment, because there are reports. An MR group has. So what our in antibiotic data suggests, most likely internal environment is important, and also a lot of other things. It's not just surface. Internal environment is important. Otherwise, antibiotic will go and bind there. So we have done some experiment which we are still doing, which doesn't suggest, we suggest is not really going to and binding the protein per se, that antibiotic and reducing the activity, because it's a metastable conformation. It can go and bind to the protein also, right? So it's most likely not doing that, and actually going and interacting with its canonical ribosome interacting site, which is in the.
Yeah. Of course, I've been part of these experiments, are very interesting, but it's still true that the only explanation that seems to be possible is almost too fantastic to be true. That it's like the part of the ribosome is acting like a self-peptide or something, finishing the folding. I mean, that ribosome is not even a protein. I mean, it has some proteins in it, sure. It seems like it shouldn't be happening. So it's really something that is very perplexing to me. I don't know what Ravi thinks about it.
So if you
part of the ribosome acting as a patch for a missing part of the peptide in GFP, where everything has to be a proper beta barrel because the geometry has to be right, and that's why it gets quenched. And it just seems nearly impossible.
So the one thing I just mention here. So nascent polypeptide interaction with the ribosomal interior is not new, because say those proteins which targeted to the endoplasmic reticulum, how they do it? They are otherwise started with on this cytoplasmic ribosome, right? So they have this second sequence that is stuck in the ribosomal RNA inside the ribosome, and then translation stops. That means sequence recognition on the ribosomal RNA has something to do with allosterically, and there are papers on Alexander Mankin's group, has something to do with the peptide transfer center. And then the intercomplex comes into the endoplasmic reticulum, reinitiates. Both the things require the peptides recognition with the tunnel and its interaction with the PT center. So there are a lot of complicated things. Exactly, and more interestingly, Lucifer is also Lucy. Don't.
Yeah. So it's very exciting. I have a comment. Or can there be more than one conformation for GFP which can fluoresce?
Possible. I don't know. I can't tell you the answer unless you do the cryo.
So in that case, this problem is not there. No, this has to be too fantastic.
The chromophore has to form somehow. Otherwise,
He has something to say.
Maybe I think there's something to learn from your BAM experience, actually, right? In terms of folding beta barrels. The protein itself, actually, or one has to look at the surface, essentially, whether there is a template that is already there, actually. So my question here is, this is a beta barrel. If you did the same thing for something which was helical, now I don't know whether there is such a.
No, it also has the similar kind of beta.
So if there is a template which actually allows you actually to form like beta barrels, for example, that could act as a finishing component.
Yeah.
It could be generic actually, but one has to study the surface there.
Yeah, this is the starting. The only thing that we are trying to trace, or whose activity we can measure in very kind of reliable, like a fast time scale. That's all we are kind of. Oh, yeah.
Okay, so with that, we will close the session now. And the questions can continue at lunchtime also.
Sure.
And so let me thank all the speakers of this session.
Okay, just an announcement. We will start at 2:15. Lunch is being served in West Canteen. Please join us. And I thank a wonderful morning session from all the 7 speakers. And it's so gratifying that everybody came in person and delivered so nicely and had so much affectionate words for Sudipta. So thank you very much. Good. Yeah. So welcome back after a nice lunch, and I hope some of you had a chance to go around a little bit to the seaside back again. Somebody did go back to some lab. So, so I welcome Senthil. Senthil actually, of course, finished his PhD with Sudipto in 2008, roughly at the over. Oh, oh, okay, masters. Sorry, sorry. My bad. Masters in 2008. Something at the same time with Kanchan was also there in the lab. And now, of course, he's an independent faculty at Monash. So doing beautiful super resolution, lattice sheet microscopy and other kinds of, which he will teach in IIT Bombay tomorrow. So Senthil, the floor is all yours.
Thank you, JD, for organizing this trip. It's very honorable and pleasure to do this for you. I think I was one of the 3 master students from biology who did a master's in Sudipto's lab. I was lucky to do that. And I think that was a foresight from and vision from Sudipto and Veronica at that time. I don't think Sudipto was not in my interview panel, but I remember Veronica asking me a few biology questions, and I have a chemistry degree. I totally failed, and they all looked at each other and nodded, and I think they sent me to Sudipto's lab. And then when I started to Sudipto's lab, his lab was in the basement there. And we moved all the optics and stuff to the 3rd floor lab there. And then I remembered that nod when they all looked at each other, and I thought maybe they looked at my size and stuff, and they thought this guy's going to be useful for Sudipto. His lab is moving, right? But then I learned a lot in Sudipto's lab. My lab still now looks like Sudipto's lab, where you could just get your optics parts and try out new things. And I do a lot of light sheet now, but I must tell you that the first light sheet I ever built with Himanish Ghosh from Vidita's lab was in Sudipto's lab. We just imaged some fluorescent dumped in tissue paper, and we imaged the tissue paper scanning with hand. So we just rolled the thing and scanned with hand and tested that, okay, it works very well. And then, now we're building more sophisticated light sheets. Anyway, to go on with the session, our first talk is from Mr. Shafi Mohammed from Hallmark. Please.
Hi, good evening. So I am here. So my name is Mohammed Shafi. I'm from Hallmark Optomechatronics, Kochi. So I am going through some of our spectroscopic products, which is actually our start from the 2006 onwards. I joined in 2006. Okay. This is our Hallmark product category. You can see we are manufacturing more than 4,500 plus products in these categories: microscope and imaging instruments, optical measuring instrument, spectroscopy, analytical instruments, lab equipments, physics lab instruments, breadboards and tabletops, optomechanics, optics, linear and rotation stage, motorized linear and rotation stage, and laboratory automation products. Our products, actually, we are internationally, we are selling these products. We can see we are sold this instrument all around the world to major institute in USA, and we are selling these products as a OEM in USA and Canada. We might hear about the MTA Corporation, so we are selling with their name only. So our first product was in the spectroscopy is actually spectrometer goniometer. And the second year in 2008, actually we got an inquiry of monochromator from C.K. Jayashankar sir. And we did a 500 mm focal length Cerny-Turner monochromator. This was the monochromator. And then we moved to the standard monochromator, which is have focal length of 300 mm and 400 mm. Then we developed the multi-channel CCD-based scanning spectrometers. The After that development, we did some motorized high precision theta to theta goniometer stage. Then we developed a multi-channel spectrometer and monochromator, which the development project was from General Fusion, this is from Canada. He's working with fusion reactor and all. So we developed a high resolution spectrometer. The focal length is 500 mm. And we achieved the spectral resolution of 0.01 nanometer with this model. Actually, this thing's the development of fluorescent correlation spectrometer, which is started in the 2011. I was here and I got the training from the Sudipta Maiti sir. I would say because at that time I don't have any idea about the confocal system because at that time I don't have the experience, but I got a very good experience from him how to do this confocal thing. This was our first confocal fluorescence spectrometer. This was the item. You can see the software is supplied by TIFR only. Later that year, we developed a line CCD camera. This is necessary for the spectrometer. If you see any small spectrometer or higher spectrometer, we need a camera with the length at least 25 to 30 mm. This actually we are buying from Mitex. You may familiar with that name. So they are supplying this line CCD camera of 90,000 rupees at that time. Then we developed this board our own. Now this board cost, the total cost of the instrument is less than 10,000 only. And then we moved to the this CD. This is actually prism spectrometer, which is useful for physics lab instrument because mostly the Hartmann constant, those things are calculated with this prism only. So we put our sensor in this spectrometer. Later, we developed in 2015, we have got one inquiry from Aliga Gare, which is IIT Guwahati. So development requirement was develop a UV visible confocal Raman spectrometer. So this was the first attempt with the confocal technique. So we achieved a good resolution at that time, but compared to now, the resolution and the sensitivity was less only. In this unit, actually, we incorporated our Toshiba detector as well as the PMT, which is from Hamamatsu. It's a R2949 PMT that is also used. Then we developed a small spectrometer. This is a USB compact CCD spectrometer, which uses the same sensor. We developed two type of spectrometer, one with the concave grating and another with the Cerny-Turner configuration, as you've seen in the monochromator. Later, we developed a mini monochromator because in most lab, the space is very constrained. So we have developed a small compact mini monochromator along with the light source. It can work from the 185 nanometer to 3300 nanometer. And we got an interesting requirement from Jairam sir, which is a director of NAR, National Atmospheric Research Laboratory. So he asked to develop a nano satellite polarization spectrometer. We want to put the spectrometer in air balloon for the initial study and all. So we have developed one spectrometer with a range of 350 to 900 nanometer. Which also we also incorporated a camera unit, so we can see the subject, and you can select the desired location. So the spectrum it can collect automatically at that point spectrum with the software. This is our second model because that was for fluorescent correlation spectrometer only. Here, actually, with the help of Sudipta Maiti sir, we did a cross correlation technique. So this was a successful model because we did a lot of changes. As you can see, the hardware, in 2011 model, actually we use a manual version only. All the fiber adjustments, those things are manual only. Here we put a motorized mechanism in the two because we don't need to open the system. From the software, we can adjust the focal plane and the fiber positioning. And we also can see the software layout, which is which we have developed in the C#. It has some special feature also we incorporated just for the focal plane scanning, those things. This is the inside layout. We can see this is the motorized fiber selection. We have 2 channels. This for FCCS, those we have 2 channels. And we can hold up to 2-3 laser here. This structure is designed like that only. In 2022, we got a requirement from the IPR in order to develop a high resolution spectrometer for the plasma, which is actually generated in a fusion reactor. They are working with the fusion, Aditya Tokamak, it's called. And their requirement was to develop a 0.02 nanometer spectrometer, just to want to study the Doppler effect during the reaction. So we have achieved a 0.017 nanometer resolution. This is the spectrometer. They published on paper with this. You can see this is their paper. You can see in their website as well. This is our new development. This is our 5th generation model of the Raman micro since the 2015. So we have different models. This is the latest model confocal micro Raman spectrometer, which uses the motorized microscope along with the spectrometer system. This is the layout. As you can see, this is the motorized microscope, which uses a motorized XY scanning and a motorized turret and motorized filter selection. And this is our spectrometer, which uses 400 mm focal length optics, the Turner configuration. This is the laser selection system. We can hold up to 3 numbers of laser inside. This is the one video, which is sure. It's okay. Sorry. I just want to show this movement and all. That's why. This we supplied to the IIT Delhi, IIT Madras, Cochin University, and Brunei Dar es Salaam University, and one Indonesian university as well. This is a motorized selection. The objective is a motorized. And later we introduced this inverted configuration. In this model, the light collection is inverted way.
Series inverted confocal micro-Raman spectrometer operators an automated infinity confocal microscope featuring a high-resolution spectrometer and a precise laser system. This configuration allows researchers to conduct in-depth chemical analyses with outstanding spatial resolution and spectral precision.
And we also did this kind of work. The UV Raman lidar, that is for NARL, and spectroscopic ellipsometer, reflectometer, and optical rotation measurement unit, and oral cancer detection spectrometer, and theta to theta for thin film study, and diffused reflectance spectrometer, spectroscopic refractometer, and a hyperspectral camera for NIR, and PL spectrometer, fluorescent spectrometer, and we also have a different range of quantum efficiency and other spectral response measurement device. So our main core is to customize the product. If you have any idea and if you want to develop any product, you can communicate with us. We can, because we have in-house electronics, mechanical, optics, and software team, including the fabrication, design, everything is in-house only. So we can easily customize any product and actually I didn't say thanks to Sudipta sir as well as Das sir actually, because I cannot speak fluently in English actually. I'm sorry. So I thought I would like to share some more details about Sudipta because I have a lot of experience because I heard this name from the 2008 onwards. In 2011 only I meet Sudipta here. So I did a great experience from him and also looking for in future more collaboration. I don't know how he is planning his career after his, where you want, means where are you planning after this TIFR?
We'll talk about it later, but thank you very much for all the
Thanks.
details. Right. Thank you, Shafi. Right. One of the great things about Sudipta's lab was coming from a biology department, you learn cell culture from a physicist. And along the great lines of these people, one of the first ones is biology, who will be giving a talk now. About your
Okay, thanks. All right, good afternoon. I'm starting with three constraints here, right? Number one, everybody wants to go and have tea. And if we all had just a good stomach full of lunch, so we'll be sleepy, including myself. So I want to make sure that I don't sleep in my own talk, but it's such a wonderful feeling, right? It just, I can't believe myself standing here when I came for the interview in 1998. I'll be giving a talk thanking my mentor in this stage, right? Is amazing. The journey has been wonderful, just to say the least. Okay, I can keep going on and on and on. Okay, I was told I had to give a few inspirations. Few is the key, and then talk about my own research and tell how it is been inspirational. To add to that, see, as you would have heard from everybody from the morning to evening, Sudipta's work, a lot of it has to come from serotonin, neurotransmitters, building optics, beta amyloid, blah, blah. Except for the optics part, I don't do anything in the lab right now, but you will see it's true. There has not been a single day that has passed by in my lab where I have not quoted Sudipta. Okay, is just an amazing person. So that I'm going to dedicate just one slide. After that, I'm going to come to my talk. Okay, so inspiration, right? This is the effect of this inspiration is this. I don't think this of course is my lab at IISc. This would not have happened if not for Sudipta. I can definitely vouch for that. So with that, I borrow words from Winston Churchill and modify a little bit. Never was so much owed by so many to an individual. It's really true. And probably every single student would feel the same way. I'm talking for all of them, but definitely this is really heartfelt. And with that, I want to take many things that have happened as a guidelines. I'm going to talk about 3 guidelines that I still today use and tell to my students. Number 1, develop quantitative measures. Balaji, you've been hearing a lot of descriptive. It's like one of the benefits of the first student is that you get a lot of time with the mentor, right? Same with Sudipta. We used to have breakfast, have lunch, do night outs, all sorts of things. And much of my PhD was on this. In fact, the penultimate day of my PhD thesis defense, I don't know if you remember, we were just walking back to the hostel, doubting, have we measured the serotonin properly or not? That's really how our discussions were, and it was very good. So you would see in a bit, I do completely different things, but this spirit has not died down. At least I would like to believe that's not died down. I'll illustrate with few examples where we have, I think we have stood by that through spirit. Build your own apparatus, build your own experiment setup to push the limits of technology, not just because it's cheap. I remember one of his quotes. If you can build a Ferrari cheap, it's not to your benefit. Tomorrow, a Chinese person will come and beat you. But if you tell me the car can look like a bullock cart, I don't care. But if you tell me it can beat the Ferrari by 0.1 of your technical proficiency, you are the winner. So that's why we build. I still think that's why we want to build. Of course, it's economical and all that, but that's secondary. Third, strive for analytical description. The beauty of science is in writing down things and then being able to see and understand what it is. So I'm going to tell you the usefulness of these 3 in our research, in my research. Okay. The lab, the neurodynamics lab, we are interested in understanding memory, particularly of one kind, which is called as the declarative memory. The memories that you would go back from here of this event, right? These lifetime events encode the information in your brain, and those memories are called declarative memories. They have a particular character. If you step out, somebody asks you, hey, who was the third speaker, fourth speaker, you would be able to tell. But a year from now, somebody asks you, then you may not be able to tell. They tend to generalize. And we are interested in understanding this very process. Clearly, you can see there are very many aspects to it. Today, I'm going to pick the aspect of how the brain tells apart memories that are very closely related. Okay, so what do I mean by this? Now, let's take an example here. The example is if you encounter this person walking along the park, walking her dog along the park, what you see is that this picture gets encoded. When I say encoded, there is a defined pattern of neuronal activity in a small ensemble of ensemble of neurons in a small region in the brain. And you can say that, okay, when you activate these ensembles again, you get this same feeling, right? That's kind of a very simplified version of what you call it as a neural code, and what you can think of that as memory, right? I'm talking about a particular view here, but that's okay. We'll see what the trouble is and how we are trying to overcome that. Next day, or little later, you see something here, right? With what you can actually say that there are some similarities, right? Apart from the dog being the same, there are some similarities, not just in terms of exact same features, but then the conceptual similarity too. There is a walking, there is a path, so on and so forth. And that takes a representation in this yellow subset of neurons. Both of them have some overlap. In the field, when you talk about a memory that is related, they tend to think, or one tend to think, when there is a higher overlap, there is a in the ensemble that reflects the higher similarity between the events that you have seen. Okay. This comes into a problem. The problem is as follows. Okay, this is the dominant view. Okay, even now, I mean, even though it's 2021, 2024, if you ask the view hasn't changed much. The problem is this. This kind of encoding, we call it as a symmetric encoding. That is, once you have encoded this memory and this memory, you do something to this, depending on the proportionality of the overlap, okay, the effect that you erasing this memory or removing that memory will have on that will be determined, right? Like, for example, if there is a considerable overlap, okay, let's take two events, event 1, event 2, and then you can measure those overlap. If this overlap is high, or overlap is low or high, depending on that, you can say that the events are bound or integrated, right? This is completely independent, while these are completely bound. Together with it, implicitly what we are telling is also that when you want to identify a particular event, that identity is kind of lost, right? While the binding is kind of increasing in this as a function of overlap between two events, the identity goes exactly the opposite direction. Okay, so to see if it is, this is what is actually represented in the brain, you would like to actually look at these very bubbles, right, that we have actually talked about, right? These very simple balls and their bars, how they are, and so on. So when we started, we built our microscopes, multiphoton microscope, to be able to peep inside the mice's brain, and somehow, all right, somehow, if you could actually identify the neurons that are actually taking part in this encoding, we may be able to start to answer this question. You quantify what are the similarities from outside, you quantify the neuronal ensemble that is representing it, then first order of business is to see if there is a correlation. If not, what are the rules that defies that, right? So we will do that with the mice. And first thing is to tell you, how do we create memories in mice? Very simple. Probably you all know, but just to get all of us into the same page, we take the mice, put them into a box, provide them a mild foot shock. Nobody likes the shock. Mice also doesn't like the shock. The next day you come and take the mice and put them back into the same box. They express the fear of the shock. I don't have to present the shock. They express the fear of the shock because they can understand this box means I'm going to get the shock. The box predicts the shock. So it expresses a behavior of freezing, basically cessation of all movements except for breathing. Now you can change the box a little bit. Okay. So what you do is you measure the freezing. You see that it goes up for this particular context state. You change the box a little bit, the amount of freezing goes down. The freezing here is the proxy for fear. So clearly you can alter it. But the beauty is you can completely take into a different context. Context C is almost to the baseline. Well, one may argue that, okay, it's not a big deal because you have a way of modulating this context. You can quantify it, whichever, what are all the sensory modalities that you're changing, to what extent. Based on that, empirically, you can actually determine. Also, once you determine these parameters, you can quantitate by taking the sets and say that, okay, this is like half of this and this is 20% of that. But the irony is, as I just told you in the beginning, you wait for some time. All right. The same mouse that got shocked, right? I was clearly able to tell the difference between A and B. Now cannot differentiate between A and B. It's not that the mice is not having the memory, right? If it doesn't have the memory, it will be at the freezing at the baseline. There will be no fear. It's actually having the memory. It's just that it cannot tell the difference between whether it is A or B. It's not general because you can put the mice back into the C. Clearly, it can differentiate between B and C. All right. So now this is a very good way where you can actually say A and B are more related than B and C or A and C. Okay. So now you can actually take this difference, measure it as a ratio of the original fear. That's a good proxy, a good measure to measure the similarity of what you are actually doing at the initial stage. Now let's look at this at the behavioral level, right? Now let's look at the mice brain. And first is how do we know which neurons are actually taking part in memory? So we tag along a class of gene, in this case a particular gene called CFOS, but they are a class of gene called immediate early genes. They are the first responders. After the neuronal activation, the gene expression starts, but they're transient expression. So they go in, and the repressors also start in at the same time. As a result, what you see is that the expression of a GFP that is tagged along with the CFOS goes up and comes back down. This people have been using quite a bit, not the way in which we have been doing here, simply because there is no way to image in vivo in the same mice. So what they would do is they would expose the mice, a group of mice, sacrifice the brain, count the number of neurons, keep doing that, and then say, okay, how much of the neurons are there? By that, you can actually follow it. The trouble is, that's not, I mean, that's again a proxy, but here we said, okay, you can actually think about it, model it as a simple sequential reaction, write down the kinetics, solve the kinetics, look at the measure the fluorescence, it beautifully fits. No problem there at all. Bonus to this is that this is following one of the exposure. You can actually do it multiple exposures. All it takes is you have to change the equation a little bit because you know this model fits. All it takes is to include more and more of this. And you can actually get this expressions too. And now you have a way of telling which of the neurons took part in one, which of the neurons took part in two memories, so on and so forth. We can go back and ask the question, after exposing the mice, if the mice was exposed to A, how does the brain look? Exposed to B, how does the brain look? Merge it, the idea being, if they are completely individual memories, independent of each other, then the merge should be just a random chance event. Chance event, how I know it? I know the average number of neurons in here. Actually, I can estimate it here. And then I know a fraction of the neurons that are activated. F1 times F2 should be the random chance. And what we see is that the overlap is not any more than the fraction, the random chance, the product of the fractions. Suggesting at the neuronal level, if you want to try to identify which of them are actually estimating this, representing this context, probably the answer, you don't have that answer. I mean, maybe you have it, but you don't have it. The reason being, we know that A and B are different from A and C. A and C are distinct even after 30 days, but A and B are not. Adding to that, we did another experiment. This is a behavior experiment where we said, okay, let's form this context A and context B. I'm going to modify, I'm going to try to kill the fear for context A and context B, then put the animal back. So basically, I have created these two events and modified one of them and asking, first hypothesis, according to this, right? Is it symmetric? If I modify this or modify this, both of them behave the same when I test back? The answer is a big no, they don't. These are the tests for the A and B, and you can actually see they have learned very well. However, depending on which of them, are you extinguishing the second learned context or the first learned context, the answer is different when you test them. Like if the animals have learned the context B as second, and you are extinguishing that, it has some effect on A, but definitely the A is, I mean, the first memory is stronger than the B. Now look at that. I am actually extinguishing A here, right? But that extinction should not have done anything to the B, given that extinction is only so much here, right? But even this much of extinction of A is good enough to bring back the B. completely as if that they have not learned. So definitely there is an asymmetry. So then clearly the model that's been proposed in terms of neuronal overlap is not sufficient, and definitely this asymmetry cannot be explained at all. We don't see that asymmetry in the overlap. So that's definitely not possible. Then what's going on? So we explored this at two levels. One, I won't go into the detail of how exactly we arrived at. It's a pure rigorous analytical sitting down and thinking with the neuronal circuit people, where what we said is that, okay, look, there are a class of neurons. We tend to think that all the neurons are of the same type, right? There are a class of neurons which are excitatory and inhibitory. In the inhibitory, they have two different subtypes, many different subtypes. Two of them we are actually concentrating on. One is called as a parvalbumin, and another is SST. The SST neurons suppress the input to the excitatory neurons at the dendrites, while the parvalbumin neurons suppress at the cellular level. So what's happening is that if you activate the PV neuron, it will increase the amount of input that is required to excite this neuron, while on the other hand, if you activate SST also, then at the input level itself, you need to have a higher input. I mean, this looks very simple. What we said is, okay, maybe this PV is not just projecting to the soma, but if the PV were to be projecting into somatostatin, right, directly from here to here, then what you are actually doing is that you need a much lesser dendritic input to activate the somatic level. So this has been shown, this kind of inhibition is called a disinhibition. That kind of disinhibition, we can actually go ahead and show that can be very useful for fine tuning the inputs. So then we went ahead and checked it using simple chemogenetics. So what we are doing is we are actually infusing a set of designer receptors. They are responding only to the outside. There is no endogenous ligands that can bind and activate, but then the outside ligands can bind and deactivate the neurons. So we directed them to the PV neuron selectively. At first, we show through electrophysiology that it is working the way it is. And if you take a look at it, that's how it looks. These are the PV neurons, the green one, and the yellow ones are the overlap between our virus that carries this designer receptors and the PV neurons. And clearly, when we suppress this, what we find out is that you can actually suppress the specificity or the ability to differentiate between A and B in a very age-dependent manner. The key thing to note is, as a function of age, our ability to suppress through parvalbumin interneurons also goes down, completely agreeing with the idea that, okay, the specificity that we are talking about can be modulated both by the parvalbumin interneurons as well as by the, through the age of modulating the PV. We didn't, so that agrees well with what we had said. So in summary, what I would like to say is that relatedness of memory, it's dependent on the content. However, that's not dependent on population overlap. So we could not have done this, all right, if we were not able to do two things. One is be able to have an in vivo imaging thing that's going up time and again, you can come back and image it, and be able to sit down and write the gene expression profile and measure the fluorescence and show that the model fits or not fit. Third, we say that, okay, it's they are preserving by the identity, and the mechanism probably is through PV interneurons. I'm just going to take 2 minutes, it's super important, to show why the statement I made, the first statement, never the Winston Churchill statement. So I'm just going to skip this. So a true leader, a true mentor, not only inspires the first generation, right? generation after generation. Now, that's really what I meant by saying that statement. So in my lab, one of the students, we were investigating. This is, I mean, one part of the lab is doing rodent-based work, while the other is doing human-based work. For the human-based works, we used to design headgears and all that. He's from ECE background. 2 years he has been working with me, devising methods of, okay, so this kind of spectroscopic cap that you can actually do that has very, very unique features, like where people normally look at hemoglobin and all that stuff. Now, currently, he is able to extend it to measure simultaneously not just the hemoglobin, but also the cytochrome C oxidase and the glucose in the brain, while the person is actually engaged in a task. It took 2 years for me to really convince him to really work hard and do this. Sudipta comes there for a day. This was during this stage, okay? He's still making this kind of a headband. He talks to him, he volunteers, clearly, and that's Rajesh. For whatever reason, this particular picture, he was the person who was doing my webpage and all that. That day onwards, not just my lab webpage, his page, all right, has this as if like a big award. It's just so inspiring for him just to talk to him and he look at the dynamics of that person and doing this. He developed the entire project. Actually, you can actually now see while the person is engaged in a video game, this is a small kid here, you can actually see the energy consumption while the task at what point and so on and so forth. It's just, I don't know, there is no word. So I in fact asked Sudipta, you have done so much, Rahul might know this. IISc comprehensive exams are a pain. Okay, he was very, very worried. I said, I will ask Sudipta to come as an external. He was very happy. Unfortunately, Sudipta couldn't come, but that one statement, he cleared in one attempt. No, nothing at all. He is not here, but I'm not joking. I'm not exaggerating anything. It's just very magnetic. And it's not the 2 years of me not doing anything and 1 hour, probably 1 hour, maybe less than that, of him staying there was good enough for him. This is labs, our lab at very different phases, times. Some common phases will be there, but most of them changes. And the current funding is from here, and these are the people. And thank you, and thanks everyone.
I think we have time for one quick question. And if not, the memories are found very quickly, but you're looking at gene expressions that are hours long, right? Right. All right. Thank you very much, Balaji. Our next speaker is Rahul Roy from Indian Institute of Science.
Can you hear me now? Okay, and thanks everybody for joining, including people online. So I'm the last person on this speaking session, at least scientifically, but I have never collaborated with Sudipta. I realize that now, my mistake, not yours. But I have learned a lot. And so today I'm going to talk about a mix of learnings from Sudipta, and you have heard so many things that has inspired me. It has inspired my students, inspired a large aspects of things we do. Okay. So first of all, congratulations to you, and I'll come to that Sudipta Da part for this spectacular first innings. And let me show you this picture. This is very recent, I think 2023 maybe. But what I learned from him is that fluctuations are the norm. Changes keep happening, right? But if you think about it, he is the one who disproves it first, okay? Because if you look at him, he has been this bubbly, enthusiastic character who looked exactly the same so many years ago when I first met him. And he's still the same. I might have grown old. Trust me, the photograph, I couldn't find my photograph from that year. I have changed a lot, okay? So I came here as a visiting research student. Before that, many people like JD and Somi, who had worked with you, had told me, hey, go work in Sudipta's lab. It'll be amazing. You will be fun. Somebody had said single molecule was the thing to do. So I ended up reading Sudipta's paper, right? And I came to IIT Bombay for a conference. I was a UG, third year UG. I had come for a conference, and I wrote to him. Can I come by to see your lab? And he said, yes, of course, you should come by. And I came by, and kind of introduced myself. I told him I had read his FCS paper, and then he was so excited, he went around the whole campus introducing me to everybody. But I didn't realize that at that time that he did that to everybody. So thanks to the VSRP program and Sudipta Da. And Sudipta Da came from the fact that we had a long discussion over tea one day, because as soon as I had arrived, I was saying, sir, just like we would do in IIT Kharagpur. And Sudipta say, what are you doing? You cannot do this here. And so we discussed for a long time. He won't remember this, but I have vivid memories of this. So over tea, we decided that we will make a compromise. I cannot call him Sudipto, and he won't let me call me sir. So we just said, okay, so we'll stop at somewhere Sudipto Da. And then, of course, I made amazing friends, Parijat, Balaji, Eric, who was visiting for UCSF at that time for that summer. And of course, Koti, Ira, Somi, and many of these Biophotonics lab members, and including the VSRP batch. So I have learned and gained a lot from that 2 months that's probably a peak experience for me. And I learned a lot. I first learned that you can build a very advanced level biophysics lab in India, because I wasn't sure if I went for a PhD abroad, would I ever come back? But he was my example that I could come back and I can do that. I learned that you can build instruments. You do not buy instruments and place them in the labs. The first thing I saw was Balaji was opening the cards from the computer and said, you could do that? And he said, yes, of course, you should do that. So the other thing I learned was thinking from the perspective of single molecules. The molecules were the individual entities that were actually carrying out the reactions. And biology was all taught in the perspective of this deterministic fashion. RNA polymerase comes, binds to the molecule, makes the RNA and all that. But there was nothing deterministic about it that we learned once I learned about diffusion and fluctuations. Of course, and then the most important thing that I learned was that you can have fun, and nobody has more fun than Sudipta, of course, while doing science. Right? So that ensured me that I can have a career in life. And of course, there were lots of gems of wisdom that I still remember and that helped me during my career, which I will share a little bit as I go along my story. So it's my story, but you will see how much Sudipta is responsible for shaping it. So this is the paper that I had read. I understood very little, and I came to the lab for the VSRB. I, of course, remember this picture vividly from the paper because that explained a lot. And I learned that good, beautiful schematics can make a big difference in your understanding. Equations took me a lot longer to learn, but the VSRP time that I spent here, I worked on that and I learned a lot. I then worked with Eric on PCH. But I'm not going to go into those because I'm also supposed to show you many things. So I start my PhD career. The first thing I say, I want to do now single molecule dynamics. There's nothing else better than this in the world. So I wrote to none other than Webb. And as gracious as he is, he said this, I'm paraphrasing, of course, him, that while I'm not taking any students presently, but if you are recommended by Sudipta, of course, you're most welcome. That at the end, I didn't join Cornell. Instead, I wrote to Enrico also. Enrico Gratton, another major player in FCS. And Enrico said, yes, you should come over. UIUC is a great place for doing biophysics of this kind. And we have this young faculty who is recently joining, again, another single molecule person. So I ended up joining TJ. So I'm not going to tell you my whole PhD story, but PhD, there was a comment about PhD that Sudipta said, and that helped me a lot. There were many times, there was a time when I felt as if I think I'm about to quit in 2 months or 3 months. And Sudipta had said something very interesting. He might not even remember. He said, PhD is a roller coaster ride. And every time I was about to quit, I remembered that and said, okay, it looks like maybe I might someday be reaching the top, not the bottom necessarily. At the end of the day, I did my PhD working on single molecule FRET. My temptation to see single molecules had what got me there, and I did see my single molecules there, and I did extract from, so learned how to make these microscopes, of course. And from these, you could extract the mean behavior of each of these single molecules, but you could also see the kinetics of the same molecule as it underperformed these behaviors. In this case, what you see is the donor and the acceptor doing anti-correlated energy, because of energy exchange. It is able to give you these anti-correlated signals. You can infer the distance changes that are happening either on the same molecule or two molecules interacting. Okay, and you can do this for very long periods of time. And from these dwell times, you could extract the rate kinetics in equilibrium coming from the fluctuations of the same single molecule. And that was the power of these fluctuations that I got learned. You could apply it to different types of systems. I will only show you one today just to give you a sense of the power that these have. So this is a very simplistic protein from bacteria. You also carry a similar version of it. It is a protein that wraps the single-stranded DNA and prevents it from getting chopped off. The protein is amazing because it binds at picomolar affinities to the DNA, but it also can fall off very quickly. And what, when I would do these experiments where I would put two dyes on the DNA, I would see all sorts of fluctuations like this. We learned how to extract from those fluctuations FRET states, which were quantized. And as you can see, these kinds of methods are powerful enough to give you well-defined multiple states which are within a few nanometers of each other. Okay, so what I'm trying to tell you is that a single static molecule that you normally think is stuck onto a protein or a DNA stuck to a protein, they are not static. They are also highly dynamic. And we could extract the rate constants for each of these steps from going from one to the other. Of course, the rate constants came out to be all the same. That's because it was doing one-dimensional diffusion on the DNA. Okay, so my learning was, even if the biologist is telling you something is deterministic, at the molecular scale, what is happening is what physics tells you or chemistry tells you. Okay, Robo, who was in the lab, junior to me, he went on to show that this protein kind of moves using reptation by folding the DNA, binding at some other place, and then taking the or freeing up another part of the DNA, and so on and so forth. And that's how it was able to do one-dimensional diffusion, even though it was wrapped up like this. Okay, and we could measure everything, all for kind of physical properties that you want. So the details are not important here. Okay, I also learned that I could copy Sudipta very nicely. So, in the physics department in Lumi's lab in UAUC, so I was in the biophysics program, but TJ was in the physics department. So I said, okay, physics department sounds good. I should go to chemistry now. This is about time. So I went to Harvard, working with Sunny Z, and then said, okay, fine, now I should do some biophysics. So I joined ISC, and then also the engineering, why not leave deep engineering? So I was here in ISC. So I started my lab, and then again, another gem of wisdom that came from Sudipta was, I said, what should I work on? I'm here in India. I know the methods. What should I work on? And he said, you know what? You should find a problem which is like an onion, right? The idea is that you will peel a layer, and then it'll, of course, reveal some new idea or a new puzzle. Then you peel another layer, and you keep peeling at it, and that will be your career. And this will allow you to have a career out of this problem that you have. So I decided to work on a problem which will make my career, hopefully, one day. And Sudipta has done the same for himself. So thanks again for this. So we work on infectious diseases. I will show you again from my examples how single molecule fluctuations are leading us to tell something about the systems. So one system that we study is these spore-forming toxins. These are proteins that you would have got when you had food poisoning and you got diarrhea. These things will assemble. They are membrane-binding proteins. They're bistable in the sense that they're completely comfortable being in solution in water. And when they bind to the membrane, they become membrane proteins. So amazing, because normally you think of membrane proteins and cytoplasmic proteins are completely different. And then there's many challenges that come with it. The way we study them is, of course, we tag them with single dyes, and then we would put them on supported bilayer membranes or cell surfaces, and we would watch them bind, and then we will let them assemble into this ring-like structure. And this is a very large class of protein. So even our body has them, and they punch a hole into the membrane. Okay. So if I can play the movie, can you play the movie? Anyway, I think you would have seen single molecule diffusion, 2D diffusion. These particles will basically do that. Okay. That's fine. I'll go over. I'll just show you the quantification of that. It's okay. It doesn't matter. So what if you see the trajectory of these single particles, what you normally think about is that they would be doing Brownian diffusion. Of course, that's true in an ideal world. Even if your membrane was completely homogeneous, if you had no interactions with the surface underneath, you might still end up seeing fluctuations which are very, very large from deviations from the standard Brownian diffusion. And what we realized was happening was because of changes that can happen in the protein rather than in the lipid membrane, you could see large deviations from this. Every time the protein changed its conformation, it will lead to a completely different diffusion coefficient, and that's what we were seeing. Okay, we of course can extract those from the single trajectories because we are watching one protein, its ability to move around, and its diffusion coefficient changes as it moved around, rather than taking the mean of all diffusion coefficients. And we can extract these kinds of conformation transitions that are happening. I'll summarize the story by telling you that we could measure the conformation change of one monomer of the protein, even before it has formed the ring, as it was changing its conformation from an initially partially bound, membrane-bound state to something which was starting to insert into the thing. But what I want to emphasize is our ability to be able to extract conformation changes from just fluctuations in locations. One thing we found, of course, was in this data, the behavior changed only once for one of the rate constant when cholesterol was present. What it was doing was this was the initial binding state, and this was the inserted state. And this state, we claimed that was getting stabilized by presence of cholesterol in the membrane. And this is the state which is supposed to lead to the pore formation. So we believe that cholesterol in the membrane was helping. And the consequence of this is that our cells have cholesterol where bacteria doesn't have any cholesterol. So we thought cholesterol was important for activity of this thing. And again, thanks to cues from him, we collaborated with theorists, MD simulation people, just like he does, and structural biologists. And we have been able to now, what we predicted before, show both with MD simulations as well as structure of the pore that yes, indeed, cholesterol goes into the pocket exactly where we MD simulations predicted. And just like we thought, it stabilizes the structure of the pore. Okay, now I'll tell you another story, which is at a scale which is slightly higher than the single molecules. These fluctuations are inherent even at the cellular level. You don't have a single phenotype and every cell is not exactly the same. They are dynamic and they switch dynamically between gene expression states, and we know them as phenotypes. And to believe that there is one single phenotype is just a gross 5. Okay, so we study, of course, antimicrobial resistance emergence. And the phenomena that is well known in this field is that most of the time you will be able to kill all bacteria. But when I say all, the very small fraction of bacteria that tend to survive, they are known as persisters. But if you do this kind of killing assays, you will once in a while find, and these are rare events, that the bacteria is also able to grow, unlike the persisters, which are not supposed to be growing. We can estimate all the mean properties, but these outliers, people have never been able to explain. They happen once in 5 times, or once in 10 times, or once in 20 times. So they are bacteria that growing every time, and these resistance and persisters exist in almost every antibiotic or antimicrobial peptide we would test, but also these behaviors where they would start growing. So they were acquiring resistance of some kind. What I want to tell you is, of course, I didn't want to tag ampicillin. Fluorescence methods are not best for doing that. But we could, again, thanks taking cues from Sudipta, we could tag the peptides, antimicrobial peptides, and we could do the measurements on those. So it didn't really matter for all properties. Antibiotics and antimicrobial properties seem to, at least they tend to show the same kind of heterogeneous behaviors. So these are live cell experiments where we are killing the bacteria. The dye going into the bacteria binds to the DNA when pores form on the membrane. And you will notice that most of the bacteria are dying. But so these susceptible cells are the ones which are picking up the dye. But there are also these tolerant cells which do not pick up the dye, right? And then there are daughter cells, which one of them dies and the other one takes much longer to die. Okay, so the phenotypes are extremely heterogeneous. Right? And what we found was a peptide like colistin would bind more efficiently to, and also will be correlated with how much dye it was taking up, means that colistin binding or the peptide binding was defining, and the peptides are cationic peptides in this case, which would bind to the membrane and kill the cells by puncturing holes. So you can do these live cell experiments, but we could eventually extract mutants that were coming up. And what was different in those was some genes which are known to control the membrane properties of the bacteria. The charge on the bacteria is what was getting mutated, and that's what was causing this to happen. So if you took, of course, now the resistant bacteria, they would continue to grow, whereas the susceptible bacteria shows this heterogeneous behavior. We can still measure now the colistin binding that happens to the PI signal, and you can see the resistant bacteria basically doesn't do anything. So the mutation has changed the properties of the bacterial membrane, and hence coming back to Sudipta, again, learnings from him. I'll leave you with this last example. So we, of course, study viruses as well. And in viruses, of course, they have their own membranes. They are membrane binding proteins that in COVID, for example, your SARS-CoV-2, you know about the spike proteins. Almost all RNA viruses and envelope proteins have these envelope viruses, which would allow membrane fusion to happen. They also use this to do the immune-scape. Antibodies generated against them, and this is how we have these various strains of Omicron and the Delta viruses and so on. So in dengue virus, for example, we went around the country because very little was known about the viruses that were propagating in the country. So, even before doing the single molecule experiments, we had to learn about what was the diversity that is existing in the country. So we measured sequences from patients directly of the viruses that were propagating in the country, prevalent in the country. And of course, dengue viruses are 4 different viruses, so they are all interrelated to each other. But what we found was their genetic architecture with respect, or their basically the envelope protein, with respect to its own variant that was a few years ago, was changing. That's not surprising, right? You would expect them to go away from what was previously there. But what we found was they would also once in a while come back and then go back again and then come back with a span of about 3 to 4 years. They would evolve, they would fluctuate around the mean while the mean is moving away from the. So what we found was this evolution was also correlated to negative correlations. Means when I would find, so this is positive correlation for us. Dengue virus is moving away from itself, its own ancestor, but dengue 2 virus is also moving away from an ancestor, and both of them are moving away from each other. Okay, that makes sense. But we would also find that once in a while they're moving away from their own ancestors, they were moving towards each other. Okay, and then the surprising question, why would it try to like to mimic some other virus? Right? And what we realized is that dengue has a phenomena called antibody-dependent enhancement. The idea comes from the fact that antibodies that bind to me but do not neutralize me can help me in get into cells which have antibody receptors. So it has been shown before that the second infections are worse in some cases when your antibodies are no longer able to neutralize. They go to an intermediate levels. If you have no antibodies, you would be fine, but intermediate levels of antibodies actually will give you this. And the virus now, of course, doesn't have a brain of its own, but it was taking advantage of the fact that every virus that looked like a previous infection, sorry, my bad, causing infection before would have an advantage and would continue to evolve and become a dominant virus. Okay? And what we found was indeed, whenever this kind of a phenomena was there, when negative correlation was there, those were the places when that new virus, which was starting to mimic the old virus, was taking over the Indian population of viruses. Yes. Yes, we found that it was only happening in the envelope protein and not every, and also these mutations were only on the top surface, which is what is accessible to the antibodies. I'm skipping a lot of details, sorry. Okay, so I would end here. Of course, the work is done not by me, but by the brilliant students. And I talked about work from many of them. I'm not going to list them individually, but I would definitely like to thank Sudipta. Thank you. Stay young as you have, and good luck for your second innings.
Viruses, have you checked what does that antibody do with respect to invading cells? Do they modulate trafficking or?
The easiest answer that people have put forth is that it helps in binding to the Fc gamma receptors because the antibody is already has a receptor for itself. So now you bind to cells which you would not have bound to before, and then now you're able to do invasion of those cells.
Sure, we'll have more discussion over there. Thank you once again, Rahul.
Thank you.
Thank you, Rahul, Balaji, and Shafi. Thank you very much for coming over and sharing these experiences. And for sure, you know, both Rahul and Balaji will call you again. This is very highly exciting. These are only nuggets. Sorry about that. It's only 20 minutes, but thank you. Thank you for coming. So it's the moment that we were waiting for. Actually, the high tea, sorry. not the remembrance. So, you know that there are population fluctuations exactly before food. So you can see in this auditorium right now, many people are back. And before we go towards Haiti, I just wanted to mention, so the next session is pretty much the last concluding session of the evening. We will have, of course, we will hear from Biophotonics group, young and old, okay? Or I would say, experienced and the one who are learning. And then we will have a few of the colleagues from TIFR speaking. And then we have the industry partners. And hopefully, if Sudipto brings the family, maybe the family, and then the last word. So we have that plan. Let's so and there will be a small amount of felicitation before you start. So that's the plan, but we might be sort of exceeding at this point to like 6:15. So just carry on, please, with us. And I will hand over the session chairship to Professor Ravindra Venkatramani, who will take care of this part. But I request Sudipto's lab members to be ready for some of the aspects that I might have to convey to the group, because I don't see many people in the Zoom. So this half an hour, at least I am Dev Shankar, will be ensuring that most of the people are up. If not, we will hear from people who are already physically in this auditor in this lecture theater. So first, so let's actually disperse and go to the West Canteen. Have some high tea. There is good food. Go.
Hello everyone. Hello, hello. I'm sad that I'm not attending today's event in person. I literally planned for months so I can be at TIFR today, but it still didn't happen. So instead, I'm sending this video message. If you don't know me, I am Parijat, Sudipta's first student. I simply cannot believe that Sudipta's tenure at TIFR
Deepali Dadi? No, 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 no. That is not exam.
से बात करवा देते हैं.
मैडम आइए 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 তোমাকে রোস্ট করতে হবে তোমাকে ডাকা শুনুন আমি এই কথা শুনতে পারবো না আমি স্টার্ট থেকে যতক্ষণ আলোচনা চল চলো 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 সেকেন্ড রো না এই যে এই সাইডে বস না 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 এখানে Okay, let's everybody take seat and we will give the control to a person who joined in 2012 in TIFR. So we are talking about graduated people and person who have joined in 2012. Ravi Venkatramani. Take over.
Okay. Yeah. You know that I'll give enough time to everybody at least. Okay, so welcome back. This is the reminiscence session actually. So what that means is piece by piece we'll be reconstructing Sudipta, right? We will look at him from different perspectives and finally we'll see what we create at the end of the day. So I think the first agenda is first we'll start with the Biophotonics group and then we will go to the faculty. So I'm not putting things in any particular order. I've tried to kind of rank it in seniority, but it's not going to work, I think now. So let's start with the Biophotonics group. So first we'll start with the video message by Parijat, one who was the first.
Hi Sudipta. Hello everyone. Hello, hello. I'm sad that I'm not attending today's event in person. I literally planned for months so I can be at TIFR today, but it still didn't happen. So instead, I'm sending this video message. If you don't know me, I'm Parijat, Sudipta's first student. I simply cannot believe that Sudipta's tenure at TIFR has ended. It makes me feel really old because I remember the day he started. I actually joined TIFR as a graduate student a few months before he joined as a faculty. First time I heard about Sudipta, I think, was from my friend Ira, who was 1 year senior to me. When Sudipta came to interview at TIFR, he gave a sensational talk, and that energized the student population. When he accepted the offer to join DCS, everyone was super excited and everyone all the time were just talking about him. And at that time, Ira, with her special brand of infectious enthusiasm, had convinced me that I should join him. A few days after Sudipta arrived at TIFR, I requested a meeting with him. We met in front of the West Canteen. He came wearing his signature smile and, of course, his blue jeans and white t-shirt. I was so very nervous and he could see that. And I was really happy and relieved when he agreed to be my advisor. At the beginning of it, we didn't have a dedicated lab space. We collaborated with Professor Rabindra Kumar, and our first paper came out of that study. It was 1999. In parallel, we were also starting to build our very first FCS machine. It was in the Chemical Dynamics lab. At that time, the lab space was shared by Professors GK and Perry. We worked on a small table behind the large Nd:YAG laser. We worked mostly after hours. The setup was assembled on our aluminum breadboard machined at TIFR. We didn't have a laser table. The first autocorrelation curve we recorded came close to midnight and on a Friday. I remember Balaji called Sudipta and he was there soon after. He verified everything and we were really happy. We all celebrated next day with pizza and ice cream. After Sudipta received his funding from the Wellcome Trust, we got our own lab space and we moved to the basement in the other side of B block. It was an L-shaped room that he divided into two parts, a dark room for optical experiments and another small part for wet lab workbenches and student desks. He literally started with an empty room, and in the course of a few months, it was transformed into a fully functional laser lab. This room was also the space where I spent most of my time at TIFR. Under Sudipta's guidance, we all worked hard and played hard. He was always present there, early in the mornings and also after dinner, setting examples for us. If laser mode locked, then we all worked till the experiment ended. Sudipta was also doing experiment with us. He instituted a culture of reading and thinking in the lab. We had long lab meetings that always ended with pizza and drinks. We went to cafes and restaurants together as a group, and we went out for monsoon treks to the ghats. He made sure we were productive in the lab and had fun doing it. My time at TIFR had its own ups and downs. I was very fortunate to receive a great deal of support from my close friends, Kanchon and my other lab mates. And Sudipta played a pivotal, significant and a very positive role in shaping how I came out of it. And I definitely came out of it a stronger person. Sudipta, thank you for that. And thank you for teaching me how to celebrate small wins along with the big ones. You most probably do not remember that conversation, but I do. See you soon, and I wish you all the best for your future endeavors, for the new chapter of your life in Hyderabad. Thank you. Bye-bye.
Next, we'll go to Shibu. Shibu is here. I'm sorry, I'm going to be calling you by nicknames as if I know you for ages, actually, but this is what has been written down. Yeah.
And follow India for always. So thank you for giving me the chance, and hello to everybody. Hello, Sudipta again. So first of all, I tell you that I spent about a year. Okay, I think so. Yeah, I spent about a year here in Sudipta's lab as a visiting fellow, coming back from abroad before starting my own academic career. So interesting story behind it is that, when from Belgium, I applied first time in Sudipta just for a position temporarily here. So he wrote that, what are you asking? To work with me or to work at TIFR? If you want to work at TIFR, write a letter to the department chair or director. And if you want to work with me, come and join with me. So as simple as that. So that's the lesson, he is always as straight as it can be. I think more like a laser light. And as simple as that. So I joined, as Parijat said just now, that we had to be there in the basement DCS lab, but what is the number? I forgot now. Whatever it is, there was nothing, whatever. So it was almost empty lab, and he used to tell something, myself and Balaji would go to near station. What is that market? To buy Lamington Road. Yeah. We used to go there to buy all those components to build up things, etc. Then myself and Balaji started making the table probably first before the laser was made. So to put the angles and screw it out and all these things. So all fun. As I said, as they said, it was all fun. Learning how to build up in the morning session, who was telling that building biophotonics lab, I think Rahul was telling about that. So all these things we did, but unfortunately I had to leave because I got a position at BITS Pilani. I moved out there, and then we came to contact again in 2008 or 7, sometime like that, with that DIT project, I think flagship project of the only he can think of this kind of project and implement it and implemented it quite nicely. Because at that point of time when probably he was almost picking up at TIFR, getting a 1 crore rupees project in 2006-7 and spending almost all the money to the younger colleagues by donation of instrument, that is unimaginable. Normally, we don't think like that. So again, thanks to Sudipta that you taught not only science to many of us, and till now you are doing, but human behavior, attitude towards life, and all these things. These are small but very important steps for us to follow always. And Deepantadi, as always, I think she forgot me, but so now it's not working, of course. I don't know what happened, but anyway, I think you can hear me. When we came here, I had a small daughter. My daughter was quite small. I think she and Aniket was almost of the same age or a little junior to him. So my wife still speaks out about the father Sudipta that he used to play with Aniket in the afternoon, 5 minutes at least in this lawn there with football. And she says that whatever you do in science, follow that person who does all these things with the small kids. So that was wonderful. And these small memories, I personally I tell that I don't have too many peaks to show like Paijat and others they had, but a lot of memories. As a mentor, as a guide, as an elder brother, he is always there with us. So I wish so that you stay fit as ever, stay charming as ever, and I wish you all the best in the Hyderabad life. Probably you will enjoy it over there also. And the transition, I think morning again who was telling that from IIT Kanpur physics, chemical science in TIFR, biology in Hyderabad. Hopefully mathematics remaining. I'm sure that I'm sure you will put a step in that afterwards. Thank you all and take care. Please stay well.
Can I request Balaji to? Your cell phone light is on.
All right. You have heard a little bit of stories there before, but I think my stories are much more simpler and but lot more jokes. Okay, so at least I feel that way. The one starts with very first time I met him, and this is like a student coming from a master's from completely where your professors are SARs, right? You don't call anything else. So first time I met him, so he explains to me, okay, this grandeur idea of we want to do this experiment and we don't have a lab, we don't have anything, but I know there is an instrument, a spectrometer, which we can modify. And all it takes is a small little base plate. And he explained to me with so much diligence that we spent at least, I felt like half an hour, 45 minutes discussing every single detail of how this thing should be done. And I definitely understood very well. At the end of it, he says, okay, okay, by afternoon, can I have a drawing? I said, drawing? What drawing? These are my exact words. And I keep telling this to my students. When I said that, I was watching his face, all right? There was not a single change in that smile. There is not a single, he realizes this guy does not know anything about teacher. All my time of 45 minutes I spent explaining to him is gone. And then he tells me, okay, these are drawings drawn for machinists to understand so that they can see it and all that. And
have you seen do you know about mini drafter? So those are the days where AutoCADs are not that in there. So no, I don't know. This is where I think really I learned a big lesson on that day, apart from maintaining that demeanor, is that all you need is a geometry box. I said, I have it. I will run and bring it back. That day, just with the geometry box and an A4 sheet of paper, we made the engineering drawing, or at least I made it, and then took it to him with all pride, said, I think you need a mini drafter. Uh, Again, I didn't understand the gravity of the situation at that point. When we got the mini drafter, both of us went to our Victoria Terminus, Sterling, somewhere stationery, bought the mini drafter. Then he drew the drawing for me, showed the. Can you see the difference? The difference was his drawings only had the pencil mark. My drawings had every other mark apart from the pencil mark, eraser marks, everything else. And that's where we started, literally. Again, many stories and many things that there is endless number of things. I gave a brief thing about serotonin issues of quantifying things. This was at Mekarajan, right there. So at the end, we had a doubt: are we actually measuring the concentration properly or not? So next day is my thesis defense and all that, and so I'm asking Sudipta, if it goes wrong, what do we do? He looks at it. Okay, we will correct it. How? That's why we both are here. And the conversation went till about 1 o'clock. The person does not have to stand. It's just one example. It's just amazing feeling. And there were, again, many personal there are personal tragedies, loss of life and all that stuff. He was there with me. I can't even explain it. I will start crying. So, but just thank you. Thank you for all that. And yes.
Can I request Kanchan? Where is Kanchan? Oh. He wrote a speech actually. That's great.
No, I didn't write a speech, but yeah, So in the morning, as I said, that I was a physics student and did 1 year of coursework in physics. And then when I was talking to many professors, then I was also talked to Sudipta. And as I said in the morning, that because of his magnetic personality, I got attracted in biophysics. So one of the things that I was asking him about his work, and he said, we are trying to understand the brain and how the brain thinks. And so I was a student in Belur Ramakrishna Mission, right? So my understanding of brain and how humans think and behave was little spiritual then. Then chemical. So when Sudipta said that this serotonin and how it controls our mood and behavior, I was a bit completely surprised that there's a chemicals are doing all sorts of things, which I thought should have been a matter of spiritual discussions. And so that was one of the magnetic monopole or whatever attracted me into biophysics. Well, so I had to join to chemical science department. And then I think in those days, there was a rule that one PI cannot take more than 2 students. But so I was the 3rd student maybe I was the first one to break the rule, or Sudipta broke the rule for me or whatever. Yeah, something like that. Yeah, for maybe the first student and first PI for whom the rule was broken. Then I joined biophysics. And I realized that before you do serotonin chemical, whatever, you have to first make a buffer. And you know that mostly before that, all I would do enjoyed solving equations and maximum writing some codes in the computer. And then Parijat was my immediate mentor, and she gave me this composition for phosphate buffer saline. And there were like some sodium phosphate, some 0.1 gram or something, and then sodium diphosphate, monophosphate, potassium phosphate, and then there was sodium chloride, potassium chloride. And I had a lot of struggle. It means that, I know I was making it somewhat stupidly. It means I put one salt and then it's supposed to be 0.1. And then if it is become 0.12, then again, I try to adjust it. And then I put the next one on the same pan. And so the next one becomes a little wrong, then I have to do it again. So it was like a lot of stress. And a lot of, at some point I thought maybe, my God, I should just go back to physics. It looks like this buffer test is too strong a test. So anytime we will have a meeting and Sudipta will, of course, sort of plan for the experiments and all. And I know that this buffer demon I have to face. So before I face the demon, all I will do, so we had a distillation setup in the lab where we could distill water. So and it was very slow. So all I will do, turn on the heater and just go. Then whole day I will use my spiritual training to train myself for the next endeavor. Anyway, with all my best efforts, then we were doing FCS, right? And so Parijat was teaching me how to make this rhodamine solutions, which we'll first use as for characterization of the diffusion time, G0, 1 over n, and all those things. And so I don't know, Sudipta also probably was enjoying the fact that I'm struggling. I mean, at least it was kind of funny also in some sense, right? In that sense, I would say. So it's okay, let's take a solution from Kanchan. So it's like 1 nanomolar rhodamine. So today we get 10 molecules. Some other day we get 0.01 molecules. Then he said, Kanchan, are you sure it's 10 nanomolar? Then what do? I said, well, it's probably between 100 nanomolar to 0.1 nanomolar anywhere. I thought that it was a pretty reasonable estimate, but he laughed, and of course, Balaji, Parijat all laughed. So I thought maybe I have to do a little more accurate than that. So anyway, it went on for quite some time, and then I think I was eventually able to sort of figure out how to do things so that I don't. And I also had this, coming up with strategies about how to sort of correct these problems. So I was improving. And then, as I said, that, but Sudipta was always, while I was thinking that I'm on the verge of crashing, but he sort of always was sort of encouraging and making it like fun also. Like one day in the night, I don't know what I was struggling with, and Sudipta said, Kanchan, I have an idea for it. So what? Can you make me a 1G centrifuge? I was pretty much busy with something, but then this challenge, how can I say no to challenge, right? So I kept on scratching my head, and I couldn't come up with any idea. 1G centrifuge, how do I do it? I could do all sorts of calculations, m omega square r and all. It doesn't work. In the end, he gives me an append tube and says, that's your centrifuge. I said, where is the centrifuge? It says 1G. Okay, so that's sort of the thing. But then what boosted my confidence, I should also say the positive thing, right? Was that, so we had this, we have one of the very important instrument in the lab was the FCS, right? Of course, Balaji was more into the multiphoton, which is also there. But since I spent a lot more time on FCS, and since you guys, many of you have done FCS, and even Hallmark is also making FCS, all of you know that these techniques are not that sort of not that simple. I mean, you have to really work hard, or you have to know what you are doing, etc., etc. You need a reasonable amount of expertise to be able to build an FCS and get a reasonable quality data, right? Counts per molecule or signal to noise, whatever you call it. And then Sudipta one day said that he has this fantastic idea that he wants to do FCS with an optical fiber. And of course, with a little bit of knowledge of physics, you could calculate that sensitivity of a fiber FCS would be basically minimum, even if every stars align, it will be 1/100th less than a normal FCS. Because the numerical aperture of an optical fiber is 0.12, while an objective has a numerical aperture of 1.2. And so at this 10 square, right? So minimum. And through years, like I think even Balaji and I, and there was a VSRP student, we did something. And we were able to get some fluorescence, but not FCS. But then again, we'll discuss and Sudipta will give some ideas and all. Then again, after a year or so, we'll try again. Because every time it will be requiring to order something like an optical fiber with a better quality, etc. But the thing is that neither he gave up, but also somehow by the time I was getting better at FCS, so I also didn't give up. And in the end, we were able to get signal from FCS. And that challenge, it had to go through, we had to go through a lot of troubleshooting and sometimes, I call it a bit of luck, but you had to also think about it. So it gave me the confidence that yes, even if something looks really, really difficult, because theoretically it was not impossible, 1/100th less we could do it, but you know that difficulty level when it goes to factor of 4 up, probability goes down by factor of 4 to the power n, where n is anything. So yeah, so that is about the research part. I will probably spend a couple of more minutes. So then the other thing is that the human side, right? So, and everybody has been talking about Sudipta's human side. So I had like 2 big obsessions when I was a student. I have gotten rid of one of them now. So one was for food, the other one was for playing football. Actually, both of them starts with F, right? So food and football. And so, for example, one day Sudipta invited, so he used to invite us every year once to his home for dinner, at least once, I mean, could be more than once. And so we were invited and we were discussing in the canteen at lunchtime that like who eats what. And I said, I can eat about 20 rasgullas anytime after lunch, before lunch, it doesn't really matter. And so he said, oh, good that you told me. So actually then we go to his home and it's like this, Dipandita, they asked Sudipta, are you inviting 20 people or 5 people? So there was like so much. So anyway, so I mean, I ate a lot. And but the thing is that I don't think I would be able to encourage someone if somebody says, I would just think, man, why does this guy eat so much? I'm not going to sort of encourage someone to, oh my, and enjoy it. But he did it for all the years that I was here. And of course, thanks Dipandita also for that. And the other thing was football. And my kind of obsession for football was so much that that this 5:30 I have to go. It means whatever, the summer it would be a little late, winter it would be a little faster. But, and then Sudipta has this, as Parijat mentioned, long lab meetings. So one such lab meeting, I remember that I started showing impatience that I want to go. And Sudipta said that the lab meeting is still going on. I said, no, you cannot, if you continue this so long, then how can I, I'm going to play and all. Anyway, so there was some tug of war. So I stayed in the lab meeting with a lot of sort of faces and tantrums and all. And he kind of ensured that I still stay. But next time we sort of, I think the lab meetings magically finished just before whatever. I was getting impatient. And so, yeah, so basically he continued this encouragement. And the other thing I think I should tell about my marathon running. So Bombay Marathon became suddenly a big thing in 2000, some 2, 3 or so. And one day again, night, we were working in the lab, and Sudipta said, Kanchan, Bombay Marathon, are you participating? I said, yeah, I just signed up. He said, oh, great. Are you running for 6 kilometers? Then I said, no, I signed up for 42. He says, 42, what is the longest you have run? And I said, 3 kilometers. Any clue that there is a difference between 3 and 42? Anyway, so he realized that I have no clue what I have done. But the thing about is that if somebody like my student did it, I would just think this guy has gone crazy and whatever. But he actually told me, why don't you talk to Professor Rao and Rajan? They are also participating. And then maybe they can give you some advice. So I went to Professor Rao, and then he actually gave me advice. He even took me for practice and all. And so anyway, I did demonstrate that I could run 27 kilometers in the next 2 weeks. And then I go for the marathon running. And then I see Sudipta at this Chorni station or something. Say, Kanchan! And then there is then the marathon runners go, and there is a turn from Bandra. There was this place called, And when I'm coming back, by the time I have reached my limit, and I was getting a lot of pain and so I thought I'll go. And when I just thought that maybe, you can see the train station on the side. And when I thought that I should now give up and go, I see Sudipta and Balaji both. I said, Kanchan, you have done 32, so you should just walk and finish it. Don't give up. And so I didn't give up and just walked and finished it. So, okay, I think I spoken along. But the last thing I will still say that another thing about him was that about this encouragement, right? So it's like, even though, as I said, that I was not doing well as a student for the first several years, but that didn't stop me from throwing tantrums whenever I did. Like, for example, one day Sudipta was explaining, wanted me to build a power supply for the APD, or avalanche photodiode, which are very sensitive to small fluctuations in voltages because they just burn. And I was not paying attention. And then after some time, he said, you are not paying attention. I said, yeah, don't worry. I have my friend who knows much better electronics. I'll get it done. So he looked at me, and then he said, okay, that's fine. So anyway, now that I have said that my friend is greater than him, or whatever I indicated, so I had to prove. So I did build the power supply, and then my friend made some extra modification than Sudipta's original design. So that Sudipta was convinced that my friend is good. And so not only that, he became friendly with my friend, also during Dashera, he brought a big box of chocolate for my friend and gave it to him. So basically, that is what, as Balaji says, a true leader should do. And about the other things that I learned from him, and which I still carry, as Balaji says, that it should inspire the generations, right, Balaji? So is that Sudipta had all these regular lab meetings and literature meetings, which I still try to do in my lab, because I benefited from them. And then the gems that I learned from him, apart from the lab meeting, literature meeting culture, was that one day in the Monday morning, I come to the lab, and I didn't show up in the lab for Saturday, Sunday. So Sudipta said, "Oh, Kanchan, what did you do in the weekend?" I said, nothing. And then he told me one thing, that don't tell me nothing. Either you do something in the lab or you go and enjoy. Just don't waste your time sitting and doing nothing. So actually that really sort of suddenly hit me like a piece of wisdom, that this sitting in the, I don't know what I was doing. I'm pretty sure it was wasting time in some form. They told me that, okay, either I should work or I should sort of spend the time having fun. And so I keep telling that to my students as well. And then the other thing, one day I said to him that yesterday I couldn't sleep. So I was feeling a bit tired and all. He said, see, if you cannot sleep in the night, the best thing to do is come to the lab and work. Because if you can't sleep, you work. If you get tired, you can go and sleep. Okay, so with that, I will end. And thank you, Sudipta.
Kanchan, I believe I paid you back for the time you gave me for during my talk.
Great.
Yeah. Can I request Madhuri? Madhuri is here actually. She was there in the morning. She had to leave. Okay. Then Senthil is here. Yeah.
I can't believe I'm so much up the ladder, but anyway, I'm not very good with speeches. If you want to hear a good speech, come to Gokul late at night. But yeah, I came to Sudipta's lab in 2005 as from the DBS. Sudipta thought I was a biologist. The biologist thought I was a chemist. And I had a degree in chemistry, and then Sanjeev at that time was teaching me cell culture and everything. And so it was a mixed bag of, I had no clue what I wanted to do, but it was a very sort of dynamic lab, different people doing different stuff. At the same time, the lab was in the basement. We were moving stuff. And I didn't realize what all this experience was teaching me. I think all this was teaching me was how to manage stuff, how to live through different situations. You know, you tackle the situations and go through that, and all sort of those things. I don't remember a lot of funny things that's happened in in the lab, but I do remember that we tried new things and. Well, फिर भी 0.1 to 500 like. So yeah, so but eventually what was amazing in retrospect was at that time I built a turf microscope, and it was 1.7 NA Olympus objective, which was the highest NA still possible today. And in retrospect, what struck me was Sudipta had that in 2005, that objective. I don't think anybody else, still a lot of places have that sort of objective. And Sudipta had that, and he had a vision that something can be done with this. And we measured exocytosis and stuff. So I think that sort of taught me when I run my lab, I take a lot of inspiration, or as Rahul said, you know, you copy Sudipta, you'll be fine, right? So we have stuff lying around that we don't need, but we have an inkling that this could be useful, so we get it, and then some idea props up, and then we build something, right? So that those sort of things I learned, and then we of course built the first light sheet, just a prototype model in Sudipta's lab at that time. One of the things I learned again from Sudipta was to manage people, because there were quite a range of people. Kanchan was there. And now there was Suman Nag, who was very serious, focused. And then there was Sanjeev, right? And Sanjeev was there. And I could really see how Sudipta was managing Sanjeev, right? So I'll just give you a little anecdote. Sudipta will ask, Sanjeev will not be in the lab. Sudipta will call Sanjeev, Sanjeev, कब आ रहे हो? And Sanjeev will say, मैं 5 बजे के पहले तो नहीं आ पाऊंगा, right? But and then Sudipta, okay, and he'll put the phone, and then he'll realize he said 5 बजे के पहले नहीं आऊंगा, लेकिन कब आएगा ये बोला नहीं अभी. But I saw that Sudipta was really very patient with Sanjeev and stuff. And I learned that it's okay, you know, people have their troubles and whatever situations. You don't need to go into the details. You just go over it and stuff. And so that was something interesting to see that, okay, you know, it's all fine. And then, you know, when I have my lab now, I have international students, I have students from Germany, Australia, whatever. And I try to send them to the FCS workshop. They've come quite often to the FCS workshop and stuff. And when they come to TIFR or into Bombay, I make sure that they meet Sudipta. And not a lot of them realize because of cultural differences and stuff. But they point out one thing, that Sudipta kept referring to me as academic grandchild, right? And you know, it might be a joke for them. Some people realize, but not a lot of people understand that it's a very valuable thing. There's an idea of a family, academic family there, and that's very valuable. And I tend to, appreciate that. Our lab is a very close-knit family. We all help each other, even if we have never met Vidyut, for example. And we somehow said, Vidyut, a new student is coming. Then he came to Dresden when I met him for the first time. So one can trust that you can go anywhere if you are in the Biophotonics family. You can just call them up and go and reach out for help, and we all help each other out. And I'll leave with one final gems and statements of wisdom, and it's a lighter one, okay, just for fun. I wrote my master's thesis and gave it to Sudipta. And this advice that Sudipta gives, I still follow it to the date, right? Sudipta corrected it and everything, and he gave it to me. And then he holds it back. He doesn't let me pull, right? And then he says, "Kam se kam Microsoft Word jo bolta wo to theek kar lo." Right? Right. With that, I'll close here. Thank you.
Jenu Chaku. I'm sorry, this is just a list that I drew actually. So if I'm missing somebody in between, please. Yeah. No, you guys, they'll be there.
Hi, I'm Jenu. I was a JRF here for 2.5 years in 2009 to 2011. So there's a lot to say. I'll try to be short. Now I'm a scientist in medicine. I'm not a PI. The reason why I chose something like that was how much I interacted with Sudipta, and the lab kind of tuned into what I could really become. How do I start with? So I wasn't prepared for this, so everything is in the last moment. So I come from a program in QSAT that actually was making a lot of photonics folks. So 2 batches before me, Sudipta took one person. He was happy with that guy. Then that was Jitin Jose. He's running a company in Netherlands now. Then the second was Varun Kas. He was also doing an amazing job with Bunka and made a prototype of FCS machine that Shubhida was actually talking about. So Sudipta thought, then I'll have 2 more guys. He got me and Sanjay. We were again in the same program. We came here. Sudipta quickly learned that we are not like the other folks, but he spent his time. He made it all work. Things that actually stood out. It's the science part. You guys all know how well Sudipta is, but also a lot of personal things. He helped me with understanding where I'm good at, where I'm not. That helped me tune my career where I want to be. But small things like, when we were setting up the FCS workshop, most of the people completely forget that we had an entire CCD coffee machine there. For everybody had a CCD coffee. That was completely out of the norm, and we actually spent extra time to make sure everybody got really good meals. We went out, tested out all the food, and made sure that it was a really good meal. So the time that you spend time to get the best out of even a small thing, it was very important. Those are the main things I learned, and I could again tell a lot of stories, but it might be out of my place. So I'll go to the next person.
Yeah. Now I get into familiar territory, Vidyut.
Thank you. Yeah, a lot has been covered so far. And I'll start with something that Bappa said. It's not just about Sudipta, but probably Kanchan. So Bappa just said Kanchan came prepared for a marathon. He started a marathon, and this time he came prepared with notes. Yeah. So my time in Sudipta's lab was extremely good. Actually, when I joined, the lab was probably the smallest size. Only Suman and Arkarup was there. And just before that, Kanchan, Sanjeev, and Banka left. So the smallest size. And that's gave me very good opportunity because of the small lab size to work in all the projects. So I worked on the imaging side and also protein aggregation side and learned all of them and had a lot of fun and doing the experiments. Okay, and there something came about not giving up that Balaji said. So when I joined, the dopamine imaging project was at least from the optical side almost complete. In light neurons, it has been shown dopamine can be imaged with 2-photon imaging and everything. The manuscript was almost ready. Senthil also probably worked on that. And then that was 2008. And after a couple of years, something strange happened. Every year end, I was working on the same project. I don't know why, how it coincided. I was working on several projects, and every year end, somehow I was in the Hartman lab for 3 consecutive years. And during the year end time, I'm working on the same project. And every time, actually, I'm trying out different things to convince we are actually looking at dopamine. So sometimes through immunology, something else, some fly model, and some tagged things. Okay, and finally, actually, we worked out and we showed it not optically, but through mass spectrometry. It was a completely different idea. So we actually did not give up, and finally, we published the work in 2014. So 6 years after I joined, when the project was initially, at least from the optical side, was complete. So it was sort of not giving up and finally showing to the world that is there. And coming to a funny incidents, actually, it involves Devanjan also. So we always had some which is the impromptu, sudden ideas would come up and would like to try. Okay, so we had amyloid beta and some variants of that. So one was short, truncated. We used to call it S. And then there was some permutated version. We'll just call it the letter P. Okay, and somehow the P version seemed like amphiphilic. It may behave like a lipid. Okay, it's a co-block polymer or something. So we are discussing there is a possibility it will make a vesicle, the peptide. Devanjan enters from somewhere. Sudipta just said, Devanjan, take P, make vesicles. Devanjan understand what P means and he's completely shocked. Yeah, so finally we tried, probably the vesicle didn't work out, but yeah, we had many moments of that. And so something that I actually really appreciated is Sudipta gave time to us for learn by ourselves. So something else also, others also said that. So to struggle, learn during that time, but when it's going beyond the limit, he is always there. So actually, it happened several times that I thought about the problems and worked on it. And finally, when I'm not able to go, do it by myself, I reach to Sudipta. He already knows where I am at, exactly at what level of difficulty or struggle. And then he can take it from there and guide us. And that is something I really enjoyed. And I'm trying to, I've learned many things and trying to learn also on the human side as well as a mentorship and scientific side. That's all. Thank you.
Then Debanjan, actually.
So I was just doing a calculation over there. When I joined 2009, it was 12th year after you joined TIFR. And when I left, this is the 10th year. So I exactly spent the middle part with you. So I have seen people easily calling you Sudipta Da or Sudipto to somebody who is refused to call you anything other than sir. So that whole journey. So the funny thing is, again, so he ended with one experience that he had with me. So when I joined, this all the whole senior bunch of people, including Jenu, Shumanda, Vidyut, they went to Ladakh, and they got missing. So there was a mudslide. Many people actually died, unfortunately, and there was no communication that could be done with them. People were jokingly saying, "I'm the senior most person in the lab now." and Sudipta was in Canada. So that was the beginning of my my journey in the lab. So I have nothing much to add to whatever people said. I'll just add two different incidents. So, okay, I'm doing the same thing Jen was doing. So yeah, so one thing is there was a beanbag in the lab, and it was allowed if you are working late to nap. So I took that allowance to a different level. And one fine morning, I was taking my nap a little too long, and my nap involved snoring. And Sudipta had a guest with whom he entered and found his student sleeping and snoring on that beanbag. I think right after I left, the beanbag was thrown away. That incident doesn't get repeated. So yeah, so at the end, I would say that the personal side, that kind of interaction that we had, in the personal level, that is beyond anybody's expectation. Like I have seen you, or Vidyudha have also seen him giving Kanyadan in Arya Samaj. So that level. So yeah, so that is it, and all the best. It's just the beginning, and we are already hearing what your all plans are over there. So yeah.
Thank you. Now we'll go to Bappa. Bappa, are you there actually? Can you hear us? Mute again. Why is it muted actually? They should be hearing.
Hello, can you hear me?
Yeah, can you turn your video on? Is it possible?
Yeah, sure.
Yeah.
I'm top of a 6th floor building now.
Yeah, go ahead. Whenever you're ready.
The host is disabled the video. I don't know why.
Host has disabled video. Video on कर सकते हैं? Video उनका. Okay, so we've sent a request. You can take it up. Yeah.
Can you see me now?
Yeah. Okay, go on.
Okay. Hi, everyone. I feel extremely unfortunate not being there physically. Like, I would love to be there and share all these moments with the old lab mates and new ones which I have not met so far. So those who don't know me, I did my PhD. I'm Bapparito, and I did my PhD from like 2011 to 2018. Like I started at Sudipta with the first project, but I feel like there's a very interesting point, like how I started my project with Sudipta. The first day in Sudipta's lab was in Goa for me. So the day I joined Sudipta's lab, Sudipta went somewhere, like I think in US for something, a conference, and the whole lab decided to go to Goa. So I joined on a Saturday. At the Saturday, it was everybody in Goa, and they also booked a ticket for me. So I started officially meeting everyone in Goa beach, having beers and everything. So that's how I started my lab with Sudipta. Eventually, like after I finished my first project with Sudipta, I actually being part of the bigger collaboration with Madhu. And I worked partly with Sudipta, partly with Madhu, like working both part of the solid state NMR and the fluorescence combined. So basically, it was a project like or a question driven like PhD for my case. It was not any kind of related stick to any kind of particular technique. So like talking little about what we learned or what I learned from Sudipta lab or TIFR versus other places like where I have been so far. So there are a lot of differences I have seen, like if you compare TIFR or Sudipta's lab versus when I came for my postdoc. Like the things I have seen, like, and I still cherish the part that in our lab when we were in Sudipta's lab, that everybody was so curious about science. Like we used to do so many experiments, and many of them were just based on like, okay, let's see, like if you want to do these things or if you want to try these things, what will be the results? We never had not never had like for many of the projects, like we initially didn't have very clear goals at what will be the outcome. We were just curious based on the question. So the most of the science part was question driven rather than a very specific hypothesis driven. So there are two different ways of science I have learned so far. So there is nothing wrong or nothing bad in any of the part, but they are very different approaches. When I came for my postdoc, I've seen people the way it's less curiosity driven, more hypothesis driven. Like there are a very fixed way or fixed routes people follow here, compared to what we did in Sudipta was like that we was just curious about like or having fun with different experiments. And the part I really missed later on was that Sudipta was always there to support us, like when we are doing experiments, when we are having failures. So really, if we had failures, like we never had to scared of anything. Like okay, Sudipta was there to think okay and to suggest okay, maybe it is because of that, maybe it's because of that. So we was always feeling encouraged about doing more and more work or more and more sciences. Something I deeply respect about Sudipta is like its passion for science. Like I can give you one small example, and I still remember that. But I try to get that learning from Sudipta was that there's a one day I think like there are a few work from our lab. I think from Vidyut and others that we would work distinctly from monomers and oligomers of amyloid beta, and we find that there are distinct differences between monomers and oligomers. And there was a work, I think, by Vidyut that monomers does not bind to the membranes, but oligomers do bind. And at some point, before we could publish the paper, our work was scooped and published in a JAX paper by some group. I forgot the name. And the day we realized and read the paper, everybody was like, I was feeling very shocked, although it was not directly my word. And I was thinking like how Sudipta will react like on this situation. And completely contrary to my like belief and surprise, it was like Shweta was not feeling so like so pathetic or so bad. Like he was feeling encouraged. Okay, at least science-wise, people know that this is important results, and they know it. It's sad that we could not publish it before them, but at least the community knows it. So I learned something that the way he handles competitions was I really respect that part. Like it doesn't come from a very negative part, but like he takes it as a very positive. So that's something I really try to learn from him, that even if you face difficulties, face competitions, face that your work gets screwed or something else, there or any kind of any negative situation, you should not feel so sad or bad. Like you should feel encouraged to do more something better than that what you have done so far. So these are some things I really loved about Shakti. So, and also like when I was there, we celebrated his 50th birthdays, and now he's retired. So times really flies. So even if like TIFR gives him a retirement, like I feel it's TIFR loss and bits gain, because even if at this age, I can bet he is more energetic than many of us combined together. So it's just a new beginning for him, and I believe that he'll do excellent in his new venture. And also, as a part of Biophotonics lab, like we are always as a bigger family. Like we never feel like we're separate from each other, even if we don't know. Like many of my seniors, I don't. Can you hear me now? Actually, I can.
Yeah. We can hear you. Yeah.
Okay. Yeah. Okay. So many of my seniors, like for example, Sumon Pariyadi, so many concerns. There's so many other, like we never met during our PhD time, but whenever we meet later, we always feel that okay, we're part of a bigger family, and everybody helped each other, stay with each other for any different causes. And for Sudipta, it was not just a guide or mentor; it was more like a senior friend, like who can help you in your work. At the same time, I bet for everybody, he was a more also as a personal mentor, like for everybody or for every one of us, like I think he knows most of our personal stories, personal struggles. And still today, like if we face some difficulty, we still go to Sudipta, even personal or scientific. So he's still there and he's always there. And I believe he'll be always there. And not just with Sudipta, like we still have very great bonding with Dipantadi, Aniket, Dumbas, who we always have to be a part of bigger family. We went to many different outings, like many restaurants. Like we had a lot of fun in the lab together. And but finally, like I want to wish best of luck to Sudipta for his new venture. And I want to ask one thing to Sudipta, that Pariyati told after long group meeting there used to be pizza. When did that stop? We never had pizza after a long group meeting. anyway, my best wishes to Sudipta, and he'll be doing great. So thank you, everybody. I'm sorry I could not be part of
Thank you, Bappa.
physically be there. Yeah, sure.
Okay, I think I missed Neeraj actually. Is Neeraj in? No, no, Barun is coming later. Barun is coming later. Yeah. But he's in the next. I mean, what is the point of being a chair if you're overruled everybody? Yeah. Hi, Daniel. Would you be able to stay a little longer? We're just finishing the biophotonics lab. That's great. Yeah, great. Yeah, Neeraj. Yeah. I prevailed.
Thank you. Hello, good afternoon, sir. So I came from Cochin University, joined as a master's student, I think back in 2009. And because of his passion for optical instrumentation, I think lots of students from Cochin University came and joined you back then. And I was fortunate enough to work with you. And if you will not be able to recall, I think we created the FCS with fiber optic cables and all, alignment free. And we also got to publish it in JBO. And my biggest learning for me was like, when we started writing the paper, since I came from QSET and all, we were not having a very good exposure to the writing part of it. I remember you were very, angry on writing and drafting all those, journals and all, how to write. And if I'm not wrong, when we finished our writing that journals paper, it was the 70th draft. Okay, it took around 3.5 months for me. This was only thing I was doing for last 3 months. But the best part was like it got published in 2 days. And that time I remember he was visiting his parents in Kalyani. And when I called him in the evening time, he did not believe that it got published in 2 days. Then he asked me, Suman ko bolo call karne ke liye udhar se. Then Suman called you. And then he asked that go and take a biggest party from him. So that was, thank you so much for all this learnings and all you gave us. Thank you.
Yeah. Firstly, I'd like to thank JD for organizing such fantastic event. I have learned a lot from this lab, and there are so many memories, but of course, the time will not permit to share all, but I'd like to share a few. So I joined TIFR in 2013, but of course, during that time, we had to first go through 1.5 years of coursework. So in the second semester, we had to do 4 coursework and then project. So, so at the end of the first semester, every faculty will discuss their projects. So Sudipta also discussed all the projects to our batchmates, and he described about 10 to 11 projects. And out of them, at the bottom there was one project which is related to completely optics related, and which started with the guide star, and that seemed very fascinating. But I understood very confidently, I would say 0%. But since the name looked very fascinating, so I picked up the project. So I decided I gave the preference as my first project mentor, and he also chose me. And then he explained the project very nicely, and the experience was as similar like Balaji. After about 30 minutes or so, I felt that I understood all, but actually 0. But then after explaining the project, he said, okay, now we can go to the Hartman and start building. But I did not realize what to build and where to build. And then he understood, okay, with my face, probably I am not so confident to build. He said, okay, Anand, he was during that time, he was senior. So Sudipta said, okay, Anand will show you how to handle the microscope, and then you can put the fiber at the focal point of the lens. Okay, fine. But then you have to align with the 3-micron fiber. Okay, but I did not have any idea how 3-micron small it was. So then, okay, for the simplistic purpose, you first start with 100 micron, and then gradually 50 micron, and then 25 and 3. Okay. So the next day, Anand showed me how to operate the instrument, and I started where to put the fiber. Then once it went and showed, okay, here you have to put the fiber. Then I started aligning 100 micron fiber. And I tried during that time again, we had a coursework. So it ended around 1 o'clock. So after the lunch, I started 2 o'clock, and then at night, 2 o'clock. So 2 days I tried, 12 hours. And the third day I went to, after my coursework, I went to shift to the office. Are you sure is it possible to align?
Has anybody in this world have aligned 100 micron fiber in the top? And he looked at me and started laughing. You can ask anybody in this lab. Everybody has aligned 25 micron and you are struggling with 100 micron. You can try again. And then I went back, and then at 4 p.m. next day, you can give me a call if you cannot align. But just before reaching, maybe around 1 hour ago or so, I could align with 25 micron fiber. So that's the starting with with Sudipta. Okay, and then it was a quite maybe first or second group meeting. But before that, I used to hear that, okay, Sudipta is very particular about the timing. And I always try to make sure, okay, I can reach on time. But that day, and during the time, the group meeting was used to be on Sunday 10 a.m. And of course, it was very hard for a grad student to wake up at 9 a.m. in the morning on Sunday. Anyway, but we used to wake up, and that day I make sure, okay, after the breakfast at Jagdish, 9:50 finish it, and then within 10 minutes, I'll come to the group meeting. And that day I forgot to take my notebooks. In between, I had to go to the office and took it and came here. I thought, okay, maybe I am reaching at 10. And Sudipta was walking, and I opened the door and saying, Varun, group meeting start at 10 o'clock. Just within 10 minutes, I have come here and looked at my watch. It said 10:02. That kind of punctuality he used to maintain. And the other is funny story, which involves Vicky. He was my senior. During the time he was rotating our lab, and he was doing the project with me. So one day, Sudipta said, okay, Vicky, can you make this solution by mixing the glycerol and the water to maintain the viscosity so that we can see how the conformational dynamics is changing as a function of viscosity. And Vicky was not doing nothing for 2 days. And Sudipta realized and was not happy. And then before leaving the office, he just went to the lab, and then he grabbed Vicky and asked Vicky, what did you do? And Vicky said, I was telling blah, blah, blah. And then Sudipta, what data are you telling? No, I was telling, there is only one data point. What data are you telling? And then, okay, can you go to the lab and what are the mixes that you made? And then he went to the lab for bringing the books. And during the time, I tell Sudipta, he was not telling any data. He was telling. Okay. So I'll share one more thing and then I will end up. So of course, I have learned a lot of things from this lab. The one thing that really I would like to mention is the attitude for the work. So one thing he has made sure within us that first ask the question very clearly and go ahead whatever needs to be done for that, including if you need to be sometimes work as like a carpenter or sometimes maybe like drilling the holes. So you should do it. And that's what happened. Maybe we had the cutter, we have the drilling machine in our lab, and sometimes we have built an instrument, and to get rid of the dust or light from outside, we have to cover up with the wooden parts. So we used to get the wooden parts from the workshop and then maybe cutting with the cutter at 10 o'clock at night. So those kind of things that he has basically spread it out within us. And so we used to keep our shoes outside at lab. And since during that time, the number of people was more, so outside the lab, it's not comfortable because so many shoes are outside. Then Sudipta thought, okay, maybe then if we can buy the shoe rack, then it will be easier. So he ordered a shoe rack, and through the Amazon delivered around 5 o'clock or so. So Sudipta called me, okay, can you please pick up the shoe rack? I said, okay, fine, I picked it up. And around 10:30 p.m., Sudipta came to the lab and then asking, Varun, क्या कर रहे हो? अच्छा वो जो shoe rack आते चलो assemble कर लेते हैं. I mean, during that time, Sudipta was around 53 or 54. At the age of 54 and 10:30 p.m. after the dinner, I don't think anybody will come to assemble a shoe rack. So those kind of like working attitude, all these kind of things that has been with us, and I hopefully will be carry all these things and spread it up into our next generation. With that, thank you, Sudipta. Yeah, thanks, Varun. So I'm missing a few people basically. So I'd like to call Rahul actually to, yeah.
If I may request one thing to everybody else, actually, I'm really enjoying the stories. I have no punctuality issues, but my co-chair is getting a little nervous, actually. So let's keep it a little short, actually.
Yeah, I already said what I thought I have learned from Sudipta, so I'm going to keep it short. I would say it was also about Sudipta, but also the kind of people he got into the lab. He had an eye for the right people, and that showed in the students that he was able to get into his team, and they have been like a family. So congratulations on doing that. I think it is a great achievement in that regard. So.
That was too short, actually, I think. Okay, I'll now request Arpan. Arpan, can you hear me? Arpan, are you there? I think. Yeah, I can. Yeah, Arpan. Hi, Arpan. So you're muted now.
Hi. Yeah, now I am unmuted. Yeah.
Yeah, we can hear you.
So
Please.
yeah, I know we have less time. I'll try to keep it short. So it's first of all, it's weird that I'm sitting behind the screen this time because like just a few months back I was on the other side. But yeah, it's also nice to see all of you together because I have heard stories about all of them from Sudipta, and now I can hear them from yourselves. Yeah, so that was amazing. So I'll just tell two incidents, which will, and I will also like to keep it short. The first one is, so I joined TIFR around 2017 as an integrated PhD student after my bachelor's, and the lab around 2018. And the initial days, I used to make a lot of mistakes. And so one of the thing that I remember was it was my annual watch seminar, and I completely forgot that that day was my annual watch seminar. And both me and Sudipta, we were in Charudi's defense, if I'm not wrong. And suddenly there was an email from JSG that today is Arpan's seminar, and I never even cared to look at it. I was like listening to the talk, and Sudipta was in between, and then he calls me up. Okay, is today your seminar? And I said, no, I think there has been some mistake. But I went ahead and I found out, yeah, that that day indeed was my talk. And I was like completely shattered, like because there was no presentation ready, etc., etc. And then Sudipta was like, try to convince me that, okay, there are moments in life that happens like this and you have to prepare your talk in between. I couldn't take it. I just went to room and fell asleep. And then he was worried. He asked everyone of the lab that where is Arpan and whether he's doing fine or not. And later in the evening, I came back and he said, are you mad or something? You should have at least informed. So that is one. And then the second one was like, I think during our first trek, that was my first trek in Naneghat from the lab. And I think Borunda was there, Diana was there, and there are many others as well. And so it was my first trek. It was difficult for me, obviously. And so Borunda was constantly kind of motivating that, yeah, you should complete it. You should complete it. And Sudipta was like vanished in between a few minutes, right? We couldn't see him any further. And we were kind of very sure that definitely these people who are old enough, they must not have completed the trek. And we are the one who are struggling to go up. And eventually we completed it. But when we were on the almost the penultimate step of the trek, we found Shrituda coming from the top and saying, oh, you guys have not yet reached. And that was like amazing. Oh, okay. So that's like the kind of energy that he has and the kind of attitude that he has on making things complete of things which also seems to be very tricky to begin with. And so just lastly, so when I reached here in Cambridge, the same day he texted me saying, have you reached properly? Have you been to the lab, etc., etc. So I think that those are the moments where you feel that you have transcended the relationship between just a supervisor and a student, and it's more like a family, the entire biophotonics family that we are seeing right now. So yeah, so thank you every for all the things that you've done, and wishing you very all the best for the upcoming journey that you're going to take. So thank you so much.
Thank you, Arpan. Yeah. Now I request Dev Shankar. We are now in the current batch.
Hello. So I joined TIFR in 2018, and so I was a very fond of Walter Levin's lectures. So I used to see his lectures in he's in MIT, but then I thought, okay, can I ever be able to see something like this in my can I be a student of such a guy? But then I came here, and the first lecture that he gave here, it was I still remember I was with Aditya. He was my friend, and we was jaw dropping, and I couldn't I wanted that lecture to be go on and on and on. So that was why I joined Sudipta. So yeah, everybody mentioned uh, lot of things about Sudipta, but I would like to mention one incident which shows the energy that he has got towards life. So it's a little funny also. So once I went to Europe in Paris, and there Shimridi was also there, and we planned a trip, a 1 day trip to Paris. So I went today, and then tomorrow we have planned to roam around the city. So in the morning I went with Shimridi to Shudipata's flat, where he was planning to stay. And then we went at 10 a.m. and then but we couldn't find Sudipata. So where he is? So then we called him and his phone is switched off. Then we found that okay, see, he's coming that day in the morning, he's flying from India on that day. And then he came. So we thought that okay, then the plan is gone because he's coming so late. But then what he did, he didn't go to the hotel, or he didn't, and he went with us to go around and roam around the city. And then so we went to 3 places, many places, and then finally we went to Louvre Museum. And me and Shimridi and Sudipta was also there, Aniket was also there, and we were roaming around, seeing all the sculptures, and suddenly we saw that Sudipta is not with us, not with us not roaming with us. So then, and then we went to the previous room and see that Sudipta is still there looking at one of the sculpture. And then what he was doing was actually he was reading, he was seeing all the sculptures, reading all the notes that are there in the sculpture. And not only that, he would also take the phone, he will put it in Google Lens and also read about all the sculpture. And he did it for all the sculptures that are there in the Louvre Museum, and we couldn't finish the viewing the Louvre Museum. So this was the energy that he has, not just learning science, but learning everything that is there. Yeah. No, it's in English. Yeah. And then, yeah, so I learned a lot from him in the last 6 years. One thing that he also taught me, not scientifically, but he also taught me to drink beer. So that's something that I also like. Okay. And lastly, I am sanitizing. Yeah. Lastly, I would say that I'm still here in TIFR in the lab, but it has been 2.5 months, and every day I feel that I काश आप होते यहाँ पे.
Thank you, Devan. Anup, are you there?
If Shankar is defending.
Yeah, if Ankur is here, basically he should also come in front.
Next slide.
Hello. So the first time, let me tell you how I ran into Sudipta the first time. So after my +2, around that time, my grandmother had passed away due to some disease, having some relation with Alzheimer's and stuff like that. So I was pursuing some chemistry, something so that I can pursue something related to drugs or something like that. So at the end of my BSc, I was looking at labs which might be working on Alzheimer's. Okay, and then I saw there's a lab which is having to do something with light as well as something to do with Alzheimer's. So then I checked for any internship opportunities there, but sadly had missed the deadline. So I mailed him at that point of time, and within 1 or 2 hours itself, I got a reply. So that was the first time I am getting a fast reply from anybody in that kind of scientific regard. And then after that, I came to TIFR. I met him. I told him like I wanted to work in your lab. And then I had my lab rotations. I went into his lab. After the second day of entering the lab, COVID came. So then I was like back to the apartment. We had to work with the COVID. Then we started the lab. But after starting the lab, I somehow got traumatized a little bit. Like there are meetings after meetings. Like every single day, we will be having meetings. There'll be sub meetings. There'll be group meetings. There'll be literature meetings. And every day you'll be getting ideas after ideas. So you would be confused, like, oh, which to pursue. So, but at the end, I realized that this is a good training actually, because you are not only planning something in a long term, but if you get a question, you try to pursue that particular thing. And once it leads to an answer, then you pursue it further instead of making a grand plan at the starting itself. So that's something I think I have learned it from you. And other things are like he sometimes challenges us with his own standards. Okay. For example, let's say if you're going for a trek or something like that, the next day you'll be damn tired. But he'll be there the next day at 10 o'clock looking at who has come there. He'll be there. And he himself would be there. And the other thing would be, so I had gone to a trek with him. He was there, Sumanang was there. I had dislocated my shoulder. We came down. And then we were trying to board the train back. And as you know, in the local train, it's really crowded, right? So we were unable to come back from that station. So we had to go up one station and then take another train back. So at that time, I remember him telling all the lab members to like surround me so that I don't get much injured further. So that was something that I remember. And yeah, so even when we go to the Ganavati trip, I remember he was always having some back related issues. Okay. But the next moment you can see him like riding on a motorboat along with us. But after some time, I think he got some more back issues, but he was there and made sure that he was enjoying along with us. So thank you. Thank you for all the trip that you had given to us and all the scientific journeys. Thanks.
Okay, Ankit. Ankit is there. Okay, Parth. Not there. Okay, fine. So Dev Shankar just wants to read out one message from Shimli, and then we are done with the Biophotonics lab, and then we'll go to the broader community after that. Yeah. Daniel is not part of the Biophotonics lab, I think.
Oh, look at his face.
Sorry, Daniel.
So Shimliti asked me to share this message. So I'm reading it out. Thank you, Sudipta, for creating a safe environment for women researchers like me. Cannot thank you enough to make me independent explorer, be it scientifically or in globetrotting. Forever indebted.
Okay, I apologize. So we'll now go to the honorary Biophotonics member, Daniel first, and then from there. Daniel, you're up.
Yeah.
Can you share your screen actually?
Yeah, I need to. Let me just figure this out. I think.
Yeah, we
see it.
Just a sec, it's coming on. Yeah, I think.
Okay. Can you see the screen? No.
See just a blank white screen.
All right.
What's coming?
Let me try again.
Yeah, can you just try to reshare? Yeah.
Yes.
Okay, but now I don't really see anything. Okay, can you see my screen?
I think what's happening is we are not seeing the presentation actually. I can see your apps, for example, on the side. Yeah. Can you, can you select your?
Is that the one or?
Yes. There you go. There you go. Yeah, that works. Okay.
Okay, so fine. Now you see a white screen, right?
Yeah, I think something happened again actually.
No, white screen is fine. That's exactly what I want. Okay, so thank you very much for making me an honorable member of the.
Daniel, sorry, it's still white screen.
That's supposed to be white. That's fine.
Like the first screen?
Yeah, absolutely.
That's
Yeah.
fine. Sorry.
So I just want to raise your curiosity. So because this is sort of like, we all come as white screens or white pages, and then people put something on it. And well, I've really very much enjoyed joining you. Hi to all my friends, my good friends at TIFR. So I learned a lot actually. So for instance, I didn't know that Kanjan was running marathons. So Kanjan, if I had known, I would not have gone to the Himalayas with you. Yeah, we start with sort of like a white screen, and then we start learning things. And your students, Sudipta, also said that they learned a lot from you. And some students said, I think it was Deepshankar, that he learned how to drink beer from you. I guess that's the only thing I didn't learn from you, because I knew that already when I met you. But anything else I consider important is something that you've certainly contributed to. And I'd just like to repeat a few things for all of us here. And that is, how you spell, how your name and your personality is spelled out by virtues that we all very much appreciate and have appreciated over the last years that we've met or that we've known each other. And we met about, I think, 2013 at this Bombay meeting that Madhu organized in those days. This is how far we go back. So now here's my Sudipta Maiti alphabet. So it starts with being responsible. You're a very responsible person, yeah. And I have like these quotes here. I cannot really read them because there's something from the Zoom in front of them, but you can read it. And so here is your group, and I would just like to say, and we heard all along. Oops, now it's black, right? I want the pointer actually. No, there's no pointer. Whatever. Yeah. So you take the responsibility for your group, and you've done really wonderful. I mean, if you now reconsider all the people who just gave short statements over the last couple of minutes, right? It was really amazing to hear how many lives you've touched, how many careers you have really supported, and how many people really go back and look back at really wonderful times and the lots of things that they learned from you. The next one is courageous. So you're a very courageous person. So we all had several incidents and moments to encounter that. And here is a picture of one of the most courageous thing that I've seen you do. And that was just the weekend before the lockdown in Bombay. And this is a picture which was taken on the Marine Drive. And it was Paulina in the middle and Bumba on the right and yourself playing Frisbee. Just before the lockdown, and actually the police came after us, and they were calling some, I don't know, action or so that we were not supposed to do that. And and I remember this as a very courageous thing because you said, look, I mean, I'm a free person and I can play, and I would like to keep doing this. And this was just the beginning of the lockdown, which I had the privilege to spend at TIFR. And I don't say this in a sarcastic manner. I really this was really a wonderful time for me and Pauline, because I would not have talked to so many people and learned so much about India if I, did my normal sightseeing and scientific part. So this is something I really appreciated. And yes, you are a courageous person. The third one is you are a good listener, a very good listener, actually. And now here, I think this quote that I have is something that I really
Daniel, you're muted now. Or something. Yeah, you just got muted. Yeah, now you're unmuted.
Am I back to normal? Okay. So now this is the quote. Yeah. If we were supposed to talk more than we listen, we would have two tongues and one ear. This is, of course, the beautiful way Mark Twain says things, and then this is also one thing that I've noticed, that you listen to people, and I mean you listen to everyone. I mean, this was here in Bollywood when we had an excursion learning about how to make movies and everything, and the daily soaps and so. So you're a listener, not only in daily life, in science, and that's an important virtue. And I have a feeling the older people grow and the more advanced they get in their career, the more they talk and the less they listen. But you have kept listening, and that is something I really appreciate a lot about you. So now let's see, how do I? So then intuitive, yeah. Of course, it takes intuition. Yeah, it takes intuition to do something. So Steve Jobs here has some ideas of what the intuition is. So this is you trying to get some intuition. We know your sweet tooth, and maybe a bar of kulfi ice cream helps you to get your intuition. But if you look back over your career, and if I look back over our collaboration, there's been a lot of intuitive moments where you said, look, let's just try that. And I have a feeling this could be something important, and so it turned out to be. So thank you very much for being intuitive and share your intuition. Well, then, of course, you have to be persuasive. We all have to be persuasive, I guess. And you are a person who can be very persuasive. And so this is when you give talks, which you always do beautifully, to convince people of the things that you are talking about. And that's very important to do the things that we are doing. Also, here in this picture, you are also in the role of the president of the Indian Biophysics Society. So also, giving greetings to our German Biophysics Society, and also keep in mind that we are all sort of like connected, and we should really share our common ideas and grow together in a world that's getting more difficult to make a living and so forth. Integrative. So integrity is, of course, a very important virtue. So you're a very integrative person. So you have really put people together all the time, and this is also something I really appreciate. And for you, it's not like following any connections or so. I mean, you just bring people together who need to be brought together, and this is without looking at where they're coming from and who they belong to and what country or whatever. I mean, this is something I really appreciate. And I'm not particularly fond of Warren Buffett, but he also has something to say about integrity, which I really like. The picture is from my last day, I believe, at my sabbatical in 2020, when you brought us together again during lockdown, when we were not supposed to, to hang out together, and you organized the cake from Theobroma, as you can see, and which of course Pauline liked a lot, and you guys joined. So there's Koti, there's Ancona, there's JD, there is Sanjay, there's Shunlava, and there's yourself. And that was a very special moment, sort of like, kind of like going back after this very weird time, not sure what to anticipate when I go back, and leaving behind my really friends, my close friends, and people who cared for me, and people who really made a difference for me and also for Paulina. So this was very special. And I remember, I don't know if Sanjay Vatakolanka is in the audience, but after this, he took me aside and he shook my hand. And that is something that, we were not supposed to do by any means, but it was very important, and this really meant a lot to me. Like this gesture, I shake your hands because you're my friend, and we've gone through all these tough things, and this is how exactly I feel about you, Sudipta. So we've also gone through quite a few things, and I think it's very important to keep this integrity over everything. So you are a lifelong learner. So this is you next to Hartmut Oshkinat in our seminars. So you just joined the NMR sessions. Whenever I gave lectures, you stuck around, and this is also a very rare virtue. I mean, there's few people who listen to the to lectures of other colleagues if it's not their method or so. I mean, you wanted to learn, and you wanted to learn about NMR, and I really appreciate it a lot. Your enthusiasm you had, the questions you asked, and also the help I received from you to put it in perspective also for the students who come from the optical background and so forth. Yeah, I have no special talents, Albert Einstein says. I'm only passionately curious. So the M goes for empathic. So this is also a very important virtue. So you're a very empathic person, as you see in the picture. You can put yourself in the position of a frog. I'm trying to put myself in the position of a B, but you can really be empathic, and you are with all the situations. Also, your students just mentioned that, right? I mean, like I think Papa said that you pretty much know the story of each and every one of them and help them through tough times and rough times. And as you and maybe some others know, I'm sort of like in a big crisis, have been for the last 2.5 years, and your empathy and your continuous support is really very important for me. Of course, you're a very passionate person, yeah, and pleasure in the job puts perfection into the work, is what Aristotle said, and you have many things to be passionate about. So this is you in another role of the of the policeman, I suppose, right? A passionate policeman. Again, this is in Bollywood, where I take the role of the villain, putting the gun to Devanita's head, I suppose. Passion, and you are very creative, of course. So creativity goes a long ways. So you're very creative, especially if it comes to taking pictures with your cell phone. So I have a lot of memories. You know, putting yourself into very interesting looking positions, and then almost like asanas in the yoga sense, where you take pictures of us. And this is just one example. And then honesty. Again, you're a very honest person. So this honesty, my family has really experienced a lot and always appreciated a lot. Being honest with us, giving you advice, giving you support, that really means and meant a lot to us. And then I have, of course, the last one is kindness. Now I quote nobody least than Buddha himself. When words are both true and kind, they can change the world. And I believe that this is really true. This is you and Pauline when she was really little, on her first visit to India. And as I said, I mean, my kids love you as a very kind person, and this really, I mean, knowing you makes means a lot to them. So now we have these different colors, and these colors sort of like allude to the you know, personality that you are, and the many virtues that you shared with us. And there's just more than these colors. I mean, this is, as you see, this is a line spectrum, right? And the people at TIFR, some of whom are here in this picture, so the people of TIFR have really benefited a lot. And this is not just the professors, I think it's everyone in TIFR with whom you had the chance to interact. And many of them are here today. But, you know, sometimes you just need to find your people. And it seems like the feeling that you had over the last 20 years or so is just like you found them and they found you. And this has become a really nice and touching story to all of us. But as I said, life is not discrete, as the flame spectrum here, for instance, shows you. Yeah, I mean, life is the world is continuous, but the mind is discrete. Maybe this is true or not. But how to convert this line spectrum into a real continuous spectrum, and what fills the gaps? Well, of course, there is this other person standing with you and has been standing with you for a long time. And of course, in India, it's really great because women have these wonderful kurtas and saris in all different colors, and yeah, and this makes the spectrum continuous. And you and your family, Bumba, and sorry, I don't have a picture from Ankit. This really converts the line spectrum with special virtues and special properties into this continuous spectrum of a very warm-hearted family, a very appreciated family, and people who really mean a lot to me and have always been over the last years that we've been together. And for that, I'd like to thank you very much personally from the bottom of my heart, really, Sudipta. So you've really made the difference to me. And yeah, what can I say? Enjoy the continuation of your journey, and certainly do this along with all your friends, and to which I have the privilege to belong to. So with that, on behalf of Charlotte and Paulina, I say thank you very much also from my group. We love you and we wish you well for the future. And we'll see you soon, I hope. And I hope we are in for a lot of projects. And one of them is to drive down from Bombay to Trivandrum, the southern tip of India at some point. We'll have to do that. And I hope you're still in for it. And yeah, let's do it and enjoy the rest of the day and your symposium and yeah, and even Gokul or wherever your ways may be leading you tonight. So thank you very much. Bye bye to India. Thank you all.
Thank you. Thank you, Daniel. Yeah, I know you really wanted to be here and the scheduling somehow didn't work out actually, but we'll have you here one way or the other. Yeah, thank you, Daniel. So now I think we'll go to the faculty members, but first I'd like to open it to the people who have traveled to TIFR. So I think first I'll ask Professor Hosur to say a few words. Right? Shall I bring the mic to you there actually, or do you want to come up? Thank you. Huh? Hey, ठीक है इधर? Yes, good and fine. Okay. Okay. First of all, thank you for calling me here. Deepan, it's a wonderful moment. And Sudipta I have known from the day he has joined here for so many years. He has been a great person. I mean, I'm very happy to hear all his students, the kind of love he has got from all the students. He is not only a wonderful scientist, a wonderful human being. He has created so many wonderful citizens of India. I know it. I don't want to talk about his research because that's not my area anyway. But I know his achievements. Of course, when he came here, he came with a welcome grant. There was a huge grant with which he could build his laboratory. He not only used it for building his laboratory, he used it for allowing his students to go abroad for attending international conferences. That is his generosity. He built excellent labs. He established the culture of instrumentation here. He wanted to extend this to other parts of the country. He organized workshops, made people to build FCS instruments and take them home. Not just be here, but take them home. So therefore, this culture of instrumentation actually spread across the country because of Sudipta's effort. And now everybody does that. So he built one of the best instruments. Of course, I remember this multi-photon imaging equipment which he built here. We have put that in the annual report of the TIFR in the Silver Jubilee celebrations. So that was a great achievement which the culture had spread. He had a great passion for many things. He always loved people. He loved things. And one of the things which he enjoyed was music. I remember the days when we played Holi, the kind of entertainment we had during these holy times, beautiful music. And he organized tours, and along the tours you will have enjoy. All the people enjoyed with food and music and whatnot, everything. So this is a great personality. So this is something which one has to emulate. I'm very happy to see so many students of his, no matter where they are doing excellent work, producing the same kind of values in their lives. So it is not only just doing science, but also you must have the values, ethical values. Somebody talked about spirituality, but spirituality is all about values. So that is a great thing to have that kind of a culture, spread it out in the society. And congratulations, Sudipta, for having achieved all of this, and all the best for your new venture. We are going to do, you're going to spread that culture further in the new place which you have. Wonderful. It is a loss for TIFR, but a gain for somebody else where he has gone. And I'm sure he will continue to perform extraordinarily well in the same way which he has done here. All the best. All the best to Dipanvita. She has been a great support for Sudipta, taking care of the children. I interact with the children also. I attend food dinners in their houses. So it has been a great moment. All the best to you, all of you, and all the students. Thank you. Thank you, Professor. I request Anindya.
Thank you, Ravi. All this time I was trying to think very hard of funny things to say. I cannot think of many. That is a first, but that is how it is. I knew Sudipta long before I met him, because I was a PhD student in ISCS, and that was the time when he must have been applying. ISCS being ISCS, these applications somehow found their way to a room where I used to sit. I mean, I was not inspecting them. I don't know why they were there. That is where I first saw him, and I was awestruck. Who is this man with that kind of CV? I don't know if I told you this, but that's the first time. Second time I met him was after joining IIT Bombay. I wrote to him and he said, come over. Those were pre-mobile phone days. So I came over and I discovered myself in the middle of one of the group meetings that was being talked about so much. Kanchan was there, Balaji was there. And my arrival disrupted the group meeting. He was gracious enough to call it off. I remember Kanchan's smile. And today, after 22 years, I finally know why. Because he could go for his game of football a little early that day. So now it falls in place. See, he showed me around and all that. Then we met from time to time in conferences and all, but my association with him really started from 2009 when this FCS workshop that has been talked about. I really wanted to be a participant in that workshop. I will not say here why I could not, but I could not. But he organized this conference alongside. I don't know why he invited me, but he did. And I came, and that was really the beginning of a very long association. Next year, it was in Shillong. Shibuda was our very generous host. Once again, I was invited. Then, year after, and that is when our very, really strong association began. Year after, it was in Delhi in 2011. That is when Fluorescence Society started taking shape. And we decided that we have to keep doing it, even though the project was getting over. And the rest, as they say, is history. So we have been doing this every year. We have learned a lot from Sudipta. What I have learned personally and what we have enjoyed immensely is that his tremendous passion of doing something. He has said many times that I want to learn. What is there for me? Sometimes you might feel surprised because so many times you see people going to conferences, giving their talks and going away, not listening to any other talk maybe. And here we have somebody who's already very well established saying, what is in the workshop for me? What will I learn? Why will I go there? So that is something that struck me very much as a very unique thing. And then we have been organizing it many times. So there have been many interesting interactions. Sometimes Sudipta can get really impatient about certain things. It's supposed to be a roast. Nobody has roasted him yet. So this year we are organizing owls. We are inviting people, and completely my fault, this visa thing got delayed because I was sitting on it, no other reason. And then he got very impatient. And then when the thing is, after you submit any government paper, you have to wait. There's nothing in your hands. But then Sudipta kept saying, isn't there any other way? And I could think in my mind, Sudipta trying to get in a lot of people from other countries through the donkey route. Because what other way would it be? So there are many, many stories, I suppose, but there's so many that I'm a little overwhelmed. I'd just like to say that association with you, Sudipta, has been a very, very important it has left a very important mark in my professional and personal life. Thank you very much. I'm very happy that he has joined BITS Pilani Hyderabad campus, because what that really means is that for 10 more years and a decade with Sudipta, that means he's going to do something very new. He's a great teacher. It's a teaching institute. He'll get to teach as well, other than doing whatever he wants to do. There are many plans that he has. Some will work out, some will not. But it'll be a great journey. We're very sure about that. All the best for that. Thank you very much.
Thank you, Anil. I request Shobhan, actually.
Yeah, it's always been a pleasure to talk about you. Again, what you missed in 2009, I actually gained. So that's where we started. I still remember those days of a PhD when we were doing, and we learned that, some stalwart has joined TIFR because from Hochstrasser's group, did PhD and so on and so forth. But then the chance of meeting him was that time when we came here. And
28 days, I remember, 28 days total. 28 days, we just had the fun. So I think today I'm feeling like we are having a alumni meet of that, Jenu is here. I'm only missing Suman, I think. Yeah, Suman is missing. So I believe we are going to have it a big, next one full week of this FCS again. What I really realized during that time of 28 days, because I was really directly involved in that particular project, directly learning as an outsider from TIFR. So see, at that time, this kind of culture was not there, because that senior professor is spending 3 weeks or nearly 4 weeks time of his to just train outsiders. You can always train your own students. That's not a problem. That's always you do. But you just train the outsiders and making that, notebooks and the manual. I got it this time also, that same manual, okay? So that manual, if you look at those manuals and everything, so you know that how much effort have gone to do those things. That was something very, very important for the Indian scientific community. I think that was missing for a very, very long time. When I first, heard his lecture, obviously I met him for the first time when I actually came here. Before not, I heard about him, but that never met him. Once I started listening his talk, I thought, okay, this is the person that I should have the more amount of, resonances in many, many ways. And that actually happened over the time. And I feel that, in many times when, especially during this organization of the FCS meetings, we have shared in many, many things that what can be done and can we really do it the similar way that what we have done in 2009? And that was a fact which will remain. And I believe that we'll have much, much more, possibilities to do a very similar thing, because now you are independent, different place, and maybe bigger opportunities might actually come also. So I believe what we learned as a whole, it's not only me, also my student, that is Sachin, which all of your friends in that way. In fact, Sachin has even learned a lot of things from your way of doing things. I remember because Senthil was talking about these things. I used to call Sachin at 12 o'clock in the morning, that Sachin, are you coming to the lab? Okay, and then would not come at 1 o'clock or something. But then after doing this 28 days of workshop, he was totally changed, by the way, because of that kind of a culture. He thought that okay, this is the way. Because we used to work probably 2 o'clock in the night, in the morning, and then would have a cup of coffee, and then again go for something, and then the cricket match. So that is a big way change, not only me, but also many other, next generation in many ways. So thank you very much for all those things. And I believe that, we're going to have it anyway in many other, positive input from your side. And he's full of life. And I believe that everybody should follow and, admire in many ways. Thank you very much.
Thanks, Shobhan. Yeah, Samir,
Hi, good evening. So thanks JD for inviting me here. I think it's wonderful. And I told for Sudipta, wherever I am, I have to come. So Sudipta has that kind of personality. So I met Sudipta, I think around 2002, and I just joined David Tableau's lab, I think around 4 months. And Tableau, I think, who is discoverer of protofibers. I mean, I will tell you that there is 2 professors who discovered the fact that oligomers could be toxic. So one is the Tableau, another is Lansbury. And Tableau one day morning is saying, Samir, one very smart, talented India researcher is coming. I was saying, oh, David is saying talented, very smart Indian researcher. Who is this person? So Sudipta said, I was mesmerized the talk at Harvard Medical School. And I still remember I walked with him from Harvard Medical School to railway station. And then I was stuck for last 22 years. And all the time, he is my recommender. Any problem I face, Sudipta is the person. All the time, he's supportive. And what I admire, how he can all the time smile. I never seen him angry. I don't know, so what he do at home. But outside is like all the time smiling. I mean, all that. So anything, I think few days back, I came to his lab. I think, I want to develop TARF. Oh, it's not a problem. I will develop. I will make for you. So he asked immediately one of his students, can you build? So then one day I called him that how much it cost. He said 40-50 lakhs, and he's so excited. He's excited more than me. And I was discussing in the lab then where I can find the fund. And my student is saying, do you have any problem to solve with TARP and where you will get the money? Then I call Sudipta, no, I'm not interested now. But he have so much kind of want to support. And I think another thing I would like to mention that after joining here and at IIT Bombay around, I think 2009 January, I met him. And before that, all the time, I was in touch with him, what I was doing from 2002 to 2009. And then Sudipta was saying that, let's start something else here. So I think a couple of meetings we did in his office, and we started biophysics position. So basically our goal was, Sudipta was very fond of that who are other people there next door? Can we collaborate? Can we help? Can we take help? So he has amazing capability to, kind of kind nature to help others and collaborate. All the time, he always, if there is somebody is coming, inviting, even making a phone call, Samir, there is a guy is coming, can you come and attend the talk? He don't have benefit. He just want to support all the younger colleagues. So thank you so much, Sudipta. So one thing I want to be like you, like energetic and smiling all the time. So I don't know that what resource you have. And hopefully that, beats Pilani, Hyderabad, and I will say, Somu Mukherjee is a very smart guy now, I believe, that, that he choose someone who all the time smile and very smart according to me. And during your age, I want to be like that. So thank you very much.
Thank you so much. Okay. I request Chandrabas to say something.
Actually, I didn't think JD would allow me to come here. Because when Debanjan told me that we were going to have Sudipta's conference for Sudipta, so I said, why I was not called? So I realized that it was a close meeting for you, and I have not had direct interaction. Yeah, I'm part of it. But interestingly, today, when morning Anindya called me and told that you're going to come directly to here, I was very happy. And again, there was some issues because the driver showed me the ceiling three times. He took the wrong U-turn. So I ended up spending a lot of time on the ceiling. And when I reached TIFR gate, and though he has actually instructed there is somebody coming from with name Chandrabas Narayana, and then he looked at everything and he's not allowing me inside. He's trying to reach you out. Stop me. So I was sure that I'm not going to be part of this one. But jokes apart, I'm extremely happy. Thanks, JD and Anindya, for making it possible for me to come and say things. But I don't know whether Sudipta remembers in 1995 is the first time I met you. You won't remember because I had just joined Cornell. And Manish, who was in chemistry department, had actually told that there is a Diwali festival because I just joined. Okay. And Sudipta had joined in 94. And already, as you know, Sudipta actually is a star there. I go there and even today I can remember your face because Babu Mashai was standing there, fully dressed. I will tell you why he couldn't recognize or remember me, because around him always there is a crowd, right? So he had more beautiful things to look around than me. Am I correct? That's right? So yeah, that's one of the reasons why he couldn't even recognize. I had a beard and I was very lean at that time, and
famished because I had not known what to do in corner. And that is the first time I met you, but your face still was very much in my mind, because when I met you in TFR again, I could recognize that I had met you before. We didn't actually interact because he was very busy with the chemistry department. I was in the materials and engineering department, which is at least about 800 meters away or 1 kilometer distance away. So we couldn't meet regularly because I used to be in the chess, which is down under the earth, other side. And I used to spend a lot of time there. But we both left Cornell at 1998. And I came to JNCSR and he joined in TFR. But in 2010, when Madhu called me for the colloquium, is the time when we actually came to know again. And we had a nice interaction at that time when I had spent time here. But then in 2012, suddenly Sudipta calls me. I was in the office and he called me on my land phone and said he started explaining to me about the FCS. And it was very fascinating because he was actually so passionate as usual. He was telling me what this particular conference is. And he told me one of the things is that you have to stay morning to night. You cannot get escape. You have to spend time. You have to actually do hands-on and all those things. But he said that now it's time that Raman has to be introduced into the fluorescence community, because that is becoming very important. And he said I would be the right person to actually start doing that. And it was nice of him that he thought of me as the person for Raman. Anybody could have been actually selected, but I'm very thankful to you because I got a huge lot of students and faculty members who are really passionate about this kind of FCS. And I wouldn't have been able to be part of that if he would. Very fascinated by the time he spends on actually organizing it. And that day when I had met him first, that is exactly what I had seen, that whole function, though I don't like the ABCDs there. I somehow didn't like them, but I liked you very much because you had you were actually managing the whole thing, and it was wonderful that. So you have been an excellent science communicator, excellent person who actually motivates people, makes people think that they can do everything by themselves and build it. So we also, I mean, I also build my own instruments. So we actually hit upon a lot of things where we learn from each other. And it is always a pleasure to always listen to you. Something new comes up in your talk and something new ideas come up. I always follow your papers, even though we are not in the same areas, but we do actually have a lot of things in common. And it has been a wonderful time spending. We wrote a proposal, actually. You remember, with Balaji, he left just now. Three of us actually wanted to have a sensor. It's an interesting thing. Sensor in the toilet and find out the diseases you have, right? Actually, we had proposed this, and I think we should work on it because it's a wonderful idea. We didn't get the fund, but then we all got busy. But it's a wonderful idea. Actually, three of us should get going, and this is something which is now people are actually trying to actually look at it. Can we identify early prognosis for diseases which you may be having? Because today non-communicable diseases are much more in the fray, and people would be that's the best place to actually find out and it is not requiring an FDA approval very much because it's non-contact. So we should work on it, and I look forward. I was actually surprised when I heard that you were looking to move out of TFR, because it's somewhere nobody wants to leave this place, right? I love coming here and interacting with the excellent people who are there in the TFR. But I think, as earlier speakers told, that it is a loss for TFR, but gain for BITS Hyderabad. And I would definitely like to come to Hyderabad and see you there, and continue this association as this friendship I always cherish. And I wish you all the very best and wonderful time for next innings, which is going to come for you. Thank you.
Okay, I'll request Gautam, do you want to say something? Okay, so I'm the real first real outsider to the area, but I'm part of Sudipta's family in a different way. Let me first explain when I met Sudipta. That was 44 years ago, I think. That was 1980, when I met Sudipta at some felicitation ceremony where, because of his stellar performance in his secondary exam. But I don't remember much of that thing, except that we have a photograph proving that we were both there. After that, we basically became family when I got married, because Sudipta is related to my wife. But at that time also, I didn't meet Sudipta. And then Sudipta joined TIFR, I think in 1998. And the first memory that I have of Sudipta, one of the first memories, is how Sudipta is handling his boss of about a year old. That's his son, Aniket. They were staying at the guest house at the time. That was probably the first week after his arrival. And Aniket is saying this keyword, up, down, which means that he wants to go up and down in the lift. So here's the stalwart professor who has just joined, and he is listening to the command of his one-year-old boss and going up and down the elevator. And I was witness to that. So anyway, many things have been said to Sudipta. It was wonderful to hear all the students saying that. Let me tell you some of the things from the other side, how it looks. Okay, so many of the students mentioned, lab meetings, sub meetings, literature meetings, group meetings, and so on and so forth. So once Sudipta's family and our family decided to go to the Andamans together. This was an LTC trip. Andamans is the farthest point. So of course, that's a very natural choice for all of us. So it was in the air. I like to plan not very early, but somewhat early. Okay, so the idea was that Sudipta and I will sit together and plan it all out. Okay. Now, it's, of course, before dinner is difficult because there's some meeting, perhaps a lab meeting. After dinner is a little difficult because there's a meeting, maybe a sub meeting or something. And it went on and on and on for, and then eventually, of course, after some heartburn, we sat together. And Sudipta, with his amazing efficiency, I think within an hour, it was all done. All we had with us was a Thomas Cook list of hotels. So he used that, and he sort of fleeted around from one website to another website, choosing the best website to book the hotels from, and everything was done, including the boat.
So now I also realize I can connect this to one of the things that Parijat said, that, so we had nothing before that. And then there's this filled sheet of all the hotels and all the bookings done. So it's like this L-shaped room, which was completely empty. And within a few months, many things one could say. Sudipta is really a brilliant lecturer. People who have heard his talk, they know. But because I was family, I was privy to listening to some of these lectures after dinner at his place or at our place. And so no, even science talks, etc. Yes. For example, there was a talk on Alzheimer's. Okay, probably some continuation of what he said here. So we were at his place. But in addition to listening to the talk, we also had the benefit of glasses of water of various kinds. And it was all really wonderful. And even with all that water, I still remember, what he had said about the so, as Professor Hosur said, that it's a loss for TIFR that Sudipta is leaving us. I do feel that, it's a shame that Sudipta has to leave this early, TIFR. No doubt, he is going to do great stuff wherever he goes. So it's he will do equally well, but it's a loss for TIFR. It's certainly so. Anyway, I wish Sudipto and his family all the best. We'll miss him, of course. But I have seen the place where he's going to be. So we are certainly going to be there very soon. All the best.
Thanks.
Yeah, so I Maiti. Anyway, so I had many interactions with Sudipta. The first time I met him when I joined in 2001 in February, I think 16th February on that day. So when I joined, of course, Sampath was looking after all the things. And on the first day itself, he made sure that I know the entire TIFR system. And then he wanted to ensure that I don't have any problem in my arranging or organizing my personal things. So he thought that he should introduce some of the people whom I could get help. So one was MK and another was, I think, Devu Goswami and the other one was Sudipta. So I remember those first day very, very, very well. And somehow, I mean, as a typical Bengali, I also follow like anybody who is senior, I used to call Dada. I mean, normally that's our tradition. But Sudipta is someone I have never called him because from the first day itself, I feel so close and he's so friendly. So I always called him by name. Somehow it has never happened that way. And I would enjoy, like to be like that all the time. We had many, many interesting time during the entire period here. For example, we had potluck parties. I think there was one very unique one when we were in Raman. So, I mean, people used to cook something and come outside and play games and so on. Also, I mean, this pandal hopping during Durga Puja and so on. So we really had a great time.
Even I remember like this holy time, for example, initially, of course, I used to come out to play, but then later, because of some allergy, dust allergy, I and my son, both we had, so we cannot really tolerate too much. But almost every year I see that near my door, Sudipta and Dipanita, they are there with this Abir. So it's really great. I really enjoy your your friendship all through and all the parties that, and the stories associated to it. The two things which I think Daniel also mentioned about it, which I was very, very attracted with, is his clarity. I think anything that you talk to Sudipta, he's so clear. Even when he was explaining what he was doing, I also at some point was thinking that I should probably do the same thing and join it. It's really, he has a great passion for doing things and he's extremely clear about it. Even one day, I think during the morning walk, I think Sudipta was walking with Aniket and I was also walking. He was explaining how to solve a problem through predicting things, like you predict something, get a solution, and then how to go about it. So, at every level, I think he has been extremely clear. And the other aspect which I felt that he never was afraid to speak loudly whatever he feels very strong about it. So he has been, really vocal and try to pursue things till the end is achieved. So it's like that. As a chair of the department, I think he has got many new things into it, even for the hiring process. And I think he has many innovative ideas, which he tried to implement so that the institute benefits. I'm extremely sad to see that Sudipta is leaving. And since I feel very close to Sudipta as a friend, I also feel that now it's my time to think about it. But anyway, so I wish you all the best. I'm sure BITS Pilani Hyderabad will benefit significantly by your presence, your personality, and also your great teaching ability. All the best to
Thank you, Kalada. I just wanted to tell you that we are running completely an hour late. So, so just I request everybody. I know there are people who want to say a few things, including me, but I will take it out right now. But I want to call few people who have been waiting. Kedar is one, and then Maitreyi is another person, and then I'll give you something. Okay, please.
I'll I'll keep this very short. Yeah. So I'll keep this very short. I came here in 2004 and I was allotted a flat in the same building as Sudipto. And I remember, it was all very new for us and we had just moved back with a 8-month-old baby and it was kind of a stressful time, like many people who move. And among the first people I got to know was Sudipto as a neighbor. And such was his warmth and such was the friendliness and inclusiveness that very quickly we felt at home. And I remember the first two New Year's parties we spent at his house. And, these small things make such a big difference. Very quickly, I started thinking of this as my home. And I remember Bumba was probably the first person our son played with. And so much was the warmth that within a year or two, when our second one was to be born, and I was in a sort of a panic thinking, now how do we come back from the hospital? The first person I could think of calling was Sudipto. So Sudipto was actually the chauffeur who brought our second son back from the hospital. And, this kind of small touches is what makes TIFR special. And it affects everybody's work as well. If you have such warmth around you, you feel you belong and you really start doing what you can do yourself. So I really cherish those 2 or 3 years we spent in the same building as Sudipto. And I think people in BITS Hyderabad will soon find out what a pleasure it is to have him around.
Maitreyi.
Yeah.
Sudipta will have forgotten, but I met him before I actually joined TIFR because I was here after I'd received my offer letter trying to figure out if I'll actually fit in here. And I was talking to our then chairperson, Professor Veronica Rodriguez, who's no more. And she said, you should go talk to my colleague in chemistry. He builds multiphoton microscopes. So I went to Sudipta's lab. And I think the first thought that struck me was, is this really a microscope? Because I'd never really seen optics laid bare on a table. And I was like, where's the stage? Where are the lasers? Because I was so used to seeing things in glossy boxes that all our friends here, commercial microscope companies make. But it also prompted me to sort of, or it made me realize that it's important to know the inner workings of the instrument you use. And I think after I joined here, I actually brought some of the fly embryos. Senthil was a master student then to see if we could do some imaging. We weren't very successful because of how customized your scope was. But I think I learned a lot about what one needs to know about the instruments they use. Besides just buying them and being users, you need to sort of know it inside out. And I think that's what I really learned from Sudipta. And I think after that, he's been really helpful in all the sort of microscopy decisions we've made in the department. And we've sort of really valued your advice and expertise and help in troubleshooting. I'd also just like to add that I think in addition to building microscopes, he's somehow helped build bridges, maybe between departments, but also build communities. And particularly, I think when he started biophysics Paschim, I think he included us in it, even though, I wouldn't sort of normally be included in a biophysics community, but I think just because we were doing cell and tissue mechanics, sort of included us as part of it. So I feel really thankful for, building inclusive communities and, including peripheral people in it. And I'm sure we'll keep pestering you for your advice on many things in the future. And I wish you all the very best.
Maitreyi, fantastic. Thank you for coming out and speaking. GRK, you get immediate, just a quick thing, GRK, please.
Yes, just 2 minutes.
I know.
So I am actually waiting to listen to Sudipta. So I've been waiting for a long time. I think the chair probably sort of was too elastic, let me say. Now, so my connection with, after Gautam, I probably know Sudipta the longest, but I don't know who is this Sudipta Da. But I'll talk about this Sudipta, right? So the only Sudipta that I know very well. But all that has been said, accepted, approved, the referees are very pleased, publish the paper. Perfect. I'll tell you something. He also told me a bit of roasting was missing. Everybody was just going, you're so great. Sudipta was squirming in his seat. I've seen it just sitting behind him. So you never got a chance. So, but you will maybe at dinner time. So just 1 more minute. So he also told me about his toilet project. All right. Outside the toilet. Now Chandrabas. So I want to say one thing. I think it is time you guys strove harder and deeper into the toilets. And I don't know why you need anybody's approval for that, right? In spite of the times we live in, and with the DAE hovering around everything we do, breathing down our necks, etc. And so that's one thing I just thought. I have lots of roasting that relates to his undergraduate days. We were in the same hostel, and as young people, you all do interesting things that you can't talk about. And he has a famous friend called Manindra Agarwal, who all of you know very well, the prime numbers guy. And he will tell you the stories about Manindra Agarwal, which are extremely interesting to hear. You should hear them sometime. Now, having said all this, I think it's great that you've done so much. Every word that's spoken has lots of weight. I could see how strongly people feel. You're not only multi-photon, you're multi-people, multi-this, multi-that, multi-everything in the world. I think it's really sad that TIFR did not keep you, because I think it's a sign of the times, and I'll be very honest about it. It's not good for this institution that we let go of talent that is so rich, that has given so much, and because of something we don't stand up for ourselves, we let these things happen to us. And I do see that this is going to affect us more and more in the future. This is not at all to my liking. I have to say this. But Sudipta, wherever you are, you will be yourself, but TIFR will not be the same without you, right? So thanks for everything, and everything that has not been spoken about here, everything that's been spoken about here. Now over to you.
I hand it over to Ravi.
I thought I was fired basically, but I've been put back into action at this point. Yeah, I had like some innovative ideas, but that has been shot down right now. So I think we will have to close this. We are overwhelmed by everybody. Everybody wants to say something. You're overruling everything,
Because I represent a group, so just made a disclaimer that I was not a PhD student of Sudipta, never attended his graduate course, not because I didn't like it. That year he didn't give any course. I didn't do any rotation with him. I didn't have any paper with him as a collaborator, but still I'm here. That says a lot, because what I call Sudipta's outer sphere influence. So what you heard is inner sphere, and the guy who represents the outer sphere. And you have been a role model for all of us who joined around that time, young, dynamic guy. And for many of us, you are not Sudipta, you are Sudipta because of the way you pronounce your name, right? And if you are not a scientist, I can safely say you are a very good CEO of a company, or a motivational speaker, or an auctioneer. I still remember just one anecdote that once you did that for us for our hostel auctioning, and that year, Saurav Ganguly had stripped of his captaincy and Rahul Dravid was given the captaincy. In the hostel auction, what Sudipta did was he put up two posters, one of Saurav Ganguly and Rahul Dravid, and he said that whoever wins this poster can put up in the newsroom, and you can see the crazy fight among the students. And that year, we collected the highest amount of hostel funding. So, and the other thing Sudipta did is that the day I joined TIFR Hyderabad, he was there and he was organizing that conference. He came to know that I joined. He held my hand that come, we're having a banquet and this is how we treat our newcomers. So that's how he is. And that's and many things to tell, but I didn't tell him in person. And moreover, you are coming to Hyderabad and I heard that you are going to have a satellite lab in the Hyderabad campus, TIFR, and I'm going to be a neighbor. So everybody's lost my gain and I'm happy about that.
Okay, I think by popular demand now, we demand that Sudipta say something. No. I am the chair. I am the chair. I am the chair.
Not by him. You need to sit and go ahead. You have 2 minutes to roast me, not more than that. So that's I have something.
Okay, so quickly, I would like to state this that the first time I, of course, saw you, it was as a VSRP student, and of course, I saw Balaji and Parijati and running with you all around, a young faculty, absolutely impressive to talk to, and I think I already told in the morning that how it's easy to talk to you. One of the things that I wished was this VSRP program had this option of joining as a PhD student by clearing an interview. And I, of course, never thought that I would be selected. But if I were be selected, I wish that it was Sudipta who would pick me as a student. And I still to this day feel, of course, my PhD advisor is Charles Dismukes, but I still wish that if I had that chance, I would have absolutely worked with this guy. who motivated so many people around him and was building equipment with so much of excitement, running around the lab, finding a small optical part and telling, let's go, Balaji, let's go, let's fix this. So I have never seen this kind of energy and passion. And I still to this day, as a colleague, I'm mesmerized by his energy. I'm mesmerized by his way of picking details in the science. And Sudipta, I think you have motivated eternally me, and I will have more things to say after some water has gone in. And I wanted to say one thing, that this name, I don't know, I love this name that I've been able to come up with, a halo of memories. It encompasses everything that Sudipta does. Encompasses everything: the optics, the neurons, the brightness, the glow that comes behind from his head. It encompasses everything. So I'm so truly grateful that Deepa gave me this opportunity. So thank you. Yes. Right. Right. But without further ado, I think let's Sudipta speak. As a department, we have to felicitate him also, and we'll have to take a picture. So let us do this, and let us have a good time in the next 15-20 minutes. So thank you very much.
So you're going. So you're going
Yeah.
Robin Hochstrasser. You're going Robin Hochstrasser.
I'm going Robin Hochstrasser.
Yes.
Yeah, so lots of things. Sorry. That should be fine.
Yes.
Yeah.
Who's going? Sanjeev.
Yeah, okay. So thank you so much for all those nice words. And I was just saying that you guys are old enough to know that has to be taken with a pinch of salt or a fistful of salt. So that's all right. So, but it's really nice to be here and to have this. And I thought my primary duty of what I'll do is actually just thank people. And my primary duty are to myself. All of you are here, all of you are friends, some colleagues, co-workers, some friends, colleagues from other places, but it's my students that I have to thank throughout the years, for the past 26 years. You see, I mean, science is like playing a game, okay? When you're a kid, the games are defined for you. In the summer, you play football. In winter, you play cricket. And you have a bunch of your friends. Everybody knows the rule of the game, and you go out and play. That's fine. When you have your own lab, you've got to define your own rules. You've got to invent your own games. And that becomes a little difficult, especially the second part, that you have to motivate the players, who are your students, to play the game well. And inventing the game itself has difficulties, because you have to come up with things which are consequential. We are lucky as basic scientists, especially I was lucky to be in TIFR, that you could pretty much define the game. I mean, nobody really questioned you. The overall thing, of course, had to be something, but the details nobody questioned. But that gives you the responsibility to come up with things which actually makes a difference. And when you're young and, young 32, 33-year-old,
and you believe you can change the world. Okay, so you have to have that kind of game invented and tell people like Balaji and Parijat who joined the lab first with wide eyes that you can change the world, we can do things which are really consequential, and actually show them that it can be done. And so that became confident people. This is difficult. So, of course, there are two ways to play the game. The first way is slightly easier. You take up games invented by others. Okay, so still new games, not like something has been invented 50 years ago. New games, but invented by others, typically in the West, typically by scientists in the Western world. But you still have to seek an angle which is somewhat new. And you have to make sure wherever you are that you have to believe you can outdo the others in little corner that you do. And the second one is much harder, that you have to come up with your own game because you have now looked at science from sort of zoomed out view, and you realize that there are some holes here and there, and come up with games that can be played there. That's harder because not only because you may be making mistakes, this is a much harder game to play, because nobody has played it before. And also, even if you are right, it's very difficult to make other people means the editors and the reviewers, see your way that there is something very significant here. So, as I said, in TIFR, you are lucky. So, I have been lucky to sort of play the game both ways and come up with things. But the game, of course, keeps changing. I mean, 26 years, you cannot be playing the same game. The game kept changing. But if you look back, you realize that it's actually the bricks coming up layer by layer. It's just that because people who are the first ones, Balaji and Parijat, would have built a framework, built some expertise, built some capabilities. The next group built something else, but they are also depending on this, both the expertise, the knowledge, the confidence in the lab, that in this lab we can do these things. We may not have done this before, but we can do it. So that kind of thing, there is also a continuation, even if the game changes. A bit like building a building whose plan keeps changing, but you have started from ground up. So this is what it felt like. And the people who really deserve the thanks and your gratitude are the people who are laying the bricks with you. And again, those are the students. So I thought today I'll just take the chance to make sure that I thank the people who have dedicated 5 to 6 years of their lives, completely dedicated their lives to that, except for Kanchan playing football and things like that. But, or Dev Shankar actually attending group meetings while playing cricket. Yeah, so all that is, except for those little things, they have really given their lives to you, and with the belief that we are doing something that is significant, and that's a must. You have to believe that. And so I will go there and start. But I couldn't do it as well as I should have because I've been sick for the last 5-6 days. So I just asked people for their pictures. Whoever sent their pictures, I put a little thing for them. Some people haven't been able to, but that's okay. So the good thing about what happened? Oh, I didn't share it, is it?
No, but your computer is not connected.
No, but I'm on Zoom.
Oh, so
I'll just have to share it. Somebody will allow me to share it?
Yes.
Okay.
So
Share. No, this one. Okay. Okay.
It does not affect it here.
Okay.
That is in your computer.
Oh, I see. Okay. All right. So, of course, you have some benefits. So all of this after 26 years, as I said, some sort of structure gets made. There are some peaks, some valleys, etc. But overall, there are other benefits, and we'll start with this. This is this picture. This is my current lab, except for the guy in the front. The point is that the real great thing about being an academic scientist is that you're always 20-something. Always. because that's the people you spend 12 hours a day with. So you imbibe everything, what's the new trend that's in, Facebook or whatever. You get to hear all of that. Who are the new rock artists and all that. So, and you get to be a kid. And this we get to do, of course, every year, at least once a year, great monsoon treks. And I thank first the people who are still here. That's Ankur, Ankit, Devshankar. Back of me is Anup, and you have seen them, all of them here, and they're sitting here. Of course, that being a kid is addictive. So some people, 15 years after they have joined, come back, and the guy in the front is Suman Nag, who is a very successful entrepreneur in Silicon Valley, came back and said, no, aren't you guys going for a monsoon trek this year? I want to join, because he was visiting India. So we are there. So, but let's get back to how people who laid the bricks. There is Parijat, of course. And I remember, sometimes I have to apologize. So apologies to Parijat because I made her cry. Why did I make her cry? So I said one day, so look, Parijat, you have to build this power supply. Parijat was a chemistry student coming from Bengal, and she was very good in solving all of things that are in the textbook. But outside of textbook was a nightmare. She said, no, Sudipta, this is not something I do. Somebody else does it. I said, no, you have to do it. The power supply, I can tell you, and I will explain how to do it, but you have to do it. And she cried, I remember the day. But she then made a power supply for a long time. I think it's still there on an upper shelf, and it worked perfectly. So that's a power supply of the fluorescence correlation spectrometer. She built the spectrometer in BG33, one corner that was given to me on a little tray. And we had our first thing, the fluorescence correlation spectrometer built. And that was the first brick. Scientifically, he started the question about amyloids. What's in the conformation of the oligomer? That was a big question. So there's the game here is defined by the West. Yes, the big question, as I think Samir asked, Samir said, referred to, is that oligomers are toxic. And the question was, why are they toxic? So what is the being a biophysicist, if some property is there, it must be related to its structure. So the idea is, what is the structure of the oligomer? And nobody knew, and nobody had a clue how to get to the structure of the oligomer. Over the next 15 years, we'd be working and solving that structure of the oligomer. The first step was the fluorescence correlation spectrometer, just to look at something growing and aggregating. So, but this is not a science talk. So I'm still very much in contact with my first student, Parijat. This is, I think, taken last year. She also visited us this year earlier. So we keep talking, and we keep talking about that day when she was asked to do to make a power supply. Then comes Balaji, who was sitting over there, now left. Balaji, of course, said that I did that, explained that, and he couldn't get it and all of that. But I was a bit scared of Balaji because he would ask a question, what, but he would not stop at one part. Balaji was, what? So I was always scared of that, because that means I've completely failed to explain that thing to him. So Balaji is what, but he was wonderfully gifted. And these are my first two graduate students who joined the lab together, because Parijat was a year older and I came the year Balaji joined. So Balaji and Parijat sort of joined together to my lab. And the other big thing, so that fluorescence correlation spectrometer, of course, was the first one built in India. And there is the multiphoton microscope that Balaji built. That was also the first one built there. And we had great goals for there. Can we image serotonin in neurons? That's something Vidita and I kept talking about. Can we observe the effect of drugs, LSD and things on serotonin levels? And Balaji showed this picture and said some nice things. I'll tell you what really happened. So I didn't know. I thought Balaji liked his time in the lab. And, we spent 6 years and we kept good touch, and we have also always regular in touch. But then about a year ago, he took me to his lab when I was visiting Bangalore, and I realized that was not quite true. So he showed me this instrument that he had fabricated and says that it reads, if you think about some problem deeply, try to solve it, then there is much more energy that's consumed by your brain, different areas, oxygenation. So there is this ratio of the two oxygen peaks, and it picks it up and shows you the brain activity. And they showed me some recorded stuff that this kid came in, or that guy came in, that professor came in, and some brain activities. And then, I didn't know I was being led into a trap. So I went there and put this up, and this is the guy Harish. And he looked at it. He asked me, gave me some task to do something, move this and that. And then I kept looking at the screen, and I couldn't see much of those fluctuations. And this student turns to Balaji and says, no, it's reading in what's inside your skull, right? He says, Balaji, there is nothing there. So they realize that all those good relations for 6 years, this is what I was being paid for. Okay. So then, of course, came Kanchan, and Kanchan vacillated between joining string theory or joining biophysics, string theory, biophysics. And as he said,
the right strings.
yeah, okay, amyloid and strings. And he started coming in, but he said his own stories. I still remember that we need to work in nanomolar level in FCS. It's too sensitive. We are looking at single molecules. So I told Kanchan, look, this is this dye, this is the molecular weight, and you make me a 10 nanomolar solution. It almost blew the APD, the detector. Turned out he made 10 millimolar. He was wrong by 6 orders of magnitude. Only a theoretical, sorry Gautam, only a theoretical basis would be wrong by 6 orders of magnitude. You only put a fistful of rhodamine B in there. Then, of course, came Sanjeev, another physics student. He is the most unique person I have ever had in my lab. You can see, you can tell he is unique. Okay, so Sanjeev, of course, he didn't look like that. He looked like this when he was a student. Unique in every way. Unique in his abilities. The most gifted instrument maker I have seen, okay, at least in TIFR or in India. And he could think of anything. I know I'll think of, okay, so how do I make a more efficient collector in a direction, we call it the non-epi direction. It's a non-conventional microscope. And he came up with the front part of a flashlight, and it had a bent like this, and showed me the calculation of the angles, the solid angles, and he was absolutely correct. That actually gets you very close to a very good collection to the thing. So he was that kind of a guy. But he, of course, became a completely transformed guy with the right kind of liquid in his hand, but he became very enjoyable. I still remember him ragging Madhu's then fiancée in a restaurant that we just met. We were there separately from them, and after about 2.5 hours, I can see that Sanjeev is hell-bent on explaining. Sarovar was some social scientist. So, nay, 3-dimensional integral. This is just a triple integral. So, aise hota hai. So, she was being taught triple integral after 2 hours of our dinner, and Sanjeev would not let go. Now, another unique person is in the picture, actually. Some of you would recognize, half of him is there. That's Krishnan. So, K.S. Krishnan, he is yet really another unique person. The two of them, I don't know, one person, really unique guy, recognizes another. So, both were there, I think, in our place for something. And yeah, so this is Sanjeev, and Sanjeev doing things. And Sanjeev has remained a very close friend. And thank you, Sanjeev. I don't know if you're listening to this. And he has always been fun. He's always extremely generous, to the point that, generous to others, his friends and all that. You interact with him for a day and you will realize. So that we used to keep some lab money in a packet, because you needed to buy things. Somebody needs a 500 rupee thing from Lamington Road, because we used to build a lot of things. So the idea was that you take the money You take the bill, you encash it and put the money back, so that there is 5,000 never finishes. 5,000 at some defined period kept finishing. And so we were wondering what's happening. Then Sanjeev came in one night, can I talk to you? Because my friend, somebody named Mohit, actually is in trouble, financial trouble, this and that. So I had to take that money. Again, some other friend would be requesting, requiring money, etc. So he said, I have borrowed, I'll give it back to you. And he borrows from his friends, not for himself, but for other of his friends. Very unique person. So by the time he graduated, I think he was at least 1 lakh or 2 in debt to all his friends and to me, etc. And I said, Sanjeev, you have to go abroad. He was thinking about job in India because you have to pay back your debt and you have to earn in dollars and euros. It's so wrong. As Senthil will tell you that when he went to Germany for a postdoc, it's just that the same figures remained. He was still, 50,000 or something in debt, but now the data was in euros and not in rupees. So came Banka, very straight guy, and he also put a brick, which is he started the TEM of fibrils. His Banka about, I think, a week or 2 ago. He's in Hyderabad, so I met him. And Banka is one of the straightest guys and always in smile and did quite a few wonderful things in the lab, including some nucleation theory, which Kanchan started. And he and I had some wonderful papers on that. Then, of course, Senthil, as I said, that he seems to be doing wonderfully as a Monash professor, but he seems to have done all those hard work only after realized that one should do it only after he left my lab, because this is what he did in the lab. No, I'm joking, because he's the guy who built the first turf machine, and we needed a 2-channel turf machine, and he thought of something, and he asked me to get little magnets, toy magnets from Aniket's toys, and he built a divider, a dichroic divider with that so that we could image 2 colors. And that was the beginning of another brick that he laid, beginning of single molecule imaging. He didn't do single molecule, but the turf thing. So, and this is the time that the lab moved from the Nathan Lands to 3rd floor. And Senthil, you can see there that Shuman is one of the most versatile characters. I would not say that he was better than everybody else in this or better than everybody else in that, but he was actually a complete package. You ask him to solve something, do something, he will do it. He was somebody who started the new thing, which ultimately this year, one of my last students, Arpan, finished, which is how do amyloids interact with the membrane. He was the first guy to start that. He was called by a US professor in Purdue. I was contacted. Can you teach us? We have this machine, commercial machine, FCS. We can't make head or tail out of it. Can you just collaborate and tell us how to do it? So he invited me. I said, look, I don't have really time. I'll just go there. But Shuman can do it. And they have other things that we could work with. They knew how to grow membranes. So Shuman stayed there for 2 months and got some wonderful things done with the new things that he learned there, which is how to make lipid bilayers. But I thought that he will become a very successful academic, but I think what he has chosen to do is probably the best for him, which is he has become a very successful drug discoverer. He and his Stanford boss, Jim Spudich, and several others, of course, started a company which invented some drugs, which just got bought out by GlaxoSmithKline for $14 billion. Then came Arkarup, the guy in the middle. Thank you, Arkarup, for being part of the lab, one of the very smart guys, and also a very great singer. So many of our treks, monsoon treks, ultimately Arkarup will get there. He was not definitely the fastest. But if he gets there to the peak that we are aiming to, then he will start singing. And that's really the pleasure. And of course, good Ravindra Sangeet. And Orkurup now, of course, is a rising star using multiphoton microscopy, which he learned in the lab, and molecular biology he learned later, and behavioral neuroscientist, and in a very exclusive university, the Cold Spring Harbor Labs, where many of the major discoveries have taken place. Then come Murli. We needed to make peptides because we are tired of buying our own peptides, tired of not changing them. I'm very impatient when I keep buying things which I cannot modify. So same I was doing for peptides. I was buying peptides. I said I needed to modify it. I needed to put a isotopically labeled peptide in one place. And I can't wait 6 months for the order to go and come back. So we decided to start peptide synthesis. This me, who doesn't know anything about chemistry, is a physicist trying to his hands in biology. And we decided to buy a peptide spectrometer, peptide synthesizer, and everybody warned me against it. That this is bound for failure because 40 residue peptide is not so easy to make. Anyway, to cut a long story short, they didn't know I have a secret weapon. That's Murali. Murali was only slightly younger than me. He was working in a pharma company right here, actually same company that Dipanita worked in. And he wanted to do his secret, this thing was to do a PhD. I said, I want to do a PhD. I said, look, my students anyway take 5-6 years. You will do it on weekends. It will take 20 years for you to do a PhD. He said, I don't care. I'll do a PhD. That's fine. He used to come in Friday after his office, stay the night Friday, stay the night Saturday, stay the night Sunday, go directly to his office Monday morning. He had 2 kids and a wife, of course, which he used to, in that home, he used to go to Monday to Thursday. One of the hardest working individuals I have ever seen in my life and most motivated. And he took 7 years, but working just weekends. And he did a beautiful PhD. So, but the point is that he was already an experienced peptide peptide chemist. So we had no problem making long peptides, 40, 42, etc. And we never looked back. Coming back to the problem of, what do oligomers look like? This is now 10 years after Parijat. So Biddut, who is here, joined the lab. And he was one of the nicest gentlemen, of course, and also a serious researcher. How serious you can tell. My other project student, Rahul Deshmukh. Huh?
Rahul is on the.
Oh, Rahul is there. Okay. And Rahul was opposite. And you can see him laughing. And if I'm a Bengali and I like I have a sweet tooth. I like the sweets. But it's Rahul who really knew how to enjoy. Rahul will take a piece of cake and will feel, you should see his face glowing. And he'll put in the sweet piece in his mouth and his face will be glowing. So I bet this is in anticipation of some sweet treat right now. But Vidyut, of course, is nice and composed, serious researcher, and he did some wonderful things. The first conclusion of our amyloid oligomer story, we got together with Madhu, and we solved some of the atomic level structures. Of course, when Vidyut realized that he went to a different place and realized that people around him are even more serious than him, he started smiling. That's in Japan, okay? Rick in Japan, that's a more recent story. Okay, so then there was Anand Khan Das. Of course, nobody called him Anand Khan Das, but everybody called him by the full name, Anand Khan to dance. Of course, there is a sala after that, there is a part of the song. And here, Shayan is trying to teach Anand, Anand, come on, you can dance. And of course, Anand can dance. So, Anand actually started the speculation between a connection between 2 parts of my lab, which is serotonin, etc., and amyloids. And that actually still goes on. The next to him is Barun, who is also here. But Barun, so in between, Devanjan had joined. Devanjan, of course, was a heavyweight in every sense of the term. Okay, so in science, in his abilities, and of course in his weight. I'll tell you, Anand and Devanjan both were 100 plus kgs by quite a bit margin. And once Narayan Murthy came visiting the lab, and I made the mistake of sending him down with Anand and Devanjan. Little did I know that the D block lift, of course, cannot take both of them plus Narayan Murthy. So Narayan Murthy got stuck somewhere in the middle. And I was waiting. I took the stairs and waited downstairs, and they never came. So then I went upstairs, and I see a haggard-looking Narayan Murthy taking the stairs because somebody had opened it. He jumped out and took the stairs down. So anyway, that's this thing. But Devanjan started the Raman part of our work. And I have to thank, of course, all my friends like Gilbert Walker. I spent a sabbatical there. And then Devanjan was there for a while, learned all this plasmonics things and the membrane making. And our real Raman stuff started from there. Now, what is Devanjan doing here? This is the story. So you see, this is a microscope objective. Okay, this is the plate, that is the sample holder. And you can see a single molecule there, almost. So one day I see my lab student, I forget who it was, not Devanjan, carrying a big bag and walking towards the NMR room. And I asked, what's in the bag? Where are you going? He said, oh, somebody's birthday. I said, okay, somebody's birthday. Then I got a call that can you come to the NMR room because we had a meeting at that time. Maybe an hour later. So I went there and turned out it was my birthday and my 50th. And Devanjan and his friends in the lab got a special cake made in the shape of a microscope objective with a this thing. That was really, really touching. I really liked it. Oh, so this was something. And so Devanjan is some, of course, heavyweight. And Shimli had joined at that time. And his job was to teach Shimli and also to Rucha Pandit, who was a project student at that time, about things. And he always complained that you guys need to build up some stamina to do some work like this. For hours you'll have to align things, etc. So one day I think Amazon delivered some big barbells, weight things, etc. They're still there in my lab. Okay. Devanjan said, you'll have to every day, you'll have to lift these so that you have enough stamina to do the research. So after a few months of this training, there was a picture taken who has grown more muscle, and Rucha and Devanjan here. So you can try to tell who has more muscle. So they're showing off their muscles after their weight training. Okay, so then came Bappa, and Bappa was very passionate about science. So you'll tell him a story and he will catch on to it, latch on to it, and try to solve it. It was very nice. And he went further towards after Vidyut, towards solving the atomic level structure. As it forms, starts aggregating, monomer becomes dimer, tetramer, etc., and how the structure changes, perfecting the stuff that Vidyut and Venus, Madhu's student, did. So yeah, so it was good to have Bappa, and you heard him. Bappa actually visited me this week, actually, within the last few days, I think, maybe 7 days ago in Hyderabad. So here we are. And he has just got a faculty position in the US. So he was very happy about that. Then came Barun. So we had solved this problem of amyloid oligomers in solutions to the extent it was possible. And this is 15 plus years of work. It's true that even then it was not so known. It didn't get established to the extent that we thought it would be, that it is the crucial thing for amyloid toxicity. But we have solved the problem, that's for sure. So Barun was gifted in optics, optical theory. You can give him some equations, complicated 6-dimensional thing, which is typical for confocal microscopy, because there are 2 spaces. So you have to do 6-dimensional integrals. Very good in those, and also with his hands, the stuff that he said, putting the fiber. So he was joking. He was very good at those things. So he started nanosecond FCS, took FCS to a much faster scale, And he had this cool idea of doing, instead of structure-based drug discovery, nanosecond dynamics-based drug discovery. I'm really proud of that paper. And also for guide star microscopy, for which he was aligning the fiber. And I'm so happy that Barun has just joined as a faculty in Shaha Institute. Then came Shimli, and the real single molecule work starts. Shimli is here. She was, of course, a fan of Harry Potter. And here, I think she is trying to vanish Anirban, who is sitting next to her, by trying hard, abracadabra. Okay? Of course, Anirban was very nonchalant, but she tried hard. But she also tried hard in the lab, built the second version after Senthil of the microscope. Now it's a real single molecule microscope, and started this thing called single molecule photobleaching. We could understand how aggregates go into the membrane and what are the populations in the membrane of monomers, dimers, trimers, etc. And on the left side is Vicky, who also did a lot of membrane stuff. And this is Shimli now. So all photographs are sent by them. So Shimli these days travels around a lot, and she was in Egypt not so long ago. Anirban, I couldn't contact. I mean, I did contact, I didn't get a reply. He's actually not doing so well. There's some medical problems, etc. Anyway, so Anirban was, again, a bit of a loner, but is a fantastic student. Very serious, very capable. He started something new. And when I say, put it in this thing, this is one of our own games. I told you in the beginning, you define your, you actually try to copy some game that's being played. Somebody else invented it, which is fine because you need to do well, if you can do well. Or you try to invent your own game. So by this time, I was senior enough. If I don't do it now, when will I do it? So it's one of our two things that are still going on, which is proteins and Lego blocks. Sachi talked about it when she was here. I call it nowadays Lego blocks because they're protein pieces which are held in their shape by some cool chemistry. And we ask whether it can be a specific silencer for proteins. That's what Anup, somewhere there, is doing his PhD on. But this was started by Anirban, this guy. And he showed in that paper that ubiquitin can be changed. So, Ankur Gupta, so Shimli started two things. So Shimli started that and the interaction of neurotransmitters, and that Ankur Gupta really flourished with it. So there is Ankur in Copenhagen now, and so he really flourished with, his research really flourished with this neurotransmitter membrane interaction work, which Debshankar is finishing now. So Debshankar will be defending his thesis a week from today. So they did wonderful things. Vicky extended the nanosecond FCS, did some rotational FCS, and his Arpan, who you heard. Arpan's passion was photography, films, music, and of course science. He was a very good scientist. And he finished what Suman started, which is how single, so Shuman, Shimli, Arpan, and there are a few others in that, solved the problem of the best extent possible, how oligomers sit in the membrane. We invented several techniques while doing it, and that one just got published a couple of months ago. Of course, Arpan left for Cambridge, where he is, and sent me this picture, very happy there, when 2-3 months ago, he defended his PhD. And there's Debshankar. You heard Debshankar, the guy who attends group meetings while taking cricket shots. I heard that from, so yeah, he was caught by Jyotishman who are doing that. And so another gifted scientist, and great that he is there. And he sort of has finished the whole story about neurotransmitter membrane interaction and his work. And this is also, again, another of our own games. We just came up with it. We realized that it is a powerful idea that neurotransmitters can interact with membranes and there are consequences possible. And the physical part of it, I think he is pretty much finished in his thesis. So now it still looks, it looks even more promising now, and hopefully other people will take it up, or I will take it up. I'm trying to plan up my new these things. Of course, there is always this, people talked about the biophotonics family. So always this mixing, talking about science, personal things. Of course, you can see that at 3 a.m. near the gateway, they are of course discussing science. So that's Senthil from long time ago, right there, and Dev Shankar sitting down from now, 15 years apart. But yeah, I'm happy that they're well-lit family. Okay. So we had, so these are all my PhD students. I have to be quick. Lots of good dedicated bunch of project students. Neeraj, you heard, he's here. And Jenu, incomparable Jenu, because I'll tell him something, Jenu, I need it in a day. And I'll come back in a day, it'll be done. And I realize, I think that when I think something is doable in a day, it actually takes 2 days. So how can it be done? So it turns out he worked 24 hours straight. He would work 24 hours straight, then he will sleep 24 hours, or work 48 hours straight and sleep 24 hours. I don't know if Jenu still has that ability, but he was fantastic. If you need something, he'll get it done and then sleep. You'll not hear him for the next 2 days. So this is Rahul Deshmukh again in New York University. And we have had some great postdocs. Thank these people for that. Anup Rawat taught us how to construct amylin, which is a very difficult peptide to make. First time I took him to the US for a conference, first day he came back and says, somebody has offered me a postdocship right here. Can I go? I said, yeah, sure. So he is there. This is Priya James, a postdoc now in UPenn. First postdoc with me, and then other postdocs, Shibu, who is right here, built the first structures. You see, it's figuratively also, it's laying bricks. And with the first structure that held all the instruments around my laser table, around our laser table, then Shujit Ghosh, Umakanta Tripathi, very good, nice optical alignment hand, Umakanta, and Shankho Banerjee, who is very recent. And my right-hand men, which turned out to be mostly women, the scientific officers. Okay, so you see Madhuri, incomparable Madhuri. She was good in everything that you teach her something well, and she is very good at it. Aditi, Diana, and Parth, of course, are a different kind of people. They are the ones who actually could hold the biology in the lab together. They're all PhDs. Okay, so mostly PhD from Indian Institute of Science and other places. Parth is still there, and I think TIFR is lucky to have him. And Aditi and Diana are both in the US pursuing their dreams. And other scientific officers, Shushma was with me for a while, Ajay Patil, Dhaneshwar, Sachin, they all made whatever we could do, they all made it possible. And I had been really lucky to have lots of very good collaborators from across the world. But two whose name must be there in everything, these are people who really held my hands when I hit a wall. And I thought of something, I discussed things, they said, we can do it. So Madhu, you heard when we solved the structures at the atomic level or near atomic level for the oligomers. And Daniel is still doing it for us with the neurotransmitter membrane interactions. They are NMR physicists, and I'm really lucky to have them. There are lots of other people who have contributed. You heard Vidita, Shachi, Ravi, Koti, and Devashish speak, so I would not mention them separately. And then we did other things other than science. So there is the structure of the scientific structure that we had built. But there are other things that we wanted to do, which is community building. Why can't people get together and teach each other how to build instruments? Why should you always be buying instruments? Or, I'm really tired of, when I came in, tired of hearing this, that instrument is down and it has been down for 6 months. I mean, what is there? Just open it up and try to see what is there. And this impatience is there also in the community, but not all of us know how to build or open up and fix all the instruments. So we started by building fluorescence correlation spectrometers. You heard about the 2009 FCS. The 15th FCS will start happening tomorrow morning to give a talk at 9 o'clock. But this went, I did it for a while and I thought, oh, it takes a lot of energy and time. I said, okay, that's it. But many people from all over the world came in to say that no, let's continue it and we'll help you do it by teaching these, and my friends from all over. But three people, Jyotishman and Anindo and Shobhan, are the ones who are really running the show now. It takes tremendous amount of effort, but I think Indian spectroscopy community should really be thankful to them. So thanks to Shobhan and Anindo, Shobhan Sen from JNU and Anindo from IIT Bombay. There are other people who have the other pillar of community building, biophysics, not instrumentation, biophysics. And Shamir is here, and Shamir mentioned that we created, sitting in my office, we created Biophysics Paschim, and it's now run by Chaitanya Thale of ISAR Pune. So it's a 6-monthly, biannual meeting, has been going on from 2011. And we had the last meeting in August in ISAR Pune. So it's really nice that we have to create a grapevine, where you hear about results, you hear about what works, what doesn't, etc. That's missing in India because we are a small scientific community. So these are the two things that I'm really, it's like a bigger family for me. I'm trying to create something, Biophysics Deccan in Hyderabad now. So I end here saying thank you to all my PCS colleagues for this day. Okay, thank you so much. And I have to thank one more person. Thank you. That person made it all possible.
Thanks, Sudipta. So I think we'll move to the final agenda item at this point, and that is that we would felicitate Sudipta. So our co-chair Ankona Datta would do the honors. So let's have this. Yeah. 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 So let's first.
Okay, so this was very emotional, and what do we say after this, Sudipta? It doesn't seem like you are gone. Okay, we can just pick up the phone and call you and ask you those questions for which we get the answers. So nothing much more to say. We just have some little things for you, and some things from the department, some things from students and things. So we have, I just take them out. Okay, so we have this book. So we know you like history. So Parth got this book for you on Mumbai. Mumbai. Okay. Yeah. And we also like that we also know that we have something from my here, and for people has painted this
Oh, this is the one you showed.
Yes.
Wow.
Yeah. So, I will then want to call Deepanika. Deepanika and Gumba, please. Gumba. They have been an integral part of family. We have something for you.
Yeah.
Now I would like to call over all the students on the Biophotonics went here. Please, everybody is here. Multi-photo.
You're more present.
For all of you.
I think we're going to become on both sides.
Yeah, but you have some fears, right?
और ये क्या करें? Thank you so much.
Last on the list, I'd like to call JD and hand over the flower.
Of course. Go ahead. उसके बाद
And then you have light control. That's something.
Long time ago, I said. Thank you, Martin. Thank you for making the. I really appreciate it. Serve our community well. Okay, can we do a group photo? Is it
Yes,
possible?
just I have to mention one thing before we end. I would like to thank one special person, and of course I'll come to that. But first, where is Kumar? Kumar left. Huh. Okay, so I have to thank Kumar for putting the efforts and immediately agreeing to support this day. I'm not able to speak. I also want to thank ACS, Diksha and Diksha Gupta and Ajay. They were here. Unfortunately, they couldn't stay for that long. They wanted to say something, but they really thank you for being part of ACS in different roles, from author to, reviewer to editor, now executive editor. So thanks. This is a big thanks coming from their side, Sudipta. You put a lot of effort, so thank you for that. Also, I would like to call one person up here, Kaveri Huku from Atos. There was a sudden issue with something, and you know whom to call. There's an angel, and everything gets solved. So, Kaveri, can you please come here? And just could you say a few words?
Thank you. I mean, it's just that we really don't understand science, but we do see the kind of work that you do. So you even touch us, who are supposed to be commercial people. So we like to do a small bit. Count on us anytime you need us.
Kumar is back. So Kumar, could you just 2 words?
See, actually, I'm a salesman. I'm not a scientist. But he taught me when he was talking to Reinhard of spectrophysics. I learned what is mode locking, what is TIFR laser, how it is done. Then I have another opportunity. He is talking with Eric from France about the monochromator. I was just sitting and listening. Thank you, sir. That made me to sell more TIFR laser. Thank you.
And I cannot end this without bringing one person up. Well, Kadamji will speak in the dinner. Jayeshji, could you come, please?
I'll say only one thing. Sudipta ji, the most thing which touched me, जब भी उनको मिलता था, सबसे पहली बात आफ्टर रिटायरमेंट व्हेन आई केम हियर, व्हेन आई मेट हिम, सबसे पहले ये पूछते थे, हाउ इज योर वाइफ एंड हाउ इज योर डॉटर. ये मुझे बहुत टच करता था. सुदीप्ता की जर्नी जो है, दीपान्विता जी को अगर याद नहीं करेंगे तो उनको इंजस्टिस होगा. दीपान्विता जी को मैंने जितनी बार मिला हूँ, इंटरेक्टेड with her on very few occasions, but I found her down to earth. उनको होली के टाइम पे मैं मिलता था ज्यादा करके. एक बार मुझे याद है, वो इनिशियली जब पहली बार मैं उनको मिला था, मैं दूर खड़ा था, शी रिकॉग्नाइज मी, वो मेरे पास आए और मेरे साथ वो आपकी मुझे रंग लगाया था. और आपकी जर्नी में सबसे बड़ा हाथ उनका है. उनका भी, शी इज ऑल्सो वन ऑफ द पर्सन. और उनको सुदीप्ता के बारे में 1 मिनट में ज्यादा बोल. अभी 2-3 महीने पहले मैं सुदीप्ता जी के साथ बैठा था, तो उन्होंने एक बात मुझे कही कि हम लोग ये इंस्ट्रूमेंट्स बाहर से क्यों इंपोर्ट करते हैं, हम लोग इंडिया में क्यों नहीं बना सकते. यानी बहुत सारे इंस्ट्रूमेंट्स बनाते हैं, माइक्रोस्कोप, स्कोप या और कुछ पर्टिकुलर आइटम रहेगी, मुझे याद नहीं अभी, हम क्यों नहीं बना सकते. और तभी उनके मन में एक आक्रोश था, गुस्सा था, हम इंडिया में क्यों नहीं बना सकते, हम एक्सपोर्ट क्यों नहीं कर सकते. और उसमें खाली गुस्सा नहीं था, आक्रोश नहीं था, एक कमिटमेंट भी थी कि अब हम बनाएंगे और बेचेंगे. बोलने वाले तो बहुत लोग रहते हैं, हम लोग कैंटीन में बैठ के भी बहुत सारी बातें एक दूसरे के लिए बोलते हैं, पॉलिटिशियन के बारे में बोलते हैं, लेकिन जब करने की बात आई तो बोलेंगे नहीं वो करेगा, मैं नहीं करूंगा. लेकिन सुदीप्ता के बारे में मुझे उस दिन ऐसा फील हुआ, उनके बातों में कमिटमेंट थी कि आई विल डू एंड आई विल डू समथिंग. जो उनके दिमाग में जो भी आइडियाज रहेंगे, दैट इज डिफरेंट थिंग. सो आई विश हिम ऑल द बेस्ट. आई प्रे गॉड कि आपकी जो भी ड्रीम्स है वो फुलफिल हो. थैंक यू सो मच.
Thank you everyone for joining us today. It's been an incredible day for, I think, everyone, including Sudipta, and definitely for me. I thank Sudipta for agreeing kindly. It took us some time, but I think it was fulfilling. I want to thank a person in that Zoom, Daniel Huster. He had a big role to play as well for making this happen in the mind of Sudipta. So we have always loved you, Sudipta, and I don't think, how can you leave this place? I can't imagine, but that's what it is, and it's better. It's for the better. It's for the better. So I think that is what the mandate is. For the individual, there are places, there are experiences. This is your experience, but there are other experiences that you need to have. And I think this institute experienced you. Maybe where in the brick this will all go down, we don't know. This is the situation as this institute is going through. But I would say this, that remarkably, the void is never going to be filled. And I think this will be a legacy that will continue to inspire many. So thank you very much for every effort that you have done, and for always inspiring us. So thank you very much. It was a fantastic time. This is one of my best things in my life. So thank you.